Yes, we're 3 hours and 30 minutes into today's spacewalk, the 254th spacewalk in assembly, maintenance, and upgrades for the International Space Station. NASA flight surgeons Josh Cassada and Frank Rubio are currently at the 1B mass canister installing the lower left strut after they've fixed the upper triangle to the 1B mass canister. Frank Rubio will use the pistol grip tool this time to drive Bolt M21.
Rotate to your right, please. Clockwise. Clockwise, yep. Hold on there. Okay, it's engaged. Josh, if you can rotate clockwise 10 more degrees. That's at a hard stop there. Oh, is it? Okay. Xena EV1 is now at 5 undercooling.
Copy 5 on your TCV. Thanks, Josh.
All right, Xena, I'm ready for those settings on the solar PGT.
Okay, nice work. That'll be Alpha 1, clockwise 1.
Real quick, Frank, do you want me to align this with the upper triangle? Or just hold it in position for him?
Hold it in position for now. Once Frank gets that bolt started, then you can align the lower strut with the mounting bracket and check the pip pin lanyard is free of the clevis.
3.5 turns.
Copy, 3.5 turns. Okay, so Josh, you can go ahead and align that mounting bracket strut. And Frank, for you, your next PGT settings will be Bravo 7, clockwise 2.
Bravo 7, clockwise 2, copy.
Station, this is Houston. Are you ready for the event?
Houston, this is Station. I am ready for the event.
Good morning, America. This is Mission Control Houston. Please call station for a voice check.
Station, this is Gio Benitez at ABC News. How do you hear me?
I hear you loud and clear. I am ready for the event.
Commander Mann, thank you so much for joining us from the International Space Station. Such an honor. You've been there now for just over a month. First, tell us, what's it like to be up there right now?
In one word, absolutely incredible. I had some pretty high expectations, and they have all been exceeded. It's very busy on board the space station with science and spacewalks, but it's also very enjoyable and an incredible experience.
Commander, you have been training for this moment for almost 10 years now. So what was it like to step foot on the International Space Station?
Well, I didn't actually step foot. I kind of just floated through the hatch, which was an amazing experience. After all those years of training, it is really an overwhelming sense of emotions. There's, excitement. There's a lot of pride. There's a lot of anticipation for all the exciting work that we have ahead of us on board the space station.
And so many around this country are looking at you with pride because you are a first, right? The first Native American woman in space. What's it like to be a first? Do you feel a sort of weight on your shoulders?
I think it's great that we recognize firsts anytime they happen throughout the world. It gives a good message to the rest of the world and specifically to the younger generation that there are opportunities for all in this world. And I feel very proud to represent all Native Americans in space and just to represent my country and humans in space as well.
When you were growing up, did you look at the space program and say, hey, maybe I can be the first Native American woman to go there?
To be honest, I did not. I was certainly enamored with space and science, but that was not something as a child that I realized was an opportunity for me. It wasn't a little bit till later on in life that I realized that the path to becoming an astronaut is something that is feasible and something that I would like to go after as my dream.
You are one of the few people who have gone to space. And that is an incredible feat because not many humans have gone to space and be in that room where you are right now. What is your message to the young people who are watching you right now, especially young women?
It is such an honor to be in space, and my message to the younger generation is to dream. The first part is to have these ideas and these concepts in your mind of something that you really want to do and that you're passionate about. And then you need to figure out and visualize that path to get there. That starts with a good education, and it also starts with relying on people around you that will help you throughout your journey in order to achieve your dreams. It's something you can't do on your own. It's something that family and friends and support of other loved ones will help you along with.
Commander, a lot of folks don't understand the kind of science that happens there on the International Space Station. What are the projects that you're most excited about that you're working on right now?
We have over 200 experiments that we're conducting on board the International Space Station. A few of the upcoming experiments have to do with human science, specifically a vibrofabrication facility, which is actually growing 3D or printing 3D human cells in space. Because of microgravity, we can produce these cells in a better, more truer form than we can on Earth. And I really enjoy that because the applications involve humans in space and exploration, but will also benefit humans back on Earth.
We just saw that incredible Artemis I launch to the moon. Is that something that you hope to be a part of too?
Absolutely. I hope the entire world wants to be a part of the Artemis program. As we move forward to the moon, it's really the building blocks for our future exploration to Mars. And I think there'll be a role that each and every one of us can hopefully play in those missions.
You know, I was speaking with former NASA astronaut Katie Coleman, and she told me what a different world it would be if we had seen a woman walk on the moon. And now that very well may happen.
Absolutely. I think that is a very true possibility. We have such a diverse office in the astronaut corps now. I think you'll see all different types of people walking on the moon in the near future.
You've got several months left there on the International Space Station in zero gravity. What are you most looking forward to?
There is so much to look forward to, and I feel like time is moving so quickly. I want to capture it all, but we have a couple spacewalks coming up that will keep us busy around the holidays. We have another cargo vehicle coming to visit, and of course, a lot of science on board. Personally, I plan to also spend some time just looking out that cupola window at our beautiful planet Earth and being thankful for everything that we have in this life.
Has it changed you to see the world from that viewpoint?
I think it drives home some concepts that you're aware of. You're aware of the concept that Earth is an incredible, fragile little ball floating in the universe, and that we have people around the world that can be united in our one planet Earth. I'm aware of those concepts and you think about them, but when you're actually in space and you look back at the planet and you see just that fragile atmosphere, it really drives home that point. And it makes it very, very true in your heart how important it is that we take care of our planet and how important it is that we unite as human race.
Was there anything that surprised you when you got there to the International Space Station? You've got to live life very differently, don't you?
You live life very differently, yes. It's surprising how it takes you a couple days just to adapt to microgravity, to floating around where you still don't bump into things, just to feed yourself and not lose all of your food when you're sitting in Node 1 trying to enjoy your meal. But your body gets used to it, and it's still fun. I still smile every time I float through the lab and just marvel at the idea that I'm actually in microgravity.
We know that you are on the space station now with your Russian colleagues, and we know what's happening here on Earth with Russia and the United States and Ukraine. What's it like working with your Russian colleagues there now?
On board the space station, I think we have a very unique responsibility to maintain focus on the mission, and that's exactly what we do. We work closely with the cosmonauts. In fact, they had a Russian EVA yesterday that was very successful, and we helped them with some of the transfer of those tools. We have a good working relationship on board, and we focus on operating the International Space Station and conducting their science, and that is our mission focus.
Commander Mann, thank you so much for joining us. Such an honor.
Thank you very much. It is an honor from the International Space Station.
Godspeed.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants from Good Morning America Station. Please stand by while we configure video and audio communications.
Counting down to liftoff of Orion on its maiden voyage to the moon. Launch team can no longer recycle the count. Sound suppressor water now flowing under the ML. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis I. We rise together back to the moon and beyond.
All 4 RS-25 engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour. Hearing good control on the roll from teams in Mission Control Houston. All good calls so far. Now 30 seconds into the flight of Artemis I. First milestone will be for the vehicle to pass through max Q at about 1 minute and 9 seconds into launch. This is the greatest period of atmospheric force on the rocket. SLS now traveling 607 miles per hour. You're looking at 8.8 million pounds of maximum thrust. Quiet here in the loops in Mission Control. The 4 core stage engines are throttling down ahead of passing through max Q. Now 1 minute, 21 seconds into the flight, traveling at 1,420 miles per hour. The 4 core stage engines are back at maximum thrust. The next major milestone will be for the solid rocket boosters to cut off and jettison at about 2 minutes and 11 seconds into the flight, so about 30 seconds from now. Again, quiet here in Mission Control Houston as teams continue monitoring the flight of Artemis I. We're now 16 miles downrange from the launch pad at Kennedy Space Center, traveling over 2,800 miles per hour. Standing by for solid rocket booster jettison and shortly thereafter. Confirmation that the solid rocket boosters have separated these 177-foot boosters. Now the core stage continues to power the flight of Orion, all 4 RS-25 engines firing, traveling over 3,400 miles per hour, 46 miles downrange. 2 minutes and 36 seconds into the flight. Hearing nominal calls here in Mission Control Houston. We've still got 4 good engines on the core stage. Next up, we'll be looking for the service module fairing to separate. This is 3 15 by 15 foot fairing panels, providing structural support, protecting the service module. Those will separate at about 3 minutes and 11 seconds into flight, and very shortly thereafter will be followed by the launch abort system separation. Just over 3 minutes into the flight of Artemis I, now traveling over 4,060 miles per hour, 83 miles downrange. We just had confirmation that the service module fairing has separated. And that the launch abort system pyros have fired, separating those from Orion as well. For future crew members, we just heard the call for 3 engine press, meaning if SLS were to lose an engine at this point in the mission, we could still achieve a nominal mission. We would just have an extended main engine cutoff time. However, we still have 4 good engines, all at maximum thrust right now, powering the first flight of Artemis at 5,200 miles per hour, 148 miles downrange.
If you're just joining us, we're 3 hours and 30 minutes into today's spacewalk, the 254th spacewalk in assembly, maintenance, and upgrades for the International Space Station. NASA flight surgeons Josh Cassada and Frank Rubio are currently at the 1B mass canister installing the lower left strut after they've fixed the upper triangle to the 1B mass canister. Frank Rubio will use the pistol grip tool this time to drive Bolt M21.
Rotate to your right, please. Clockwise. Clockwise, yep. Hold on there. Okay, it's engaged. Josh, if you can rotate clockwise 10 more degrees. That's at a hard stop there. Oh, is it? Okay. Xena EV1's now at 5 undercooling.
Copy, 5 on your TCV. Thanks, Josh.
All right, Jim, I'm ready for those settings on the solar PGT.
Okay, nice work. That'll be Alpha 1, clockwise 1.
Real quick, Frank, do you want me to align this with the upper triangle? Or just hold it in position for him?
Hold it in position for now. Once Frank gets that bolt started, then you can align the lower strut with the mounting bracket and check the pip pin lanyard is free of the clevis.
Okay, 3.5 turns.
Copy, 3.5 turns. Okay, so Josh, you can go ahead and align that mounting bracket strut. And Frank, for you, your next PGT settings will be Bravo 7, clockwise 2.
Bravo 7, clockwise 2, copy.
Station, this is Houston. Are you ready for the event?
Houston, this is Station. I am ready for the event.
Good morning, America. This is Mission Control Houston. Please call station for a voice check.
Station, this is Gio Benitez at ABC News. How do you hear me?
I hear you loud and clear. I am ready for the event.
Oh, Commander Mann, thank you so much for joining us from the International Space Station. Such an honor. You've been there now for just over a month. First, tell us, what's it like to be up there right now?
In one word, absolutely incredible. I had some pretty high expectations, and they have all been exceeded. It's very busy on board the space station with science and spacewalks, but it's also very enjoyable and an incredible experience.
Commander, you have been training for this moment for almost 10 years now. So what was it like to step foot on the International Space Station?
Well, I didn't actually step foot. I kind of just floated through the hatch, which was an amazing experience. After all those years of training, it is really an overwhelming sense of emotions. There's, excitement. There's a lot of pride. There's a lot of anticipation for all the exciting work that we have ahead of us on board the space station.
And so many around this country are looking at you with pride because you are a first, right? The first Native American woman in space. What's it like to be a first? Do you feel a sort of weight on your shoulders?
I think it's great that we recognize firsts anytime they happen throughout the world. It gives a good message to the rest of the world and specifically to the younger generation that there are opportunities for all in this world. And I feel very proud to represent all Native Americans in space and just to represent my country and humans in space as well.
When you were growing up, did you look at the space program and say, hey, maybe I can be the first Native American woman to go there?
To be honest, I did not. I was certainly enamored with space and science, but that was not something as a child that I realized was an opportunity for me. It wasn't a little bit till later on in life that I realized that the path to becoming an astronaut is something that is feasible and something that I would like to go after as my dream.
You are one of the few people who have gone to space. And that is an incredible feat because not many humans have gone to space and be in that room where you are right now. What is your message to the young people who are watching you right now, especially young women?
It is such an honor to be in space, and my message to the younger generation is to dream. The first part is to have these ideas and these concepts in your mind of something that you really want to do and that you're passionate about. And then you need to figure out and visualize that path to get there. That starts with a good education, and it also starts with relying on people around you that will help you throughout your journey in order to achieve your dreams. It's something you can't do on your own. It's something that family and friends and support of other loved ones will help you along with.
Commander, a lot of folks don't understand the kind of science that happens there on the International Space Station. What are the projects that you're most excited about that you're working on right now?
We have over 200 experiments that we're conducting on board the International Space Station. A few of the upcoming experiments have to do with human science, specifically a vibrofabrication facility, which is actually growing 3D or printing 3D human cells in space. Because of microgravity, we can produce these cells in a better, more truer form than we can on Earth. And I really enjoy that because the applications involve humans in space and exploration, but will also benefit humans back on Earth.
We just saw that incredible Artemis I launch to the moon. Is that something that you hope to be a part of too?
Absolutely. I hope the entire world wants to be a part of the Artemis program. As we move forward to the moon, it's really the building blocks for our future exploration to Mars. And I think there'll be a role that each and every one of us can hopefully play in those missions.
You know, I was speaking with former NASA astronaut Katie Coleman, and she told me what a different world it would be if we had seen a woman walk on the moon. And now that very well may happen.
Absolutely. I think that is a very true possibility. We have such a diverse office in the astronaut corps now. I think you'll see all different types of people walking on the moon in the near future.
You've got several months left there on the International Space Station in zero gravity. What are you most looking forward to?
There is so much to look forward to, and I feel like time is moving so quickly. I want to capture it all, but we have a couple spacewalks coming up that will keep us busy around the holidays. We have another cargo vehicle coming to visit, and of course, a lot of science on board. Personally, I plan to also spend some time just looking out that cupola window at our beautiful planet Earth and being thankful for everything that we have in this life.
Has it changed you to see the world from that viewpoint?
I think it drives home some concepts that you're aware of. You're aware of the concept that Earth is an incredible, fragile little ball floating in the universe, and that we have people around the world that can be united in our one planet Earth. I'm aware of those concepts and you think about them, but when you're actually in space and you look back at the planet and you see just that fragile atmosphere, it really drives home that point, and it makes it very, very true in your heart how important it is that we take care of our planet and how important it is that we unite as human race.
Was there anything that surprised you when you got there to the International Space Station? You've got to live life very differently, don't you?
You live life very differently, yes. It's surprising how it takes you a couple days just to adapt to microgravity, to floating around where you still don't bump into things, just to feed yourself and not lose all of your food when you're sitting in Node 1 trying to enjoy your meal. But your body gets used to it, and it's still fun. I still smile every time I float through the lab and just marvel at the idea that I'm actually in microgravity.
We know that you are on the space station now with your Russian colleagues, and we know what's happening here on Earth with Russia and the United States and Ukraine. What's it like working with your Russian colleagues there now?
On board the space station, I think we have a very unique responsibility to maintain focus on the mission, and that's exactly what we do. We work closely with the cosmonauts. In fact, they had a Russian EVA yesterday that was very successful, and we helped them with some of the transfer of those tools. We have a good working relationship on board, and we focus on operating the International Space Station and conducting their science, and that is our mission focus.
Commander Mann, thank you so much for joining us. Such an honor.
Thank you very much. It is an honor from the International Space Station.
Godspeed.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants from Good Morning America Station. Please stand by while we configure video and audio communications.
The move to the launch pad for Artemis I, a visual treat in the sky, and a NASA tech demo hitches a ride to space. A few of the stories to tell you about this week at NASA. Teams at our Kennedy Space Center moved the Space Launch System rocket and Orion spacecraft to Launch Pad 39B ahead of our uncrewed Artemis I flight test around the moon and back. Artemis I is currently targeted for launch no earlier than November 16th. The second total lunar eclipse of 2022 happened on November 8th. This 10-image composite captured at Kennedy Space Center shows what the moon looked like during various phases of the eclipse. If you're wondering about the next total lunar eclipse, that won't happen until March 2025. NASA's Lofted technology demonstration hitched a ride to space with NOAA's JPSS-2 weather satellite on November 10th. JPSS-2 is expected to help improve weather forecasts, and Lofted is an inflatable heat shield that could protect spacecraft during atmospheric entry and re-entry. A Northrop Grumman Cygnus resupply spacecraft launched on November 7th with more than 8,200 pounds of science investigations and cargo for the International Space Station. This is the company's 18th space station cargo flight for NASA. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Station, this is Houston. Are you ready for the event?
Houston, this is Station. I am ready for the event.
Good morning, America. This is Mission Control Houston. Please call station for a voice check.
Station, this is Gio Benitez at ABC News. How do you hear me?
I hear you loud and clear. I am ready for the event.
Commander Mann, thank you so much for joining us from the International Space Station. Such an honor. You've been there now for just over a month. First, tell us, what's it like to be up there right now?
In one word, absolutely incredible. I had some pretty high expectations, and they have all been exceeded. It's very busy on board the space station with science and spacewalks, but it's also very enjoyable and an incredible experience.
Commander, you have been training for this moment for almost 10 years now. So what was it like to step foot on the International Space Station?
Well, I didn't actually step foot. I kind of just floated through the hatch, which was an amazing experience. After all those years of training, it is really an overwhelming sense of emotions. There's, excitement. There's a lot of pride. There's a lot of anticipation for all the exciting work that we have ahead of us on board the space station.
And so many around this country are looking at you with pride because you are a first, right? The first Native American woman in space. What's it like to be a first? Do you feel a sort of weight on your shoulders?
I think it's great that we recognize firsts anytime they happen throughout the world. It gives a good message to the rest of the world and specifically to the younger generation that there are opportunities for all in this world. And I feel very proud to represent all Native Americans in space and just to represent my country and humans in space as well.
When you were growing up, did you look at the space program and say, hey, maybe I can be the first Native American woman to go there?
To be honest, I did not. I was certainly enamored with space and science, but that was not something as a child that I realized was an opportunity for me. It wasn't a little bit till later on in life that I realized that the path to becoming an astronaut is something that is feasible and something that I would like to go after as my dream.
You are one of the few people who have gone to space. And that is an incredible feat because not many humans have gone to space and be in that room where you are right now. What is your message to the young people who are watching you right now, especially young women?
It is such an honor to be in space, and my message to the younger generation is to dream. The first part is to have these ideas and these concepts in your mind of something that you really want to do and that you're passionate about. And then you need to figure out and visualize that path to get there. That starts with a good education, and it also starts with relying on people around you that will help you throughout your journey in order to achieve your dreams. It's something you can't do on your own. It's something that family and friends and support of other loved ones will help you along with.
Commander, a lot of folks don't understand the kind of science that happens there on the International Space Station. What are the projects that you're most excited about that you're working on right now?
We have over 200 experiments that we're conducting on board the International Space Station. A few of the upcoming experiments have to do with human science, specifically a vibrofabrication facility, which is actually growing 3D or printing 3D human cells in space. Because of microgravity, we can produce these cells in a better, more truer form than we can on Earth. And I really enjoy that because the applications involve humans in space and exploration, but will also benefit humans back on Earth.
We just saw that incredible Artemis I launch to the moon. Is that something that you hope to be a part of too?
Absolutely. I hope the entire world wants to be a part of the Artemis program. As we move forward to the moon, it's really the building blocks for our future exploration to Mars. And I think there'll be a role that each and every one of us can hopefully play in those missions.
You know, I was speaking with former NASA astronaut Katie Coleman, and she told me what a different world it would be if we had seen a woman walk on the moon. And now that very well may happen.
Absolutely. I think that is a very true possibility. We have such a diverse office in the astronaut corps now. I think you'll see all different types of people walking on the moon in the near future.
You've got several months left there on the International Space Station in zero gravity. What are you most looking forward to?
There is so much to look forward to, and I feel like time is moving so quickly. I want to capture it all, but we have a couple spacewalks coming up that will keep us busy around the holidays. We have another cargo vehicle coming to visit, and of course, a lot of science on board. Personally, I plan to also spend some time just looking out that cupola window at our beautiful planet Earth and being thankful for everything that we have in this life.
Has it changed you to see the world from that viewpoint?
drives home some concepts that you're aware of. You're aware of the concept that Earth is an incredible, fragile little ball floating in the universe, and that we have people around the world that can be united in our one planet Earth. I'm aware of those concepts and you think about them, but when you're actually in space and you look back at the planet and you see just that fragile atmosphere, it really drives home that point, and it makes it very, very true in your heart how important it is that we take care of our planet and how important it is that we unite as human race.
Was there anything that surprised you when you got there to the International Space Station? You've got to live life very differently, don't you?
You live life very differently, yes. It's surprising how it takes you a couple days just to adapt to microgravity, to floating around where you still don't bump into things, just to feed yourself and not lose all of your food when you're sitting in Node 1 trying to enjoy your meal. But your body gets used to it, and it's still fun. I still smile every time I float through the lab and just marvel at the idea that I'm actually in microgravity.
We know that you are on the space station now with your Russian colleagues, and we know what's happening here on Earth with Russia and the United States and Ukraine. What's it like working with your Russian colleagues there now?
On board the space station, I think we have a very unique responsibility to maintain focus on the mission, and that's exactly what we do. We work closely with the cosmonauts. In fact, they had a Russian EVA yesterday that was very successful, and we helped them with some of the transfer of those tools. We have a good working relationship on board, and we focus on operating the International Space Station and conducting their science, and that is our mission focus.
Commander Mann, thank you so much for joining us. Such an honor.
Thank you very much. It is an honor from the International Space Station.
Godspeed.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants from Good Morning America Station. Please stand by while we reconfigure video and audio communications.
Counting down to liftoff of Orion on its maiden voyage to the moon. Launch team can no longer recycle the count. Sound suppressor water now 15. Flowing under the ML. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis I. We rise together back to the moon and beyond.
All 4 RS-25 engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour. Hearing good control on the roll from teams in Mission Control Houston. All good calls so far. Now 30 seconds into the flight of Artemis I. First milestone will be for the vehicle to pass through max Q at about 1 minute and 9 seconds into launch. This is the greatest period of atmospheric force on the rocket. SLS now traveling 607 miles per hour. You're looking at 8.8 million pounds of maximum thrust. Quiet here in the loops in mission control. The 4 core stage engines are throttling down ahead of passing through max Q. Now 1 minute, 21 seconds into the flight, traveling at 1,420 miles per hour. The 4 core stage engines are back at maximum thrust. The next major milestone will be for the solid rocket boosters to cut off and jettison at about 2 minutes and 11 seconds into the flight, so about 30 seconds from now. Again, quiet here in Mission Control Houston as teams continue monitoring the flight of Artemis I. We're now 16 miles downrange from the launch pad at Kennedy Space Center, traveling over 2,800 miles per hour. Standing by for solid rocket booster jettison and shortly thereafter. Confirmation that the solid rocket boosters have separated, these 177-foot boosters. Now the core stage continues to power the flight of Orion, all 4 RS-25 engines firing, traveling over 3,400 miles per hour, 46 miles downrange. 2 minutes and 36 seconds into the flight. Hearing nominal calls here in Mission Control Houston. We've still got 4 good engines on the core stage. Next up, we'll be looking for the service module fairing to separate. This is 3 15 by 15 foot fairing panels, providing structural support, protecting the service module. Those will separate at about 3 minutes and 11 seconds into flight, and very shortly thereafter will be followed by the launch abort system separation. Just over 3 minutes into the flight of Artemis I, now traveling over 4,060 miles per hour, 83 miles downrange. We just had confirmation that the service module fairing has separated. And that the launch abort system pyros have fired, separating those from Orion as well. For future crew members, we just heard the call for 3-engine press, meaning if SLS were to lose an engine at this point in the mission, we could still achieve a nominal mission. We would just have an extended main engine cutoff time. However, we still have 4 good engines, all at maximum thrust right now, powering the first flight of Artemis at 5,200 miles per hour, 148 miles downrange.
If you're just joining us, we're 3 hours and 30 minutes into today's spacewalk, the 254th spacewalk in assembly, maintenance, and upgrades for the International Space Station. NASA flight surgeons Josh Cassada and Frank Rubio are currently at the 1B mass canister installing the lower left strut after they've fixed the upper triangle to the 1B mass canister. Frank Rubio will use the pistol grip tool this time to drive Bolt M21.
Rotate to your right, please. Clockwise. Clockwise, yep. Hold on there. Okay, it's engaged. Josh, if you can rotate clockwise 10 more degrees. That's at a hard stop there. Oh, is it? Okay. Xena EV1 now at 5 on the cooling.
Copy, 5 on your TCV. Thanks, Josh.
All right, Xena, I'm ready for those settings on the solar PGT.
Okay, nice work. That'll be Alpha 1, clockwise 1.
Real quick, Frank, do you want me to align this with the upper triangle? Or just hold it in position for him?
Hold it in position for now. Once Frank gets that bolt started, then you can align the lower strut with the mounting bracket and check the pip pin lanyard is free of the clevis.
Okay, 3.5 turns.
Copy, 3.5 turns. Okay, so Josh, you can go ahead and align that mounting bracket strut. And Frank, for you, your next PGT settings will be Bravo 7, clockwise 2.
Bravo 7, clockwise 2, copy.
Station, this is Houston. Are you ready for the event?
Houston, this is Station. I am ready for the event.
Good morning, America. This is Mission Control Houston. Please call station for a voice check.
Station, this is Gio Benitez at ABC News. How do you hear me?
I hear you loud and clear. I am ready for the event.
Oh, Commander Mann, thank you so much for joining us from the International Space Station. Such an honor. You've been there now for just over a month. First, tell us, what's it like to be up there right now?
In one word, absolutely incredible. I had some pretty high expectations, and they have all been exceeded. It's very busy on board the space station with science and spacewalks, but it's also very enjoyable and an incredible experience.
Commander, you have been training for this moment for almost 10 years now. So what was it like to step foot on the International Space Station?
Well, I didn't actually step foot. I kind of just floated through the hatch, which was an amazing experience. After all those years of training, it is really an overwhelming sense of emotions. There's, excitement. There's a lot of pride. There's a lot of anticipation for all the exciting work that we have ahead of us on board the space station.
And so many around this country are looking at you with pride because you are a first, right? The first Native American woman in space. What's it like to be a first? Do you feel a sort of weight on your shoulders?
I think it's great that we recognize firsts anytime they happen throughout the world. It gives a good message to the rest of the world and specifically to the younger generation that there are opportunities for all in this world. And I feel very proud to represent all Native Americans in space and just to represent my country and humans in space as well.
When you were growing up, did you look at the space program and say, hey, maybe I can be the first Native American woman to go there?
To be honest, I did not. I was certainly enamored with space and science, but that was not something as a child that I realized was an opportunity for me. It wasn't a little bit till later on in life that I realized that the path to becoming an astronaut is something that is feasible and something that I would like to go after as my dream.
You are one of the few people who have gone to space. And that is an incredible feat because not many humans have gone to space and be in that room where you are right now. What is your message to the young people who are watching you right now, especially young women?
It is such an honor to be in space, and my message to the younger generation is to dream. The first part is to have these ideas and these concepts in your mind of something that you really want to do and that you're passionate about. And then you need to figure out and visualize that path to get there. That starts with a good education, and it also starts with relying on people around you that will help you throughout your journey in order to achieve your dreams. It's something you can't do on your own. It's something that family and friends and support of other loved ones will help you along with.
Commander, a lot of folks don't understand the kind of science that happens there on the International Space Station. What are the projects that you're most excited about that you're working on right now?
We have over 200 experiments that we're conducting on board the International Space Station. A few of the upcoming experiments have to do with human science, specifically a vibrofabrication facility, which is actually growing 3D or printing 3D human cells in space. Because of microgravity, we can produce these cells in a better, more truer form than we can on Earth. And I really enjoy that because the applications involve humans in space and exploration, but will also benefit humans back on Earth.
We just saw that incredible Artemis I launch to the moon. Is that something that you hope to be a part of too?
Absolutely. I hope the entire world wants to be a part of the Artemis program. As we move forward to the moon, it's really the building blocks for our future exploration to Mars. And I think there'll be a role that each and every one of us can hopefully play in those missions.
You know, I was speaking with former NASA astronaut Katie Coleman, and she told me what a different world it would be if we had seen a woman walk on the moon. And now that very well may happen.
Absolutely. I think that is a very true possibility. We have such a diverse office in the astronaut corps now. I think you'll see all different types of people walking on the moon in the near future.
You've got several months left there on the International Space Station in zero gravity. What are you most looking forward to?
There is so much to look forward to, and I feel like time is moving so quickly. I want to capture it all, but we have a couple spacewalks coming up that will keep us busy around the holidays. We have another cargo vehicle coming to visit, and of course, a lot of science on board. Personally, I plan to also spend some time just looking out that cupola window at our beautiful planet Earth and being thankful for everything that we have in this life.
Has it changed you to see the world from that viewpoint?
I think it drives home some concepts that you're aware of. You're aware of the concept that Earth is an incredible, fragile little ball floating in the universe, and that we have people around the world that can be united in our one planet Earth. I'm aware of those concepts and you think about them, but when you're actually in space and you look back at the planet and you see just that fragile atmosphere, it really drives home that point, and it makes it very, very true in your heart how important it is that we take care of our planet and how important it is that we unite as human race.
Was there anything that surprised you when you got there to the International Space Station? You've got to live life very differently, don't you?
You live life very differently, yes. It's surprising how it takes you a couple days just to adapt to microgravity, to floating around where you still don't bump into things, just to feed yourself and not lose all of your food when you're sitting in Node 1 trying to enjoy your meal. But your body gets used to it, and it's still fun. I still smile every time I float through the lab and just marvel at the idea that I'm actually in microgravity.
We know that you are on the space station now with your Russian colleagues, and we know what's happening here on Earth with Russia and the United States and Ukraine. What's it like working with your Russian colleagues there now?
On board the space station, I think we have a very unique responsibility to maintain focus on the mission, and that's exactly what we do. We work closely with the cosmonauts. In fact, they had a Russian EVA yesterday that was very successful, and we helped them with some of the transfer of those tools. We have a good working relationship on board, and we focus on operating the International Space Station and conducting their science, and that is our mission focus.
Commander Mann, thank you so much for joining us. Such an honor.
Thank you very much. It is an honor from the International Space Station.
Godspeed.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants from Good Morning America Station. Please stand by while we configure video and audio communications.
Counting down to liftoff of Orion on its maiden voyage to the moon. Launch team can no longer recycle the count. Sound suppressor water now
15.
Flowing under the ML. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis I. We rise together back to the moon and beyond.
All 4 RS-25 engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour. Hearing good control on the roll from teams in Mission Control Houston. All good calls so far. Now 30 seconds into the flight of Artemis I. First milestone will be for the vehicle to pass through max Q at about 1 minute and 9 seconds into launch. This is the greatest period of atmospheric force on the rocket. SLS now traveling 607 miles per hour. You're looking at 8.8 million pounds of maximum thrust. Quiet here in the loops in Mission Control. The 4 core stage engines are throttling down ahead of passing through max Q. Now 1 minute, 21 seconds into the flight, traveling at 1,420 miles per hour. The 4 core stage engines are back at maximum thrust. The next major milestone will be for the solid rocket boosters to cut off and jettison at about 2 minutes and 11 seconds into the flight, so about 30 seconds from now. Again, quiet here in Mission Control Houston as teams continue monitoring the flight of Artemis I. We're now 16 miles downrange from the launch pad at Kennedy Space Center, traveling over 2,800 miles per hour. Standing by for solid rocket booster jettison and shortly thereafter. Confirmation that the solid rocket boosters have separated these 177-foot boosters. Now the core stage continues to power the flight of Orion, all 4 RS-25 engines firing, traveling over 3,400 miles per hour, 46 miles downrange. 2 minutes and 36 seconds into the flight. Hearing nominal calls here in Mission Control Houston. We've still got 4 good engines on the core stage. Next up, we'll be looking for the service module fairing to separate. This is 3 15 by 15 foot fairing panels, providing structural support, protecting the service module. Those will separate at about 3 minutes and 11 seconds into flight, and very shortly thereafter will be followed by the launch abort system separation. Just over 3 minutes into the flight of Artemis I, now traveling over 4,060 miles per hour, 83 miles downrange. We just had confirmation that the service module fairing has separated. And that the launch abort system pyros have fired, separating those from Orion as well. For future crew members, we just heard the call for 3 engine press, meaning if SLS were to lose an engine at this point in the mission.
We just finished fueling the spaceship, and we moved it to the LASA facility, the Launch Abort System facility, to put the launch abort system on the top of Orion.
And in July 2019, teams completed a critical test, the Ascent Abort 2 flight test, to validate the launch abort system works as expected. After reaching an altitude of about 6 miles, where the test spacecraft experienced high-stress conditions expected during launch, the abort sequence triggered. Within milliseconds, the abort motor fired to pull the crew module away to safety. Its attitude control motor flipped the capsule into the proper orientation, and the jettison motor fired to release the crew module for a splashdown in the Atlantic Ocean.
I feel, just honored and humbled every day to be able to work on this.
This rocket is just going to be absolutely amazing.
Now that the spacecraft's launch abort system is securely in place, Orion is ready for the next stop on its path to the pad, the Vehicle Assembly Building. Once inside, the spacecraft will be placed on top of the Space Launch System rocket, the most powerful rocket the world has ever seen.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
The sun would first stir life on our planet. Gradual shiftings and upheavals would bury creatures and plants beneath the surface of the Earth. There, they would fossilize, eventually turning into huge reservoirs of gas and coal.
Oil made possible one of the greatest inventions of history, the internal combustion engine, which gave us mastery over the air.
Pollution grew around us, until one day, at last, we've noticed that something had gone wrong with our once pretty world. Just in time, the satellite now gives us a view of pollution impossible to get in any other way.
Scientists and researchers continue to develop various technologies to cut fuel consumption through aircraft structure and engine design.
Lightweight wires and electronics replace mechanical linkage.
NASA researchers see vertical takeoff aircraft as commercially useful. These types of aircraft use less room for takeoff and landing and keep noise and air pollution lower than our present commercial planes.
One of the most unusual and highly experimental aircraft ever tested at Dryden was the Gossamer Albatross. The Albatross was human-powered and pedaled like a bicycle. The man who designed the Albatross also built the Gossamer Penguin, the world's first flight-worthy sun-powered plane.
ERAST is NASA's environmental research, aircraft, and sensor technology program, and its mission is to develop aircraft that are capable of flying very high and very slowly, primarily to do atmospheric sampling and monitoring of the global environment.
Solar power offers some unique capability for flying in the stratosphere.
The Helio should be able to stay aloft for up to 6 months at a time to function very much as an atmospheric satellite.
What's very unique to the solar-powered airplanes is that they are not polluting the very atmosphere that they're trying to take samples from, so they're ideally suited for that purpose.
These vehicles can help us attain a desirable balance between technology and nature. The stakes are high as we speed toward a challenging future.
Solar-powered aircraft don't really work well at nighttime. This is a way of compensating for the inability to get energy at night. The airplane flies off the energy provided by the laser.
This is the world's first demonstration of the application of laser energy to a flight vehicle to achieve truly fuelless flight.
NASA Aeronautics continued its green aviation initiatives. Their goal? To make air travel quieter, cleaner, and more efficient. while increasing the safety and comfort of passengers.
With this mandate to significantly lower noise and emissions and increase performance for subsonic aircraft, there will be a need to address virtually every aspect of the current aircraft configuration.
We're using a blended alternative fuel to evaluate the impact of different fuels on the emissions of the aircraft.
People have done life cycle studies to look at the carbon balance, which takes into account the amount of energy that you use in growing the plant, processing the oil. Some of the studies have shown about a 75% reduction in the amount of CO2 that you get using camelina compared to a conventional petroleum-based fuel.
NASA started investigating alternative fuels as a way of reducing the carbon emissions from aircraft, but there's other benefits of these fuels. They produce much lower levels of soot, and also they do not have sulfur contaminants.
Hopefully there will be a fairly significant return on the investment in terms of improved public health and environment.
Everything within subsonic aviation now is looking for efficiency. We're looking at structures to make aircraft lighter. We're looking at various propulsion systems in order to make them more fuel efficient, and we're looking at configurations to lower the noise impact of community noise, essentially looking at an environmentally responsible aircraft.
We really think this airplane is revolutionary. It's a big jump in technology from the tube and wing kind of airplanes that you see today. It's much more efficient. I like to say it's like a hybrid car compared to a regular car.
It's exciting to think that we're contributing to the green aircraft of the future.
The aircraft now can be programmed to have, for example, engines that are more fuel efficient. Control the engines separately and also more closely and carefully.
This is NASA's first all-electric crewed aircraft.
We can use electric propulsion systems and aircraft design in an interactive way. The wing itself is designed so that the electric motors enable extra efficiency in the wing itself.
There's several different types of airplanes that can benefit from electric propulsion. The one that's gaining a lot of interest right now is the smaller version, the air taxi type vehicle.
In doing the work of developing these systems, integrating these systems and so forth, we have helped industry along their path.
We've been able to deliver lessons learned on batteries, on how you do the power electronics, how you build up the motors. And so X-57 really has been a pathfinder early on for electric propulsion.
Next generation of vehicles, they're going to be much greener and much more efficient types of propulsive technology.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that SOFIA can do.
Right now, we are looking at the dawn of a new era of aviation.
Something has now emerged that might make even our most elegant theories workable.
Scientists developed equipment which would be able to think.
Machines that do things and make choices without human beings. That uncanny spectacle is automation. Capable of storing,
processing.
Calculations that would ordinarily take hundreds of man-hours. Unique ability to check itself on possible errors.
Cheaper and quicker and better.
Electric eyes, limit switches, servo mechanisms.
Secretary, librarian, banker, teacher, medical technician, bridge partner.
Volumes of changing data into a continuous flow of interpretations. Aladdin's lamp couldn't do more.
Joy, loading machine, electric drill, it's all automation.
Computers have taken wing.
By the late 1960s, digital computers had become more available.
Using data about the aircraft's performance, the computers vote on the correct amount of control deflection to make in response to the pilot's stick and rudder movements.
This system could make air travel of the future smoother and safer by reducing aircraft vibration through automatic response from the computer to the aircraft controls.
We did the digital engine control. We had an early large digital computer that ran the engine and the inlet and exhaust system.
We did an integrated control study to provide digital control of the inlets, autopilot, throttle, air data, and navigation system. A digital computer here, major improvement in the capability of the airplane.
Test pilots are flying a plane without having to leave the ground. It's a new way of flight testing advanced aircraft that's both more economical and less hazardous. A research pilot in a realistically recreated cockpit on the ground, complete with flight controls, flies the remotely piloted craft using computers and television.
The airplane includes computers. Those computers take stick command and
continuously monitor what the airplane is doing and compares it to what the pilot wants the airplane to do.
The computer signals the control surfaces to not only execute the pilot's maneuver, but also to counter any attempt by the X-29 to veer out of control.
Fly up.
Yikes! No doubt about it. We didn't get a roll from that one.
New initiative in the artificial intelligence area, and it's called aircraft automation. The technologies that end up coming out of this would be autonomous flight vehicle technology.
ERAS stands for Environmental Research Aircraft and Sensor Technology. Platforms that could fly higher and longer than the current piloted airplanes. Do science missions and other commercial applications.
Primarily the dull, dirty, and dangerous.
We can go all the way up to where the airplane can fly itself completely autonomously with no input from anyone on the ground.
Fly up to 50, 60,000 feet, fly a circle loop perhaps over a city, providing the capability that a satellite now does.
Now that we can fly for on the order of 8 to 10 to 12 hours, we can look at long duration processes, biogeochemical cycling, looking at carbon and nitrogen moving through an ecosystem.
To sort of kickstart a commercial UAV industry.
The technology that we've seen here in this test is what would be the foundation for a follow-on program to really address the issue of how can UAVs routinely operate in the national airspace system.
The primary benefit of this technology is the ability of it to adapt to the unknown, whether it be a system failure, battle damage, icing on the wing, or flying in an unknown atmospheric environment.
The aircraft may be able to be flown, but the pilot may or may not be able to find a solution to how to fly that aircraft.
Neural net control systems where the controls are going to teach themselves and keep being smarter from flight to flight.
It can reconfigure the airplane in an optimal way in order to give you the best flying qualities.
Okay. There is no operator of the vehicle itself on the ground. Basically, the role that the human plays is more in managing the mission, an orchestra director, not the instrument player.
The vehicle will complete all the autonomous actions necessary to release the weapon optimally positioned to hit the target.
One of the next things that we'll be demonstrating in UCAV is the collaboration amongst aircraft. How do sets of aircraft interact together in almost a social form?
We're going to examine the feasibility and technical utility of actually being able to fly two airplanes or multiple aircraft in formation with each other.
Now the trick to this is to make sure that they fly in formation closely enough that they can extract the advantage without obviously running into each other.
The station keeping would be fairly close proximity for hours. The workload on the flight crew would be quite high, so we started to develop autonomous algorithms to do the station keeping. So you basically would have an autopilot that you could engage.
The computers are flying the airplane without your
stick input, even in the system, to allow a piloted airplane to take 2, 3, or 4 unpiloted vehicles on a long-distance trip.
We're just getting started on this technology. We'll use this technology to refuel unoccupied combat air vehicles.
The basket's slightly moving. Looks like it's going high. Okay, it detected a miss and came back on its own. So I did not do anything. She's got it. She's got it. Congratulations, guys. That was fantastic.
The Autonomous Soaring Project has one simple goal, is to program a small UAV to soar in thermals, similar to the way a glider pilot or birds do. It has been reprogrammed to automatically detect that it's in an updraft and then use that updraft by circling. There's a wide variety of applications for this technology to help UAVs do things like forest fire detection, police surveillance, border patrol, and weather monitoring.
If the aircraft was damaged, you don't have to necessarily just rely on the pilot to compensate and fly the airplane. Adaptive flight controls, autonomous flight controls, different things where we're using the airplane to assist the pilot.
It'll take over basically the controls of the airplane as far as flight stability.
The platform precision autopilot is capable of staying on a given path within about 15 feet. It allows the synthetic aperture radar system to fly over essentially the same path more than once. This obviously has some potential applicability when you're looking at Earth's surface movements, such as after an earthquake, or if you're looking at an ice pack melting.
For the F-16, we went out and tested the system and based them on actual mishap cases. It prevented every single mishap. What we're developing here is merely an aid should the pilot get distracted or disoriented. By automating it, we can take out the pilot reaction time entirely.
The computer takes full control away from the pilot for a very brief period of time, and it redirects the trajectory of the aircraft to save the human.
ADS-B is automatic dependent surveillance broadcast. It's equipment on board an airplane that transmits its position and velocity information twice per second.
We were really trying to prove that we could use ADS-B as a way to do coordinated flight between multiple vehicles.
This system is present on a lot of manned aircraft, but we were one of the first UAS to perform testing of it in the national airspace. NASA has a project for integrating UAS.
So one day, UAS could hopefully fly with other commercial airlines and everybody will fly together safely.
There's various benefits to integrating unmanned aircraft, being able to monitor specific weather systems, monitor fires, delivering packages to your doorstep.
Operations to deliver medical emergency supplies, infrastructure, surveillance, and monitoring.
The technical side is a big challenge, but being able to integrate them safely is maybe even a bigger challenge.
To have thousands of these vehicles flying at the same time, you're going to have a lot more automation on the vehicle and in the airspace system.
Regulations for operations of the vehicle, regulations for airspace, regulations for infrastructure.
These aircraft are going to be highly autonomous, piloted, optionally piloted, unpiloted vehicle.
It's not just looking at the UAM, it's actually integrating the small UAS, the package delivery, or even the larger cargo delivery.
Subscale aircraft, we use those for a variety of reasons, to test things like new technology, which could be hardware or software, or even a completely new vehicle. You can do almost anything you want without much risk. And you can realize those gains very quickly. We're researching some level of autonomy. The aircraft, in most cases, are capable of taking off, flying around and landing without any human intervention. Things like ardupilots and multi-rotors and flying computers are allowing kids to play with research type tools that they never had access to before. So it's sort of driving in this new robotic learning type environment that never did exist.
I believe that this nation should commit itself to achieving the goal
before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
That's one small step for man, one giant leap for mankind.
Welcome to Introduction to the Moon. This is the first lecture in the Moon 101 series, and it's designed to give you a brief overview of a lot of different subjects about the moon that other lecturers will go into in more detail in the successive lectures. My name is Dean Epler. I'm a retired NASA lunar geologist, and I'm presenting this material, although it was originally put together by Paul Spudis, the scientist who originated the whole Moon 101 concept about 10 years ago. Paul has passed away, and I'm trying to fill in for him, hopefully in such a way that he will not be disappointed. So the first important part that we need to discuss is really what the moon is. And the real key, I think, is that the moon is a planet. It has many of the features that we think of as a planet, as in having a core, having a mantle, having a crust. No other planet is as proportionally large as the moon is with respect to the size of the Earth. Many of the other planetary bodies that have moons, such as Mars, have small irregular moons that seem to be just sort of, accidentally captured into the orbit of their primary body. The moon has a heavily cratered surface. It is partially flooded by lava flows, which erupted somewhere between 4 billion and about 1 billion years ago, with the bulk of the lava being emplaced around 4 to 2.2 billion years ago. Since the moon has formed, there have been many impacts by comets and asteroids, and they have radically altered the outer surface of the moon. It has created what is a chaotic upper layer of debris, which we call regolith, and it has deeply fractured the lunar crust to a depth of over 10 kilometers. By and large, the moon was a dead planet by about 1 billion years ago. There's a lot we don't know about the history of the moon, and some of these unknown items are key to understanding the history of the Earth-Moon system. The moon is covered by a particulate blanket. And I say particulate blanket because it is really a mix of particle sizes all the way from extremely tiny sizes all the way up to boulders that are the size of a building. It is easily accessed. It is a likely feedstock for resource extraction. And if you look at the picture of John Young's feet, this picture was taken on Apollo 16, you'll see that there is actually dirt, fluffy dirt regolith kicked up around it, and it gives you a nature of how loose and fluffy the upper layer of the regolith is. But in the upper right corner, you see the picture of an extremely small, but nevertheless almost perfect crystal of a mineral. The moon's regolith is full of things like this. And as I said, it goes all the way from large rocks down to the finest fraction that you can imagine. I want to go into some general properties. On the left is the moon, in the center is Mars in red, and on the right is Earth in blue. And if you compare the numbers for any given variable across the graph, you're going to see that the moon and Mars are actually a lot more like each other than Mars is like the Earth. A lot of people have taken the view that Mars is more like the Earth, and to a certain extent, that's justified in light of what we think the early Martian history is now, in that we think it was warm and it was wet. But the size of the planet, its composition, its very nature makes it actually a lot more like the moon than it is like Earth. The moon has a history. Before Apollo, it was dubbed the Rosetta Stone of the planets. And after Apollo, in the immediate years after Apollo, a lot of people sort of wondered, well, was it really? But as time has gone on, and as we've analyzed lunar samples, we've come to believe that moniker, in fact, is absolutely correct. And much of what we understand now about the other planets in the solar system, as well as the Earth, we've learned because the moon has preserved a history that many other planets no longer have. Now, before we went to the moon on Apollo with human beings, we had quite a bit of precursor missions from the United States. In addition to that, the Soviet program landed a considerable number of spacecraft on the surface, as well as flew vehicles around it. Before we could even think about landing on the moon, we had to understand what the moon was actually like on its surface. And it's really important to recognize that before these vehicles went to the moon, the smallest thing we had ever seen on the lunar surface through terrestrial telescopes was about 1 kilometer on a side. And the questions we had before we sent these spacecraft there seem somewhat silly now, but there were things like, where do craters run out? Are the craters all the way down to the smallest size? Are there rocks on the surface? Is the surface capable of bearing the weight of a lunar module? All of these things now we understand, perfectly well. But before we went to the moon with people on Apollo, we didn't know any of that. And this set of robotic missions clarified that. And I'm going to talk about each one in turn. The first successful spacecraft that basically touched the moon was the Ranger series. The Ranger series were hard landers in that they had no other, I suppose you could say, objectives other than hitting the surface and imaging the surface all the way down. As such, the only thing they did was photograph the surface. But this was really key because prior to the Ranger set of missions, we simply had no idea what the surface was like at a human scale. Ranger answered a tremendous number of questions that, frankly, we had had since Galileo first turned his telescope to the moon. There was a whole variety of soft landers, which, for obvious reasons, did a lot more when they got to the surface than the Ranger did. The Surveyor was an American mission. It flew 7 total spacecraft in the series, of which I believe 4 were successful. The whole purpose of the Surveyor missions was to safely soft land on the moon, to understand the nature of the lunar surface, and to do some basic chemical analysis. But largely it was, and you can think of it as largely a civil engineering mission. What we wanted to know is, A, can we land on the moon? Is it possible to have a spacecraft, fly to the lunar surface and survive? The second thing is, what is the surface like? Is it soft? Is it a hard rock? What is it like? Is it like a snowbank that we'll disappear into? And the Surveyor was an incredibly successful set of missions that we're still analyzing data from. The Soviets, in addition, flew 3 sample return missions to the moon in the 70s. The Luna 16, 20, and 24 missions not only brought back samples from places we did not go on Apollo, they did it robotically. And at this point, no other country on the Earth has robotically recovered a sample from the lunar surface. In addition, the Soviets landed 2 Lunokhod rovers, which were incredibly successful. They drove around the moon's surface, again in places that the Apollo missions hadn't gone. And the 2 sets of Soviet missions greatly enhanced what we understood from Apollo by simply providing complementary samples from other places on the moon the Apollo program did not get to. Lastly, Lunar Orbiter was another really key mission because it circled the moon and photographed about 75% of the surface. Up to the point of the Lunar Orbiter missions, the only real global view of the moon that we had was from telescopic observations, and telescopic observations that simply do not see the lunar far side. Lunar Orbiter was a mapping mission. It was intended to collect global mapping data that the Apollo program could use in planning landings. Now recently, and I say recently within the last 10 years or so, we have been flying, not just we, the United States, but the human race has been flying a significant number of orbital missions around the moon. Countries that had never done this before, like China, Japan, India, have flown a number of really successful missions and again have enhanced our understanding of the moon's surface. In addition to that, the Chinese have landed a soft lander with a rover in a manner not not dissimilar from the Lunicod missions. Okay, the first mission I want to take a look at is Selene. This was flown by the Japanese Space Agency. It carried a variety of instruments on board with three general objectives. First was to photograph the surface. Before the Selene mission went, we did not have any better resolution of the surface than we had on Apollo. The Selene mission improved that considerably. In addition to that, it carried geochemical remote sensors, basically instruments that could look down at the surface and capture radiation that would tell us what the composition of the lunar surface was. And in addition to that, it carried instruments to look at the nature of the space at the orbital altitude of the spacecraft. Chang'e 1 was a Chinese instrument and carried much or similar payloads and had similar goals to the Kaguya Selene mission. And it was doing essentially two big missions. One was to look at the lunar surface and to get good images and good altimetry. And the second was to collect remote sensing data on the composition of the surface as well. Chang'e 2 was similar to Chang'e 1, but it was primarily directed toward looking at the landing site for the Chang'e lander. So it was essentially a reconnaissance mission for a very specific spot on the lunar surface. Once it completed its mission, it left lunar orbit and went to the Earth Lagrange point 2, and then went from there on an asteroid expedition. So it was an extremely capable spacecraft, and it is still flying. Chandrayaan was a mission that was flown by the Indian Space Agency, but included payloads not only from the Indian Space Agency, but from the United Kingdom, from ESA, and from the United States as well. Again, collecting more and more detailed information about the lunar surface, similar in a way to the other satellites. Now, the first one that I think is really critical from the United States is something called GRAIL, Gravity Recovery and Interior Laboratory Mission. GRAIL was a spacecraft, or actually a pair of spacecraft, whose mission was to map out the lunar gravity field in incredible detail. And the idea behind this spacecraft was that the two co-orbiting spacecraft could determine the difference between themselves to an accuracy of about 1 micron, or 1,000th of a meter. As that distance between the two spacecraft changed, that indicated that there was a change in the gravity field felt at orbit. And that in turn allowed us to do an incredibly detailed gravity map of the moon. Once it got its primary mission done at a particularly high altitude, they stepped the orbit down and got increasingly detailed data at lower and lower altitudes until, in fact, the spacecraft ran into the surface. Because the moon's gravity field is unusual, it's lumpy, we tend not to fly spacecraft close to the moon early on in a mission because it's very easy to have the spacecraft impact. So many spacecraft will be flown at a higher altitude initially and then flown lower once we have a good data set. Another specific mission flown by the United States was a spacecraft called LADEE. Several times in the course of the Apollo program, we thought we may have seen particulate materials high in lunar orbit, and that remained a mystery as to what actually the high altitude environment was, particularly with respect to lunar dust. And the LADEE mission was flown to essentially look for lunar dust and to understand the nature of that high altitude environment. Lastly, and perhaps the most successful of all the missions, is the Lunar Reconnaissance Orbiter. Lunar Reconnaissance Orbiter was flown initially in the Constellation program, and essentially what it was doing was collecting all the data we felt we needed to plug holes in both the lunar map and our concept of global variations in things like topography and composition. LRO was originally planned to be a 1 to 2 mission. It is still in orbit. It's been there for 8 years, and it has returned some of the most phenomenally accurate and detailed photographs of the lunar surface that have ever been recovered. And they have changed many of the ways we think about the lunar surface. The only lander that has been on the surface since Apollo is the Chinese U-2 lander, which was carried to the surface as part of the Chang'e 3 spacecraft. It landed in Mare Imbrium, about 40 kilometers southwest from a crater called Laplace F, and it operated for approximately 2 lunar days on the surface. It was really important because it deployed to an area we did not go on Apollo, and in addition to that, it deployed instruments that we simply didn't even have during Apollo, such as a ground-penetrating radar. And it has returned data that is revolutionary, and it was a magnificent mission. So I want to talk about some gross properties of the moon. And it's always important to start with what the moon looks like, both from the Earth and that part which we mostly cannot see, and that's the lunar far side. The moon has presented a variable face to humankind. Specifically, it's got dark and light areas. And the variations in albedo, the reflected light, whether they're bright or dark, it turns out tell us some very important things about the moon that we now know because of the various spacecraft that have been there. This is a series of lunar globes that look at 3 different elements: thorium, titanium, and iron. And I want to look at these in great detail, but one of the things I need everybody to recognize from this is that the albedo, the change in the gray tone of the lunar surface, actually maps very nicely to composition. This is the iron map of a goodly portion of the moon, and the variations range from brighter, warmer colors as higher iron and cooler, darker colors as less iron. Now, if you look at the moon in plain light, like we see the moon when we look up at it, you can see that the higher, brighter colors on the iron map correspond to the darker areas on the moon. And that's because the darker areas on the moon are filled with lava flows, and lavas are basaltic in composition, the same kind of rocks you see in Hawaii, and they tend to be higher in iron than the lighter color rocks on the rest of the moon. So we can see from that composition reflects albedo. Now, if we look at the titanium map, we see something very similar, although there are some variations in this. Not all basalts are alike. Some basalts have higher titanium, some basalts have lower titanium. The color scheme is the same as the iron map. Brighter colors have higher, lower colors have lower titanium. And you can see that not all the dark areas of the moon, the lavas, have the same titanium composition. We essentially discovered that from Apollo, from return samples, and we were lucky before we even knew this that we picked sites that coincidentally turned out to be places that had variations in titanium. But again, you can see on the western side of the moon and on sort of the central eastern side, we have a lot of titanium. In much of the rest of the moon, we don't have much titanium. Lastly, if we look at thorium, we see, again, the darker areas of the moon having a lot of thorium, and thorium is a radioactive element, and it's indicative of sort of evolved magmas that have spent a lot more time cooking, and that will be discussed in a later lecture. But again, if you go back to the picture of the moon that we see from the Earth, you can see that the concentrations of thorium match many of the colors that we also see on the lunar surface. In this case, they map to some place that we call the Procellarum creep terrain, where creep, K-R-E-P, stands for potassium, rare earth elements, and phosphorus. Let's talk about the lunar surface environment, and there's really 4 parameters that I think are really important. One is temperature and sunlight. The 2 are paired, and the other 2 are hydrogen content and what you can see of the Earth and how easy it is to communicate. The temperature on the moon really divides the moon into 2 different regimes. One is polar, which are colder just like the Earth, and the other is the nonpolar environments, where depending on where the sun is, it'd be hot or cold, just like the Earth. At noon, we get the hottest temperatures. On the moon, at noon, we get the hottest temperatures. When the sun goes down on most of the moon, it gets quite cold at night. The poles, on the other hand, are colder, but the temperature is much more stable than it is on the rest of the moon. Let's talk a little bit about hydrogen content. Hydrogen is a really critical element for essentially living off the moon. You can combine it with oxygen to make water. You can use it as rocket fuel. So where the hydrogen is really important. The nonpolar portions of the moon, the hydrogen ranges from as low as 10 parts per million to as many as 90 parts per million. The poles, however, we're pretty sure that the hydrogen content on average is greater than 150 parts per million, and it's why the poles remain an attractive target for lunar settlement. Lastly, direct-to-Earth communications. The moon is in locked rotation with the Earth, and that means that basically wherever you are in the lunar near side, the Earth will be in sight and it'll always stay in the same place. At the poles, the Earth is really low to the horizon. If the terrain isn't in the way, you can see it all the time, much as you do from the front side. But there are many times when the terrain may block it. The lunar far side never sees the Earth. So if you're going to operate on the lunar far side and you want to talk to the Earth, you're going to need a continuous relay satellite. So let's talk in more detail about thermal conditions, because the temperature is what we're going to have to work in when we're on the lunar surface. Nighttime surfaces are very cold, down to as cold as 150 degrees centigrade. And noontime temperatures are equally high, about 100 degrees centigrade. Polar areas are either always dark or have grazing solar incidence. So there are areas that we refer to as the permanently shadowed areas. These areas are extremely cold. In fact, many people have estimated that these are the coldest places in the solar system. The permanently shadowed areas on the moon never see the sun and probably have not seen the sun for hundreds of millions of years. Consequently, they are extremely cold, down to 50 to 70 degrees Kelvin. Another critical part of the lunar environment is micrometeorites. First, there's no atmosphere to impede the impact of all debris, so the speed at which, or the velocity at which it's coming in from space around the moon is not attenuated at all as it is on the Earth. There's a variable flux. I'm not going to repeat all the numbers on the graph there, but basically the smaller the object, the more there are of them. A lot of surface rocks have craters that are on the order of 1 to 10 microns. That's the size of the crater. In many cases, the damage from the impact extends far away from that actual crater, and it creates something we call zap pits. The Apollo astronauts noticed zap pits on the surface rocks, and once the rocks were back, it turns out that it becomes a very useful piece of data as to how long a rock's been sitting on the lunar surface and whether it's been tumbled. In other words, does it have the same face always facing the sky, or has it been rolled around? If it hasn't been tumbled, the top surface will have a lot of zap pits, the undersurface won't. If it's been tumbled around, the undersurface will have zap pits. And it turned out we could actually determine how rocks were bouncing around on the lunar surface by looking at the zap pits. One critical part of the discussion of micrometeorites is that even though there's micrometeorites coming into the moon and they're not slowed down, the impact hazard on the lunar surface is estimated to be about 4 times less than low Earth orbit where International Space Station is. Now, the moon's orbit is pretty interesting. Like all bodies in the solar system, it's not in a circular orbit, it's in an elliptical orbit. And in this case, the perigee and apogee being the farthest it's away from the Earth and the perigee being the closest it is, vary by about 45,000 kilometers. One key part of the fact that the moon has an apogee and perigee is that the size of the moon is actually quite a bit different when it's as far away as it can get and as close as it can get. The one on the left is when the moon is as far away as it is from the Earth. The one on the right is its closest approach. And there is a considerable difference in the moon's size. So when you step out at night and look at a full moon and you think, gosh, that's a lot larger than I remember it being, sometime in the past, it's not an optical illusion. That's actually happening, and it's because the moon is in an elliptical orbit. There's something we call the barycenter, and that is the center, the point at which the entire system rotates, and that's about 1,700 kilometers below the Earth's surface. It is not at the center of the Earth because the moon is actually quite heavy relative to the Earth, so that center of rotation is actually displaced from the center of the Earth. The moon has an orbital period of about a month. We know this because every month we go through a new moon and we go through a full moon and then back to a new moon. It is not exactly a month long, so there are months that come along where you get 2 full moons in the month, and that's why. Okay, let's talk a little bit about the moon's orbit and eclipses. They could be more common if all of the orbital parameters of the Earth and moon lined up. Basically, what happens to get an eclipse is that at the point of new moon, in other words, when the moon is located between the Earth and the sun, it's directly on what we call the Earth-Sun line. That is the line that's drawn essentially between the center of the Earth and the center of the moon. Because the moon's orbital plane is different from the Earth, and because that plane precesses around the Earth because of tidal and gravitational forces, those 3 conditions, Earth-Sun line and the moon right in that Earth-Sun line, don't happen very often. And so it's a special case of a new moon. If all of those were aligned every month, we'd have an eclipse, but we're not so lucky. Let's talk a little bit about something we call libration. The moon wobbles around its axis, and it actually has what we call longitudinal and latitudinal axis. Longitudinal libration means it's basically wobbling back and forth on its elliptical plane. Latitudinal means it's wobbling back and forth on its essentially north-south line. Because of that, we can actually see slightly into the far side and the poles of the moon if we didn't have libration. So about 8 degrees beyond the 90-degree west and 90-degree east points, and about 6.5 degrees beyond the north and south polar. If you look at these 2 photographs that were taken at different parts in the year, on the left photograph, there's the crater Endymion pointed out, and you can't quite see it, but Mare Crisium is the black crater essentially at the center. If you look at the picture on the right, Endymion has now shifted to the left and more into view, and Mare Humboldtium, which normally we would not see, we can see. Likewise, Mare Crisium is no longer right on the limb, but is slightly tilted toward the Earth, and that's just libration at work. Topography is an important thing that geologists think about in terms of a planet's history and its conditions, because it tells us a lot about how strong the crust is and what's happening on the interior. We now have a really, really good idea of what the topography of the moon is like. The moon is bumpy. It has extremes in elevation from as low as 9 kilometers below an established altitude and as high as 8 kilometers above that. Now, we have pictures like this, and we use blue, cooler colors as the lower, and yellow, red, and white as the higher altitudes. But one of the things that's really key is that the moon has elevations extremes that are essentially the same as the Earth, from the seafloor to the mountains. There's a couple of things that I think are important to talk about. One is, of course, the lunar near side has the traditional thing we think of as the man in the moon patches of dark, but it turns out, of course, these are also where the moon is low, and that's consistent. Lava flows, when they erupt, flow into lower spots, and we know now that those lower spots are the remnants of very large impact craters from the early on in the lunar history. The lighter areas are what we call the highlands, in between the lower spots, and they're much elevated. Interestingly, if you look at the far side, on the lower part of the far side, we see this big dark blue area, and that's something called the South Pole Lake and Basin. That's generally acknowledged to be the largest impact crater in the solar system, and it's actually a pretty big hole on the moon, and we really didn't understand that it was there, although there were hints, until we had these kinds of maps more recently. In addition to the South Pole Lake and Basin, you can see at the equatorial part of the far side of the moon, we have our highest topography, again up to about 8 kilometers above the agreed on datum. The topography of the moon is largely bimodal. In other words, you're either on the rough lighter colored highland areas or the smooth, darker colored maria. When we consider roughness, we're really talking in most cases about whether it's mountainous or not mountainous, and those are big scale things in terms of the terrain. But it's also important to consider whether we have roughness at a human scale, or in the case of going back to the moon, on a lander scale. And the highland areas turn out to be actually smoother at a lander scale, and the maria are rougher at the lander scale. Lunar landforms are dominated by cratering. We talk a little bit about lava flows, but even the lava flows are affected by cratering because the lava flows are found filling craters. There are literally thousands of impact craters, ranging from the size of the South Pole Aitken Basin, which is 2,500 kilometers across, to the zap hits, which are microns across. The shape and form of an individual crater changes as a result of two things. One is the size. The larger craters tend to be flatter floored. The smaller ones tend to be more bowl-shaped. In addition to that, as a crater spends time at the lunar surface, in other words, it goes from being a young crater to an older crater, it gets more and more subdued till finally it's just barely there. Unlike the Earth, the terrain on the moon is not dominated by plate tectonics process. It is solely a function of where things have impacted and the volcanic events that have filled those areas. In any event, completely smooth, flat areas on the moon are rare. They occur in the maria, but the maria are fairly old, so they have been broken by numerous craters as well. The slopes in the maria are around 4 to 5 degrees on average, so it's not very steep terrain, although as you can see the crater in the center of this picture, if you get close to a young crater, the terrain gets quite a bit steeper. The highland maria boundary is generally sharp and abrupt, much as we see here at the Apollo 15 site in the Hadley Apennine region. Because of that abruptness of the boundaries is again why we see the dark maria areas. If those boundaries were not abrupt, the maria would not have that sharp, obvious image on the moon surface. The highland terrain consists largely of rolling hills, some of them quite high, but nevertheless not jagged, steep cliff faces like we see on terrestrial topographies. The highland terrains are created largely by overlapping ejecta blankets from large craters. If we get close to a young crater, for instance like Tycho, the terrain is quite rough, but away from the young impact craters, the average slopes are 7 to 10 degrees, but the scale of the topography at, let's say, a lander image or a lander footprint is quite smooth. Surface lighting is something that not only we dealt with on Apollo, both in terms of operating on the lunar surface, but also seeing the topography for crews to land at, but also we'll be worried about it when we go back to the moon because we're there to stay. Apollo 12 had the shallowest sun angles, so 7.5 to 9.5 degrees, very shallow. Apollo 16 had the highest sun angles, 45 to 48 degrees. On the left is an Apollo 12 picture on EVA-1. You can see how long the shadow of the lunar module and the astronaut is. On the right is the Apollo 16 site at the highest sun angle. And in contrast, the surface is much brighter, the shadows are smaller, and in general, it's harder to see your way around on the terrain in high sun angles than it is in lower sun angles. Anybody that's ever been skiing in flat light knows that you can ski off some remarkable terrain that you didn't even see because the shadows aren't there. In some ways, driving around on the moon in high sun angles is going to be similar to that, and possibly when you drive, you're going to have to be tacking back and forth down sun. These are two pictures essentially looking up sun and down sun. Apollo 12 EVA-1 down sun, the sun is 7.5 degrees, so you can see if you're looking directly down sun, you don't see much, but if you look to the right or to the left, you can see quite a bit, and that's what I mean about having to tack back and forth around the sun. If you want to make sure you don't drive into something that's exciting, you're going to have to be careful how you drive. In contrast, Apollo 17 EVA, sun's about 16 degrees, and that's looking up sun. The terrain is somewhat easier to see, but it's still glaring sunlight when you're going directly into the sun. A unique aspect of working on the lunar near side in the dark is illumination by Earthshine. Because the moon's orbit is locked and we always see the same face of the moon, the Earth always stays in the same spot in the sky. And when you have a full Earth, it's something like 80 times brighter than a full moon. At essentially lunar midnight, if you're out working under the Earth with a full Earth, it's as bright as about 8 o'clock on a summer evening on the Earth. So the reality is that when you're out at night in Earthshine, you'll be able to see just about everything you need to without artificial illumination. John Young once told me that not only was it bright enough to see the lunar surface from orbit with Earthshine, you could actually tell color differences and see individual craters with Earthshine. So Earthshine is going to be an asset that's really important for future lunar operations, unless, of course, you're on the far side. The far side, the Earth is never in view. So when the sun goes down on the far side, with the exception of starlight, it's going to be really dark. In addition to that, when we're working at the poles, because the sun is so low to the horizon and the Earthshine is so low to the horizon, you're almost always going to need some level of illumination so you just don't step into dark holes because of the low sun angle. Let's talk about Regolith. Regolith is one of those aspects of the lunar surface that has received a lot of discussion over the years. There will be a further lecture just on Regolith, but I want to touch on it here to give you an idea of what it is. The basic definition of regolith, and this is a geologic definition, is the layer or mantle of loose, unconsolidated rock material of varied origin that rests on bedrock over most of the lunar surface. In other words, regolith is what happens if you take bedrock and just beat it up until it's just nothing but fragmental material. We use regolith on the Earth to talk about soils as well, but the moon is essentially just plain old rock. The regolith can be formed in place or it can be transported from adjacent locations. Generally speaking, if you pick up a handful of regolith at any one spot on the lunar surface, roughly 90% of the material in your hand is going to have been derived very locally. About 10% will have been transported in by meteorite impacts from other locations. There are a lot of processes that affect regolith formation. Obviously, the principal one that creates regolith is meteorite impact. It breaks up the bedrock into all sizes, and the variety and sizes of meteorites create variety and sizes of regolith. In addition to that, we have cosmic rays, we have solar wind, and those create variations in the regolith which have caused it to be quite different at a very, very small scale, and I'll leave that discussion to the subsequent lecture. The median particle size of regolith is about 40 to 130 microns. That's really small, and it's much smaller than we experience, for instance, when we're at the beach. 95% of the regolith is less than 1 millimeter, and if you're out the beach, the roughly average size of the sand is about 2 millimeters. So the moon is not going to be like a day at the beach. There are a lot of things in the regolith. There's a lot of things mixed up. It's ground broken rock, it's impact melt, it's bits and pieces of meteorites, so it's very variable. The graph shows the variation in the nature of the regolith at various landing sites, in this case, surveyor landing sites. And you don't need to take away real detailed specifics on this, but it's important to recognize that the regolith isn't the same all around the moon. As the surface gets older, in other words, it's been exposed to the lunar, at the lunar surface for a longer period of time, it changes grain size, it changes character. So every landing site will be slightly different. When we landed the lunar modules on the regolith, we had a variety of essentially interactions between the regolith and the lunar module. First thing, of course, is everybody knows that down close to the surface, the astronauts saw dust moving around. And if you look at the upper left picture and the lower left picture, those are sort of striations, little ridges and troughs created in the regolith by the ejecta, by the exhaust from the lunar module. If you look at the upper right picture, you can see that in that case, the regolith was quite fluffy and the foot pad sank, probably 1 to 2 centimeters into the regolith. On the lower right picture, you can see that, in fact, the foot pad is just sitting on the regolith. So how compact and how fluffy the regolith varies from place to place. But none of it, in no place, is that fluffiness deeper than about 10 centimeters. There's been a lot of discussion about dust and what it does to astronauts and hardware and rovers and spacesuits and things like that. The picture is of Gene Cernan after EVA-3 on Apollo 17. He's just pulled his suit off, and you can see that he's got a lot of dirt on his face, not because the regolith came into the suit during his EVA, but because the suits, which you can see piled on the ascent engine cover in the background, were pretty dirty from walking around on the lunar surface. There's been a lot of discussion about levitated dust. There's been a lot of discussion about whether dust is a critical design issue that will cause failure if it's not followed or not paid attention to. Levitated dust has been suggested both by the horizon glow taken on the surveyor cameras and by photographs and notes made by Gene Cernan as the Apollo 17 command module approached the Terminator. There's been a lot of discussion, is dust levitated? Does it move around on the lunar surface? There's a couple of things we can look at to try and get some idea of whether there is a large-scale transport of dust on the surface. The first is that Apollo 11, 14, and 15, we put laser retroreflectors on the surface. Now, these were corner cube reflectors that were designed to reflect laser light back to the Earth. So if there's dust moving around, you would really expect those corner cubes to get covered. And even if they're not completely covered, you would expect to see some reduction in the signal strength coming from the moon over time. The Apollo 11 retroreflector has been on the moon now for over 48 years. The others somewhat less time. There has been no evidence of any degradation in laser signal over the lifetime of these arrays. So if there's dust moving around, it's not covering the retroreflectors. When we went to the moon on Apollo 12, we landed near the Surveyor 3, which had spent 31 months on the lunar surface prior to the arrival of the Apollo 12 crew. Although there was some dust coating on parts, the patterns on the coating indicated that the dust was blown onto the Surveyor either by the lunar module landing or by the engines of the Surveyor itself. Again, there was no evidence of dust having settled on the spacecraft from any other source other than the engine exhaust. In fact, there was even a study published where a research team looked at the Surveyor parts brought back to the Earth, and they saw no evidence that dust was on these parts except by blown on by the engine bells. Now, when we establish an outpost, because engine bells do blow dust around, we're going to have to be careful about where we land our spacecraft so that we don't spray dust all over our habitats, deployed equipment, and instruments on the surface. So in that case, we will have to accommodate the fact that if you have an engine coming past the surface, it's going to blow dirt around. There's been some discussion also about whether dust is moving in the Terminator. When the Terminator comes by, there's some suggestion that there are variations in the electrical current, which some people have suggested would cause dust to levitate. So I want to talk a little bit about that particular issue as well. And this concern was raised before Apollo, and Apollo, I think, provides us some pretty conclusive proof that it's not happening. The first, I think, that's really important is that the albedo gradients between the highlands and the mare, the highland rocks being lighter colored, the mare rocks being darker colored, are sharp and distinct. They're preserved at remote sensing scales, they're preserved at photographic scales, and the crews on the surface could see them. In the upper right, the right is a picture of the Apollo 17 site. You can see very clearly that the highland terrains are distinct from the Mare fill in the valley. At the left, you have a geologic map from a publication in 2002 that shows by using remote sensing data that those albedo variations indeed represent compositional variations, and that there is no sense that there's a homogenization of the lunar surface from dust. Likewise, if you go up to orbital altitudes and look at things like the Mare highland boundaries, in this case Mare Crisium, on the left you see the albedo picture, on the right you see the iron map, and again, you can see clearly that iron does not bleed over into the highland terrain, that the boundaries, the albedo boundaries, are as sharp in the remote sensing data as they are in the visible light. LADEE was a spacecraft I talked a little about earlier as having been sent to the moon recently to look at whether there was a dust component in the high altitude lunar exosphere. And in fact, LADEE saw, while there was some tenuous dust, there was no evidence of electrostatically lost dust at high altitudes. Lastly, if a lot of dust was moving around, we would expect the rocks at the surface to be either covered in dust or at least have a mantle of dust. And there is no evidence on rocks that have been essentially exposed to the surface for hundreds of millions of years of any accumulated dust blanket. We conclude that lateral dust transport on the moon, if it happens at all, is very inefficient and is not coating the lunar surface with new dust every time the sunrise goes by. Let's talk briefly about the origin of the moon. We'll get into more detail in subsequent lectures, but there were three traditional modes that were advanced prior to Apollo. Some of these modes date back to literally Charles Darwin's grandfather. The first was what we call the fission model. The idea was that early on in the history of the Earth, when it was largely molten, and if it was rotating fast, mass dissimilarities would cause a bulge to be created, and you would essentially birth a moon from that mass distinction. Darwin's grandfather actually suggested that the Pacific Ocean was where that body came from. The second origin theory was that both the Earth and the Moon essentially accreted in the same spot, but created two different bodies, what we call co-accretion. And lastly, we thought that potentially the Moon was formed elsewhere in the solar system and was ultimately captured by the Earth when the Moon in a different orbit came nearby. We know for sure that the moons of Mars, for instance, were captured in such a way that they're actually asteroids which were forced out of the asteroid belt and were captured by Mars and are now permanent satellites. So one of the outcomes of the Apollo program was we discovered that these models are, for the most part, wrong. And we did that on the basis of understanding that the Moon had undergone a fairly violent early history, and by inference the Earth, and also by looking at similarities and differences between lunar samples and terrestrial rocks. After quite a few years, and I mean like a decade, more than a decade after Apollo, that length of time was necessary to really assimilate all the data and start to come up with new models of the formation of the Moon. And what is now called the giant impact hypothesis is the reigning model for the creation of the Moon. What we believe now is that very early in the solar system's history, in some cases no more than 10 to 15 million years after the formation of the solar system, a Mars-sized body impacted the early Earth. And it didn't have a straight-on impact, it had a glancing impact. That the energy of that impact destroyed the impactor, the Mars-sized body, and significantly disrupted the surface of the Earth such that you created basically a ring around the Earth, created entirely of the impactor plus some of the Earth's crust. Over a relatively short period of time, they think on the order of less than 1 million years, that ring system coalesced to form the moon that we know now, and it has been evolving ever since. It's important to point out that before Apollo, we thought the moon was essentially a big dust ball. Very little in the way of history, very little in the way of internal processes, and at some level, a fairly boring object. But we now know that shortly after the moon was formed, the upper several hundred kilometers of the moon were melted, probably by a combination of impacts and the dynamic environment the moon was in at the time, and it created what has come to be known as the magma ocean. So if you can imagine an ocean, but not of water, of molten rock, you get an idea of what the early history of the moon was like. Shortly after that crust stabilized, we think around 3.9 to 4.2 billion years ago, the last remnants of large planetesimals, big rocks floating around the solar system that hadn't yet been swept into planets, impacted the moon. And these impactors created the big basins that we see now. Shortly after that, we had a massive eruption of basaltic lava. Those rocks are darker and heavier than the lighter anorthosites, and they filled in the large impact basins and largely gave us the picture of the moon that we see today. Since about 2.5 billion years ago, we think the moon has been largely quiescent, not much going on, except for an occasional impact. The smaller the rock hitting it, the more them there are. Occasionally there are big smacks like Tycho, but that's been the history of the moon ever since the end of the big period of volcanism around 1 to 2.5 billion years ago. And the real key thing about the moon, I think, is that it really has witnessed a lot of the history of the inner solar system and specifically the Earth-Moon system in a way that we can no longer see on the Earth. And consequently, it's not only an important scientific target, but it's a place where we'll learn how to live on planets other than the Earth as we move out into the solar system.
Yeah, you want to torque it though?
Oh, you got it tight.
The goal of the El Niño Rapid Response Experiment is to look at how changes in the weather patterns, the evaporation of moisture in the tropics, how that has changed during a major El Niño event like the current one out there, and then to look at how those changes further impact the weather on the west coast of the United States. My name is Gary Wick. I'm a physicist with the NOAA Earth System Research Laboratory Physical Sciences Division in Boulder, and I'm on assignment to the Unmanned Aircraft Systems program within NOAA.
Boy, that was the easiest we ever did it.
During this campaign, we have 4 instruments on board the Global Hawk aircraft. The first is a dropson system, which it deploys these very small sensors, much like weather balloons that go up, but these go down. So these small sensors, they're about the size of a paper towel roll, and as they fall, they collect very high resolution, vertical resolution measurements of temperature, humidity, and wind speed. So they give us a very detailed picture of the atmosphere.
Yeah.
In addition to that, we have the HAMSR, which is a microwave sounding instrument, and that provides sampling much like one of the weather satellites that is used extensively in our weather models. The third instrument is HIRAP. It's a Doppler precipitation radar. So just like the weather radars on the ground, we're flying a radar on the aircraft which gives 3-dimensional coverage of precipitation, of rain droplets, and with information from those rain droplets, we can derive continuous measurements of the wind speed in the atmosphere. The final instrument is the NOAA ozone sensor, which provides measurements of ozone concentration at the flight level of the Global Hawk. The Global Hawk provides amazing capability for this experiment, just in its ability to be airborne for up to 24 hours or more. That by being aloft for that long, we can sample a large range of the ocean, almost like a satellite does. That with the Global Hawk, we get very detailed sampling like an aircraft, but with the endurance that a satellite would give us. So we're able to sample this large area and look at changes in the atmosphere that wouldn't be possible with other traditional manned aircraft.
My name is John Newhouse. I'm a Deputy Project Manager for the NASA Global Hawk program. I'm actually a commissioned officer with the NOAA Commission Corps. I've been flying the Global Hawk here at NASA for 4 years as an aircraft commander and instructor pilot. So as you can see here, the Global Hawk has no yoke or stick to fly with. We use a mouse from takeoff to landing, climb and descents when we're underway. Everything is automated in the Global Hawk. So all I need to do is do a mouse click here on the screen to say takeoff or to land, climb, descent, maintain an altitude. Everything is done by this mouse click. And it's very much like flying an autopilot in a manned airplane. And what NOAA is using this is as a study to use unmanned aerial vehicles over high-impact weather events such as hurricanes, and in this campaign we're actually using it over El Nino events in the Pacific. We're going to be working with Air Force C-130s, we're going to be working with NOAA Gulfstreams, and also a NOAA ship, the Ronald H. Brown. So we've got C-130s covering one part, G4 covering another part, the ship covering other stuff, and then we're going to be in the parts that are harder to reach.
We typically take off at first light so we can get to the area of interest to study El Nino weather per the science requests. This usually takes about maybe 8 hours to transit to the area that we're studying. And once we're there, we spend several hours analyzing all kinds of weather phenomena that has piqued the interest of the scientists. And it usually takes about 8 hours to bring the plane back home. So that gives us about a total flight time of 24 hours for each sortie. I'm Herman Posada, and I'm a UAS research pilot here at NASA Armstrong Flight Research Center, and I fly the Global Hawk for airborne science. While we're flying the aircraft, we're monitoring many screens. Mostly we're looking that we're on the right track that science has requested us to fly on. We are also obviously looking at various parameters of the aircraft, make sure we don't get any trouble with airspeed, altitude, or the heading. The flight plans continuously getting updated as science changes the area of interest. Obviously these storms are moving and we are trying to keep up with them.
Hey, mission pilot.
So in the Global Hawk Operations Center during a flight, we're going to be monitoring the flight with this wonderful mission tool suite capability that NASA has developed. And with that, it allows us to see the data coming in from the aircraft in real time, satellite data, and multiple things for us to really see what's happening as we go along. And so what we'll be watching for is, can we see the weather patterns? Can we see patterns in the humidity that let us know that we're sampling the areas that are eventually going to move downstream and impact the U.S.? The Global Hawk is a one-of-a-kind capability that, NOAA, we have a great observing system from satellites to aircraft to ships, but there's nothing that provides the capability of the Global Hawk. So within NOAA, we really want to see if that is a really good addition to our current observing system. And so by collaborating with NASA, we get this wonderful opportunity to test its capabilities, see its impact on the forecasts, and then hopefully that opens the door for a broader collaboration down the line to do this on a regular basis.
Copy, and release will be in any right turn away from you.
I'm Jessica Arriola, and I am the lead for public and digital engagement for the Quest mission. Me llamo Jessica Arriola y soy la líder de comunicaciones para los medios sociales y en persona. My role with the mission is to communicate using social media channels or in person at events. The Quest mission is seeking to change rules that essentially would enable commercial supersonic flights over land. So for me, that's really exciting because that means that I would get to go from Washington, D.C. to LA in half the time, so I could see my family maybe more often. I am a product of immigration. I was born and raised in Southern California, and because of that, I work on making sure that we have as many resources as we possibly can to also include the Spanish-speaking population. To be at, say, an event and be able to communicate to someone in Spanish, it's pretty rewarding to see someone light up and then just they're so appreciative. As a kid, I was pretty creative. I remember wanting to be an interior decorator or a fashion designer. I even thought I could maybe be a singer. Mind you, I can't sing. One of the milestones that I'm looking forward to with the Quest mission is first flight. Like, I cannot wait to see the X-59 in flight. I cannot wait to see it take off and see it in the air and really experience what it sounds like. So much of what we're talking about with the Quest mission is sound. So I can't wait to actually hear it or maybe not hear it.
My name is Matt Camlett. I'm the communications deputy for NASA's Quiet Supersonic mission. Our job as communicators is to provide a voice for NASA to communicate with the public, but also it's a two-way street. We provide a voice for the public to communicate with NASA. In a given week, we might be working on social media posts. We might also be working press conferences and delivering on-camera news about what NASA is doing and the status of our mission. We will be flying the X-59 over communities beginning in 2024. The public will be providing feedback to NASA based on their perception of the X-59 when it flies over their communities and the quieter sounds that it makes during supersonic flight. My start in communications really came from being a sports broadcaster at my junior college. From there, I went to doing play-by-play announcing for the Long Beach State Dirtbags baseball team. At CBS, I covered the Dodgers and the Lakers and the LA Kings, and got to learn from some of the giants in the industry, people like Vin Scully. Growing up in California, I've grown to love the outdoors and the beach and the ranches. That's what helps provide my balance with work. You can usually find me at the ranch with my horse, Vinny, an animal with that kind of personality. He's almost more my buddy than just my horse. To actually see this X-plane, this experimental aircraft coming together, it's striking knowing that you're looking at something that can change the future of flight for all of us forever. What's really, really cool about NASA's Quiet Supersonic mission is we're seeing a lot of different NASA centers across the country come together in one goal as one NASA. We're really excited about this mission. We believe in it down to our core, and it's also a heck of a lot of fun.
My name's Paul Deese. I'm in the propulsion group. I'm the deputy propulsion lead, and my main focus is the integration and test of the GE 414 engine into X-59. For the engine, in and of itself, X-59, wouldn't go anywhere without it. So for our job, it's making sure that all the air that's going into the engine is clean and gives the engine the air that it needs to produce thrust, and then shoot all those molecules out the back and push everything forward. One of our most precious resources as humans is time. And so this technology and this capability, I think will be able to give people more time at wherever they're wanting to go. And that's invaluable. There's very few things I can do in my job without teamwork. And everything that we're doing on X-59 is building towards one final, piece of hardware. Going through school, a lot of teachers encouraged me as an individual. I was heavily involved in music and theater. And as weird as it sounds, I almost think of flight test as a musical or an orchestra. Everyone has their piece to play, everyone has a position to be in. When we actually do rehearsals, we will do practices, we will do tests with the pilots, with the sims, to practice for the actual activities that we're doing. To boil it down as similarly as a high school theater production. Everybody practices their part, and when it comes to their time to shine, then they do their part. Integration and test, I really love it.
I'm Sarah Wechter. I am the Deputy Project Manager for Execution for the Low Boom Flight Demonstrator Project. So the goal is to prove that we can go supersonic without a large sonic boom. X-59 will fly over different communities across the country. The communities will have a chance to give feedback back to NASA on the sonic thump that they hear in their house, at the grocery store, or outside in their car. So I lead a very diverse team that does everything from cybersecurity to financial management. I grew up on the hills of Ohio, at the top of a hill with a farm full of pigs and chickens and fields rolling and family on every corner. So growing up on a farm, I learned a lot about contributing as part of a team. So everyone in our family had to help. No one got to stay inside and enjoy the cool weather. We all were outside working together as a team. And on the farm, we got to get a little bit of our hands dirty, so we all were able to contribute. And same with on our low boom project team. We all worked together. Every chart, every analysis has a whole team behind it that contributes to make that a success and make sure it makes sense across the whole project. Watching X-59 fly for the first time will be so rewarding, not just for what I contributed to the mission, but to know that team members have worked on the research for this mission for years, for decades, and to know that I was a small piece of it, but more so as a part of a team that made this idea many years ago actually happen and fly and be a success and make a change for the world. There's no better feeling. That's part of why I love working for NASA, is having that pride.
I'm Don Durston. I do sonic boom wind tunnel testing for the X-59. When we run these tests, we hope to measure a sonic thump instead of a loud sonic boom. I lead the group of researchers that are involved with the sonic boom wind tunnel testing, but I would never plan a test just on my own. To run a wind tunnel test, it takes not just the researchers who bring the model to the tunnel, but the whole tunnel operations crew. It's just such a big team effort. I feel like a small cog in this giant wheel of progress in doing wind tunnel testing. What got me into actually flying is that I just enjoyed the experience of being up in the third dimension, getting off the ground, being free to fly the airplane around wherever you want, see whatever you want from the air. I grew up in Southern California. I think from the first time I looked up in the sky and saw an airplane and realized that there was a person flying that, I said, I have to do that. I want to fly airplanes. For my 7th birthday, I told my dad, I don't care about any of the presents. I just want an airplane ride. I want to feel the controls of an airplane. So we did that. We went for a half-hour flight over Disneyland and back. As I was growing up, we heard lots of fighter airplanes pass overhead that were going supersonic, and I heard sonic booms from them. So I got very excited about that. And I wanted to study airplanes and learn how they fly. So I'm a 1/4 owner of a Cessna 182. We formed a small flying club, and it's just the 4 of us. I have taken my family up in my airplane a number of times. I took the younger son and his wife up to the wine country, to Napa, and their friends were so impressed that instead of driving there, they got to ride in a private airplane to get there. When I see the X-59 take to the skies for the first time, that is going to be a really exciting day for me. I can't wait for that day, and I'm not retiring until I see that.
I'm Stephen King, a 3D artist, and I get to make images for the X-59 Quest. My job really involves working with the engineers from the get-go and getting the data from them and getting 3D models so I can do my job in producing the images for them And usually what that is beautiful images, beautiful renders, and prevising this thing to make it fly, take off, and really showcasing the features of this aircraft. My favorite part of the X-59 is the long nose. It's something so unique to this aircraft that we really don't get to do anything like this with any other aircrafts that we get to touch. Part of the process of finding references for X-59 is looking through NASA's catalog of other X-planes and seeing what features we can take from those and apply it to X-59. We really get to showcase not only how long the plane is, but the XVS camera system that's being used. And the X-59 pilots, they're going to be flying this thing without a forward-facing window, which is really awesome because they're going to be looking at a computer screen that's showing them what would be there. And that's something out of sci-fi, if you ask me. In my free time, I really don't like to do anything related to the computer. I like to work with my hands, actually. So I do a lot of scale models and action figure repainting. That's skills that actually translate back over to the computer. I like to recharge by going hiking, biking, kayaking. That's really what gets me rejuvenated. If I'm not learning at work, I'm not really pushing myself, and that's important to me. I want to stay on my toes, and I want to be able to learn new things. We've been doing these images for years now, and to finally see it coming together is just so exciting, and I'm excited for first flight and to see all that hard work and see all the graphics, everything come together. It's going to be awesome. Yeah, I definitely have the coolest job in the world.
I'm Clayton Myers. I'm the Deputy Project Manager for the Commercial Supersonic Technology Project. My role on the project is to oversee work and preparations for the Quiet Supersonic mission. The project team is made up of people from NASA Ames, NASA Armstrong, NASA Langley, and NASA Glenn. The shaping is really the key to our technology, in that we create shock waves, a bunch of small ones that come down in parallel so they don't coalesce and create the big boom boom that you typically hear with the current military vehicles. To unwind, my wife and I like to walk up to Huntington Beach, which is not very far from where we live. The path we take is about a 3-mile walk, and we just enjoy stopping and looking at the waves over Lake Erie to see how they're doing on a given day. I grew up on a farm in Ohio. We had sheep sometimes we had pigs, sometimes we had ducks, we had a few geese. We had over 400 acres where the cattle were located. When you're raising cattle, it's like a long-range project. They just don't typically grow up quickly. The hard work, I think the perseverance helped. You know, you're going to start things, and you're going to tackle problems, and then you're going to go tackle the next set of problems. When I was growing up on the farm, I would occasionally take walks out in the field, and I would look up and see contrails that were left by the aircraft at high altitudes, and I'd be fascinated by them, and so that's what got me interested in aviation. The NASA Quiet Supersonic mission is the first of its kind. I've been at NASA for 38 years, and I haven't seen anything like this. I'm excited to come to work every day and interact with the people that are on the team. When the X-59 flies, it will be a very rewarding experience built upon decades of people's work coming to fruition, and I'm just very proud to be a part of it all. It's going to be a very exciting time.
My name is April Lynott, and I'm the STEM Integration Lead for NASA's Aeronautics Research Mission Directorate, and I live here in Colorado. So my job working with the LBFD team is to see what's going on, to learn more about what we're doing here at NASA, and then take that and figure out ways to bring it into the classroom. I spend a lot of time learning more about what's going on, taking a look at what's happening within the mission, and finding the best ways to connect all of those different elements and build something that students and teachers can use. My favorite part about being a teacher was always watching the excitement on their face when they discovered something or they saw something for real that they had just done. So they might have read about it, they might have seen it in a movie, but to actually experience it, build it, get something to work that they built with their own two hands is probably the best part about teaching. Kids love the X-59. The X-59 is such a unique looking aircraft. It looks futuristic. It's different than any other airplane that people have seen. When I'm not working for NASA, you'll typically find me out in my garden or you'll find me camping or fishing with my family, or you'll find me and my kids at the cat sanctuary where we volunteer. We did adopt one of the kittens, so we caved in, and we now have Milo, who's one of our little kittens in our house. Whether you want to be an engineer or a pilot or a scientist, that's one element, but we have such a huge need for all kinds of other people to become a part of our NASA family as well. Everyone has a place in STEM.
My name is Joe Dustling. I work as a data engineer at the 8-foot by 6-foot supersonic wind tunnel at NASA Glenn Research Center in Cleveland, Ohio. For the X-59, we've actually looked at the aerodynamics of the aircraft itself. We've looked at the distortion being ingested by the engine. We've looked at the stability and control aspects of it. And upcoming, we actually are looking at the sonic boom that will be coming off of the aircraft, where hopefully we'll be able to confirm the predictions of NASA researchers that the aircraft will actually be producing the sonic thump, not the sonic boom. Working in a supersonic wind tunnel, we're constantly installing different models, installing different test articles, and we have to be able to adapt and test on the fly. We work in a team environment, and so every single person has their own responsibilities, and therefore no 2 days are ever the same. I love to be outside. I spend a lot of my time working in a supersonic wind tunnel, and so anytime that I can be outside after work, I really enjoy it. I love hiking, kayaking, running. I'm a huge ultimate frisbee player. I play disc golf. Really just anything that I can do outside, I like to do. I am an award-winning homebrewer. It's been a hobby of mine for about 9 or 10 years now. I got into homebrewing by actually discussing this with some of my friends in grad school, and we were looking for a hobby that was an outlet, that was fun, that still required some engineering and science background to it. You get to create a consumable product, and it's just fun to create a good beer. The beer that I'm most proud of is actually my Roasted Jalapeno Pale Ale. It's won several medals and competitions around the state, and it's a fan favorite. It always means that the fall harvest has come, and it's just a great beer to enjoy on the back patio, enjoying the garden as well. I've always loved my job working as a data engineer at NASA, and having the opportunity to work on an X-plane is something that as a child I absolutely dreamed of, and to be able to work on it is just such a life achievement and so fulfilling that I never imagined I would actually be here at this point in my career. And this is something that I know I'm going to look back on and cherish throughout my entire career.
My name is Tegan French, and I'm one of the supporting meteorological engineers for the NASA Supersonic mission and X-59. Really, my job is the technical aspect of building the instrumentation, deploying it to the sites that they want, and just making sure the data is good. We do surface weather, setting up surface weather stations, and we launch balloons. When we're launching balloons for the project, they want us to launch it before every takeoff. That weather data is used to map out how the sonic boom will be concentrated to the people on the ground. As a kid, I've just always loved weather. I love clouds. I discovered that, looking up to the clouds was something that really helped make me feel better, and it gave me comfort. And as I got older, it developed into a deeper interest in science and weather. I'm someone who loves all weather, and I definitely love all the extremes. I think I just do appreciate all the different types of environments that weather creates and how it connects with the whole ecosystem. I really love to go hiking. I love being outdoors. I live in the Antelope Valley in the desert, and we are surrounded by mountains. So there's a lot of rock formations in this area. I love to climb the mountains. I take my dogs with me. We do game night. I also like to build roller coasters with my niece. So like miniature roller coasters where we put kinetic toys together and we build roller coasters together. I don't think I could do my job without my team. The collaboration between them, like when we put all of our brains together, we get the best solution that we could possibly get. I love my job. It's kind of a childhood dream.
I'm Walt Silva. I'm NASA's structures lead for the X-59 project. Hola, soy Walter Silva. Soy el jefe de NASA para estructuras para el proyecto X-59. The structure really is what obviously holds everything together, and it has to be 100% on the money. It has to be right. One of the challenges that we often encounter with this class of vehicles, because they're supersonic and you want to have a low boom signature, they are required to be very long and slender. It creates more flexibility than if it was short and stubby. And so because it's more flexible, the fuselage, and then you have a big weight of the engine right back here, is going to create a flexibility that we have to address. We have to account for that. What I really enjoy is when both NASA and Lockheed teams are together and we're looking at results. And then sometimes we come across a challenge or problem, we all try and come up with ideas on how to solve it. I was actually born in Colombia. When we were little, we moved to the US. And so my first exposure to an airplane was actually flying as a little kid. And that had a big impact on me. It's just the whole idea of flight, to me, has always been fascinating. To see large, heavy structures actually just float. To me, that just awakens my imagination and just really excites the child in me. And when I'm not at work, I'm flying RC airplanes, I'm flying drones, I'm enjoying music, all kinds of music genres. Austin is our 13-year-old golden retriever. He loves to play with the ball outside. He's 13. He chases the ball as best as he can. He's just a very gentle soul, a very, very sweet boy. I'm sensitive to folks who may not always be comfortable in a language, and even if I don't speak their language, I try to use sign language or anything to help them because I know what it's like. I was helped. There were people who helped me when I was little, so I was very appreciative of that, so I just like to pay that forward. The first time when I see that X-59 flying, vea, va a ser increíble. Va a ser un momento super especial. It's going to be fantastic, a moment filled with joy and pride.
My name's Kurt Long. I work on NASA's X-59. I'm an aerospace engineer. My main job is to help design, develop, and test the pilot's life support system, the oxygen that the pilot's going to breathe while we fly. I also help out a little bit with flight test planning and execution once the aircraft is built. So many people don't know in the ejection seat for the X-59, it has to sustain the pilot in the unlikely event that the pilot has to eject. If you eject at a high altitude, the pilot's going to fall for 5 or 6 minutes before they get down to an altitude where they can breathe. So we have to make sure there's enough emergency oxygen contained within the seat so the pilot can breathe the whole way down. I am a mentor and I do get to work with a lot of really talented students. I think a lot of students are drawn to X-59 because it does represent the future. And I think it's a lot of hands-on work. This is a real aircraft that's really going to exist. And the students, they see that, hey, I actually can have an absolute say in the development of a truly, truly game-changing bit of technology. When I'm not working, I do like to take vacations that sort of go a little bit more extreme. And in particular, I go on vacation to collect stories. I'm a big fan of life is all about collecting stories, going and trying things that are a little bit outside your comfort zone because it teaches you a little bit about yourself and makes you more confident to go do other things as well. I love a lot of outdoor activities. Most every one of them relates to either wind or water. I like flying gliders. I like sailing. I sail an awful lot. Aviation safety in general, both commercial and military, has improved tremendously, leaps and bounds in the 3 or more decades that I've been working in aviation. We have lowest accident rates today than have ever been in existence. With X-59, we plan on keeping those accident rates incredibly, incredibly low. Non-existent is what we're shooting for, and I think we're just about there. Here we are getting very close to X-59's first flight. I know myself and everybody else is going to be really excited that day when we see it actually, the wheels leave the ground. Looking forward to it.
I'm Alexandra Louveau, and I am one of the technical leads for community testing with the X-59. We're going to be surveying the public in different communities across the U.S. to better understand how they perceive the sound from the X-59. My role in the community test is to ensure that we've accurately measured the sound of the sonic thump from the X-59. This data will be able to provide to the U.S. and international regulators so that they can change the rules so that in the future, you and me will be able to fly supersonic around the world. So I started playing the violin in 3rd grade. When I went to college, I studied music engineering, where I got to learn a little bit about microphones and loudspeakers and recording of music. My husband and I play in a local orchestra called Symphonicity. We put on several performances throughout the year, and we like to say that we just play for the love of music. Origami I picked up, I don't know, at some point in college and just thought it would be a fun thing to do. And it turns out that my husband also really likes origami. So we've actually gone together to origami conferences to learn how to fold more fun things. One of the things that I love about my job is actually being able to partner with people even outside of NASA, and working in this international regulator group is actually a lot of fun, where there are people from different places, different cultures, different backgrounds, but we're all working together towards the same goal. I'm really excited to hear the first sonic thump from the flight of the X-59. That'll be the beginning of a new era for commercial supersonic overland flight.
I'm Larry Clyett, and I am the technical lead for the acoustic validation phase of the Quest mission. During the acoustic validation phase of the mission, that's where we will measure the sonic thump and make sure it's as quiet as we designed the airplane to be. We'll do that a number of ways. We'll do that on the ground with a lot of sensors scattered throughout the desert. And we'll do that in the air too, with some airborne systems that have recording devices that can measure the sonic thump of the airplane. So I love to cook. It's probably my #1 hobby. I like trying new concepts, new ways to cook. I like making Asian foods, just Asian-inspired cuisines, whether it's Chinese, Japanese. I love making Thai food. I love to barbecue, and I think a big part of my love to barbecue and to smoke different foods is the method behind it. I mean, it's a process. I've loved Legos since I was a kid, and then I think only maybe 4 or 5 years ago I discovered that Legos can be for adults. And part of it is a little bit of escape. Everybody needs a hobby to get away from the demanding job, but a lot of it is just continuing on that creative mindset into our daily personal lives, I think, as well. The Quest mission is not just 4 or 5 years old. It's 5 or 6 decades where NASA has been investigating the ability to quietly perform supersonic commercial transportation, to be able to go from point A to point B faster. It's a very big collective effort across the mission and across many NASA centers to make that happen. And so that's what really excites me about all this.
I'm Tiffany Titus. I'm the ground operations lead for the Quest mission at X-59. As the ground operations lead, I'm responsible for overseeing the planning and execution of all things ground operations with the X-59 aircraft. I'm kind of in a way like a wedding planner, where I'm making sure the plane is ready to go from a maintenance standpoint, making sure all the teams are ready to go to support the mission, and just really making sure everything comes together kind of like you would on your big day. Prior to joining X-59, some of the projects that I supported included studying sonic boom acoustics and sonic boom interactions, including the Schlerin imager that's now famous of the 2 T-38 interactions. Watching Sally Ride launch on STS-7 back in the early 80s really inspired me to want to go into science, technology, and math and just pursue that career. And now I'm here today, thanks to Sally Ride. When I'm not at the office, you can pretty much find me in the Sierra 24/7, whether it be winter, fall, spring, summer. I love being in the mountains and I love being off the grid exploring. It's just a place of, for me, zen, relaxation, a chance to explore and just wander. My husband proposed to me back in the Sierra, and our wedding was actually at a lake in the Sierra where we had friends backpack into to join us. I really enjoy getting to do STEM outreach working at NASA. I think it's great to be able to go to different events, basically just inspire them to keep going, to ask questions, to keep pursuing things that they might not normally think they have a chance to do. As a girl growing up in Michigan, I never thought I would have the chance to really see something like X-59 fly. It'll just be really neat to see all of it come together and all that hard work of the team members just really pay off.
Hey, everybody. Welcome to this episode of NASA in Silicon Valley Live for October 11th, 2018. I'm your host, Abby Tabor, and today we're going to be talking all about robotic exploration of the moon. And we have some really fascinating guests with us. But first, let me introduce my co-host, Cassandra Bell. Hey.
Hi. So this is NASA in Silicon Valley Live, a conversational talk show out of NASA Ames Research Center with the various scientists, engineers, and researchers and all-around cool people at NASA to talk about all the nerdy NASA news you need to know about. If you like that, we're simultaneously live on Twitch. That is twitch.tv/NASA. And we're also on Facebook and YouTube. And if you want to participate live in our chat, you got to catch us on Twitch. But if you miss the live show, we will be on demand after the fact on NASA TV. And we can also have the podcast for an audio version if you like that better. So today we have with us our guests, Tony Colaprete and Kimberly Ennico-Smith. Thank you both for being here. And can you tell us a little bit about what you both do?
Yeah. Hi. Thanks. I'm a planetary scientist here at NASA Ames. I've been here about 15 years, almost exactly 15 years. And as a planetary scientist, I mostly study planetary atmospheres and surfaces, really focusing on ices and other volatiles that freeze out. I also design and build instruments that go to different worlds and make measurements of the atmospheres and surfaces and things like that.
Very cool. And Kimberly?
Well, thanks for having me. I'm a research astrophysicist here at NASA Ames, and I've been here a little bit longer than Tony. I study the universe, and I also build payloads or instruments, cameras, spectrometers that help us understand the universe around us, both near and far. So I have dabbled a little bit in some of Tony's planets as well.
Very cool. Well, speaking of nerdy NASA news, NASA just turned 60. Yay! Happy birthday, NASA.
Should we sing?
Where's the cake?
Oh, there was cake.
Last week we had cake.
Yeah, I missed it.
It was
I
good.
missed it. I had a lunchtime meeting, and I think I missed the cake.
It's very good cake. Well, NASA turned 1 on October 1st, and that would 60 years would be October 1st, 1958.
Do you guys know what actually happened at that point? Because, like, you picture the president signed a thing and then NASA suddenly existed, or like it was
his birth certificate.
It was his birth certificate. Signing from a birth certificate. It must have been built on earlier research labs that existed, right?
Yeah. And at the time, it was aeronautics was the focus of what the laboratories did. They weren't doing space research yet, but they were very heavily into understanding aerodynamics, aerospace engineering, and whatnot to help really the fledgling airline industry and aviation industry, doing the things that they couldn't do, helping them do the research they couldn't do.
And pushing the envelope, see what else you could do, by different designs.
Oh, yeah.
And that was the NACA, right?
Yeah.
Yes, don't call it NACA.
Okay.
No.
Don't call it that. No, the National Advisory Committee for Aeronautics is what preceded NASA, right? And I've been scolded for calling it NACA.
We are NASA, but that was NACA.
That's right. Yes.
Yeah. And there were 3 centers at the time.
Right.
There was one out of Langley, Virginia.
On the East Coast.
On the East Coast.
Yeah, and now that's Langley. What's it called now?
I went from the Langley Aeronautical Laboratory to the Langley Research Center.
That's right.
One in Ohio.
Yep.
Which was, do you guys know?
I always forget this one. It was Vincent? No, what was it?
Lewis.
Lewis. Vincent Lewis. I was close. Lewis. And it's now, of course, the Glenn Research Center. I know that. Yeah.
And then our favorite.
Our very favorite, not biased.
I can't remember the third.
It's out here in California. Oh, the Ames.
You might have been there. The Ames Aeronautical
Laboratory. So now known as the Ames Research Center.
Where we are right now today.
Yes.
Of course. Yeah.
And now that we have 10 field centers doing all kinds of amazing work. So to learn about the last 60 years of innovation, go to nasa.gov/60.
Yeah, so in this episode, though, we're going to focus on the moon research, the lunar research that Ames has worked on over those years since NASA was founded. And if you have questions, be sure to leave them in the chat, and I'll be checking for those and trying to throw some of those in later. For example, already we have questions from Zazie Lavender, who's asking, what things will you be exploring on the moon? We're going to come to that. That's the heart of today's episode. So to kick things off, we're going to go to our first segment, Let's Play. Let's roll that. All right, it's time for Let's Play. This may include game controllers, 12-sided dice, or a pop-matic bubble. But basically, it's all an excuse to play games and talk about science. And so today, what we have is the Lunar Firsts Pop Quiz. Surprise!
Didn't know there was going to be a quiz today.
You're getting a quiz, and everybody watching, you can leave your answers in the chat, and we'll see how you fare. So I'm going to
payload.
Yes, I'm going to ask a question, and there will be an image on screen associated, and we'll see how you do. Okay, question 1 here. On March 3rd, 1959, the United States sent this spacecraft to the moon, successfully making the first U.S. lunar flyby.
So what was the year again? 59.
59.
So part of the Mariner series,
Mm.
right?
Yeah. Well, the Mariners, they went to Venus and they went to Mars. Did they go to the moon?
They did a flyby.
Did they? Okay.
It's not this guy. This is another.
Maybe a first. A first person.
A trailblazing kind of
like the
space.
Pony Express?
Oh, maybe like a pioneer.
Exactly.
And I know about the pioneers that went to the outer solar system, but we went to the moon as well. That's
I think they did the flyby. So
Yep.
Yeah.
one of the earlier ones. Do you know the number too?
Well, for full credit.
Full credit.
But for partial, you got Pioneer. So this is Pioneer. Pioneer 4. Yes,
Pioneer
exactly. Very good. All right. Moving on to number 2. On October 27th, 1961, NASA accomplished the first successful test of this rocket, which shares its name with the family of rockets that would eventually take humans to the moon.
Wow.
This one's easier.
Yeah. Well, the Upgoer 5, or Saturn 5, took us to the
Saturn
moon,
5.
so it must be the Saturn series.
It is. Yeah.
Single stage, Saturn 1.
Yeah,
Yes,
exactly.
ding, ding, ding.
First test.
Yeah.
Very good, very good. Saturn 1. All right. Question 3. Let's see what that looks like. On June 2nd, 1966, this spacecraft became the first American spacecraft to soft land on the moon.
I'd have to survey my answers.
Surveyor! I like being Surveyor 1.
It is. Surveyor 1. Excellent. And I have a fun fact here that Surveyor 1 transmitted more than 10,000 high-quality photographs of the surface of the moon.
Yeah.
Wow.
As it went in for
And
landing.
the Surveyor series of these landers, this is before we had digital cameras.
Oh, yeah.
These are video cameras and film.
Oh,
And so you
yeah,
talk about how many photos?
10,000.
10,000 photos?
That's a lot of film.
That is a lot of, a lot of film.
I never think about that. Yeah.
It's a lot of
It was film back then. All right, one more question, number 4. On July 20th, 1969, this Apollo 11 astronaut became the first person to walk on the moon.
That's
People should know that.
Yes, everyone should know this.
Yeah. Neil.
That would be Neil Armstrong.
That is Neil Armstrong, exactly. Very good. So well done. You've passed your pop quiz. And
You burned your meatball.
that's right.
Your NASA meatball.
That's your prize. So if you're just joining us, we're talking about robotic exploration of the moon today. And before humans got there, before Neil, there were robots. So Cassandra, I think, is going to walk us through some of that history.
Yes. So it all started with robots.
Yeah, it started back in the late 1950s when a little orbiter named Sputnik went overhead and ushered us into...
Beep.
There it is. I hear it now.
Sputnik.
Every 92.6 minutes.
Yeah.
That's the orbiter around the Earth. So.
Yeah. And it ushered in the space age. And with it, the exploration of the Earth from orbit, but also beyond the Earth. And as part of the space race to the moon, the effort between the United States and the Soviet Union to get to the humans to the moon first, there was a range of robotic missions that took the steps necessary to eventually bring humans to the moon and return them safely.
And talking about steps, you have to leave the Earth safely. You then have to get to the moon, so you have to be able to reach the moon. And then if you want to go in orbit around the moon, you have to be able to go and get captured by the... There's a lot of different steps to when you're starting to explore. So you can use these robotic, messengers to work out all the kinks.
Okay, so Sputnik started it, and then
There were a few kinks.
Yeah.
There were a few kinks.
Yeah, I mentioned some of those.
gosh, we got out of the 50s, we got into the 60s, and what was next?
Well, so the first series with respect to the moon was the Ranger series, and that was, as Kim described, really just learning how to get off the moon, or get off the Earth to the moon.
To the moon.
Yeah, and that was a challenging period. The first 6 Ranger missions had failures or problems to make them not fully successful.
Yeah, one of them missed the moon, but that was but that was just, the rocket fired at a slightly different time, and the moon and the Earth are moving with respect to the sun.
I think we have a video.
Yeah, we do. We have video of Ranger 7 launching.
This was the first fully successful Ranger mission. Ranger 6 hit the moon intentionally, but its camera failed. The first 2 failed on launch. Others, the fairings didn't work. That's the part that holds the spacecraft. This one was first fully successful, and it did everything from teach us how to navigate to the moon, but also transmit data. So these are images of the moon as we go into crash. It's controlled landing, controlled hard landing, and it's beaming live television.
Wow.
Live from the moon, images from Ranger. So it was a really important series, and it was key because without doing that, being able to get to the moon, you can't do the next step.
Which is?
Go in orbit around the moon.
There you go.
Okay.
Yeah. And then
Step
if you
by
go in
step,
orbit around the moon, then you've shown that you can slow down your spacecraft that you've launched from the Earth and it's traveling really fast, and then control it to go and then even look at the moon and take pictures. Or perhaps you can look at something else.
Yeah. Speaking of that, I know one of your favorite images, right, is Lunar Orbiter 1.
Lunar Orbiter 1.
Yeah.
Spacecraft from, that was, we got our first image of our homeworld of Earth from lunar orbit, and that was from Lunar Orbiter 1. You're seeing it right now.
Oh, yeah.
Took place in August of 1966, and phenomenal. I mean, it's a perspective-changing photograph, because this is us looking back at home from our nearest neighbor, the moon.
Yeah.
And you can see it's, again, a video camera, and they processed the film on board the spacecraft and sent it back. And that's also technology that had to be developed.
So they had to develop film on the moon.
Well, it's on the spacecraft from lunar orbit, and then sending it back. So then we get these amazing pictures of both the surface of the moon, but also looking back at the Earth.
Mm-hmm. So that one had stripy bands throughout it.
Yeah, those are the bands of film. So they actually had the TV camera go across an image, take TV motion picture of the film, and that's what was beamed back to Earth. So that's why it looks striped that way.
I see. But then you were telling me that this was reprocessed more recently here at Ames?
Yeah, there's a group of citizen scientists who take an interest in the history of NASA, and look at this beautiful picture you're seeing right now, digitally reprocessed. And so that's that same image from Lunar Orbiter, and with today's computer techniques and looking at images, you can remove artifacts and maintain the image.
Yeah.
So, and some of our best images of the moon come from that period. I mean, you capture a lot on film. Really high quality.
Yes.
Wow.
Yeah.
I mean, down to the smallest of scales, to the dynamic range.
So we orbited the moon.
Yeah.
And then
next step,
there's another step after that.
Get to the surface. If again, the ultimate goal at this period was to land on the moon, land humans on the moon and get them back, we had to get to the moon and get to the surface, and not in the way Ranger did. That was a hard landing. And sometimes a crash.
Okay, but intentional.
But intentional. So the
Okay.
difference between a crash and a hard landing is one's intentionally.
One's planned.
Yeah, one's planned.
Okay.
So the next set of missions, surveyor missions, really were intended to understand how to land on the moon softly and in a controlled way. Mm-hmm. And they taught us not just how to land, but how to land where you want to land. Because you don't.
That's another skill. Know exactly, where on the moon to pinpoint.
Yeah, we had these images from orbit. We knew we wanted to go to this place. How do I get a spacecraft to go to that place? It's easy now with GPS, right? You pull up your map app and
you just plug in the phone.
Yeah.
Moon.
Exactly. Moon. Yeah. Put in your coordinates. So there was all those technologies that they had to learn how to have the rockets not only slow you into orbit, but now slow you down so you fall out of orbit and do a controlled landing.
Mm-hmm. And that was to learn about. They were trying to learn about the surface?
Yeah, so one of the biggest questions at the time was how deep was the lunar dust? We knew there was a dust that covered the moon generated from meteor impacts, churning up the the surface. There was all kinds of theories about it being very, very thick and very, very porous or fluffy.
Oh, really?
Like a deep powdered snow, if you will.
Oh, imagine that.
And so there was a real concern that
If you landed something on the moon, you could sink.
Like trying to walk in deep snow is just
walking in like
don't really
deep
get
snow.
very far.
And if you're landing a spacecraft, maybe the feet just go straight down and you just fall over. The spacecraft falls on its side, whatever. So
They're sending the robots, the robotic, before the humans came, answered a lot of those questions.
Yeah.
And we made us realize that, you can
could.
do
This
the
is
soft
doable.
landing. And in these places of the moon, you can land safely.
Wow. Yeah, I have a quick question from the chat. This is a fundamental moon question from Babu Kar. How old is the moon? As old as Earth?
it's yes.
Yes.
And nice round numbers.
8 nice round numbers. Like one significant figure.
Yeah.
As we like to say.
Yeah.
I mean, the origin of the moon is something that we're still trying to understand.
Exactly.
I mean, there are theories out there, and theories are only tested by observational evidence, and we don't have that time machine, a TARDIS, to go back in time to find the birth of the moon.
Right.
But the leading theory is that at some point during the early parts of our solar system, a Mars-sized object hit the early Earth and spun off what now has become our moon. And that's got a lot of observational evidence that we can support that. But we weren't there to watch it happen.
We didn't see it happen.
So it is quite old.
It could be then, if that theory is right, it's just a little bit younger than the Earth, but made largely, or in large part, of Earth material. So in a way, it is as old as the moon.
And this is one of the reasons why we want to study the moon, because it also tells us about our own origins.
Exactly.
Very much at a fundamental level.
And you talked about that surveyor mission, trying to figure out how fluffy or not fluffy the moon is. Kimberly, you said one of your favorite pictures has surveyor in it?
Oh, yeah. Here's to bring this one up. This is from Apollo 12, and what you're seeing is astronaut P. Conrad walking up to Surveyor 3. In the background is the lunar excursion module from Apollo 12. They pinpointed exact landing to about 600 feet of Surveyor 3, and they did that deliberately for, of course, testing where you can land strategically.
Okay. See if they could do it.
But now they're going up and saying hello to the robot that came 2 years earlier, and looking at the experiments that were on board and brought back equipment from the surveyor. But there was a surveyor that set the scale for the landscape, and then we followed it with the humans. And I just think it's both logical and poetic when I look at this picture, because it shows that the robots help with the human exploration, and also, it's just just That's why it's one of my favorite images.
Yeah, there's a lot in there.
So after these Apollo missions, so we got to walk on the moon.
Well, Apollo 17 was the last mission that we flew, and one of the best. And it was 1972, and then after that, nothing happened. Nothing.
It's the dark ages of lunar exploration.
Yeah.
We went into a dark period.
Until
for NASA, it wasn't until 1994 that the United States returned to
22
the moon.
years, you said?
22 years.
22 years after the final Apollo mission.
Okay.
And that was the Clementine mission, which was a Department of Defense
Not the fruit.
spacecraft.
Those are good, though.
and,
Not the oranges.
and it had some NASA instruments. So it was a DoD spacecraft, but it had NASA instruments on it. But it's a really important mission because it tested and others that water could exist at the poles of the moon. Because the moon has a very slight tilt in its axis, much smaller than Earth's, craters at the poles have floors that are permanently shadowed. So it goes back to the question of when did the moon form. It goes back for these shadows have been at the bottom of these craters for as long as the Earth's been in its current obliquity.
They've never seen sunlight?
For 2 billion years.
That's
or more.
so crazy. I only learned that recently.
And because they haven't seen sunlight and there's no atmosphere, appreciable atmosphere on the moon, they are cold. Minus 250 degrees below 0 centigrade.
Oh,
which I looked up. You told me that before, and it's like minus 400 Fahrenheit, I think.
Yeah,
It's cold.
It's really cold.
Okay.
And it's cold enough to trap all kinds of things, including water.
I brought my little moon model.
There's the moon.
It's my huggable moon model. It's a plush toy.
Very sweet. So
Do you
you're
think-
talking about the poles?
Yeah, and we were talking about the poles, the north and the south, and a lot of our earlier explorers had looked more around the equator, the tropics, you could say. But what was fascinating with the Clementine, and we learned that the poles are special places because of the moon is slightly tilted.
So what's special? There might be water, you said?
Yeah, so there might be water trapped in these craters, and that was speculated back in the late 1950s. So the Clementine mission did an experiment to test this using radar, and they saw a result for a particular crater at the South Pole called Shackleton, and it suggested that there could be bulk water ice.
Really?
Problem is,
it was inconclusive.
It is inconclusive
because the
yeah.
results could have been explained by large rocks.
Oh wow!
And they couldn't tell the difference between the data. So what do? You have to.
Yeah, and then there was one other. You have to go. You have to return. You have to, like you said, you learn from your previous experiments, right? And add to it. So that was tantalizing, not conclusive, but it inspired the next mission, which happened 4 years later, 1998. And this was a NASA-led mission, actually led by NASA Ames.
Right here.
Yeah,
Cool.
And it was called Lunar Prospector.
Oh, I think we have a model of it.
Yeah, we do. And but be careful; it's as old as the original spacecraft. So yeah, Lunar Prospector did exactly like its name suggests. It looked for certain compositions and really elements. What it did, out on these booms here, these long arms, were instruments that measured the surface composition. And one of the things it was looking for, one of the elements it was looking for was hydrogen. Now, why hydrogen? Well, there's two hydrogens in any water molecule you might have.
H2O.
H2O.
Yeah, the H and H2O hydrogen.
So if there is indeed water at the poles of the moon, it might be able to see it in the form of an increase in hydrogen. And lo and behold, at the poles of the moon, it saw increases in hydrogen. And it didn't see it around the equator, which really did suggest there was something inherent about the qualities or conditions at the poles of the moon that was allowing this hydrogen to accumulate.
So we had to wait to the 1990s, right?
Yeah.
To actually get our first glimpse of a global chemistry of the moon.
Yeah.
And it raised more questions.
So Lunar Prospector did all of that, but can you tell us more about what we're looking at here? This is a model of it, yes?
Yeah, it's a model. It's a very simple spacecraft. It's about, I think we have a picture of it. It's about the size of a human.
Oh, yeah.
There
Human
you
size.
go.
Here we go. Yeah.
So there it is on top of the booster that helps put it into lunar orbit. So just the shiny blue part on the top is the spacecraft. Those are solar panels. The white spike is the radio antenna for beaming back information to Earth. And you can see the booms are stacked along the sides. They're packaged for launch. And it had three relatively simple instruments, or suites of instruments, that measured the magnetic fields around the moon and the composition. It was so simple, this spacecraft, that you could say it didn't even really have a computer on board.
Didn't have a computer.
No. It didn't run software like we think it would run software. It had processes and electronic processes that were event-driven and commandable. But otherwise, it's pretty much just turn on and go. And it just spun in orbit. And I think we have an animation if you want to look at that. It just spins in orbit. And there you go. It just goes around.
That's a very efficient way of keeping control of the spacecraft as well.
Oh, the spinning?
The spinning.
Okay.
Yeah.
Keeps you stable. These instruments didn't have a lot of pointing needs. You didn't point them at the targets. It just went around the moon.
Scanned it.
And a relatively low orbit and made these measurements. And at the very end, like all things that are up, it had to come down, and it crashed right after about
a hard landing.
It was a hard landing. It was going to crash. It was running out of fuel, but it was directed into a place where there was this excess hydrogen. And the reason they did that was they knew it was hydrogen, but they didn't know the form of the hydrogen. They didn't know if it was the H in H2O. Okay. It could have been the H in OH, or the H stuck onto a mineral, or just protons from the sun. The sun's constantly sending protons into the soil.
And like good scientists and engineers, they wanted to get something more out of this amazing mission.
Exactly.
And they did an experiment. They did the controlled crash of this spacecraft into one of these craters.
Yeah,
that had the hydrogen
into
signature.
Shoemaker crater.
It was on the South Pole.
the South Pole.
Okay.
And it had this elevated hydrogen. And the idea there was, we'll crash this spacecraft into it, and as it hits the dirt, it'll splash the dirt up, and that dirt will come into sunlight. Remember, the dirt, where it's impacting, hasn't seen light in 2 billion years. Yeah. So to see it, it lifts it up into sunlight, and then they were going to observe it with the Hubble Space Telescope.
So they're going to point Hubble at the moon at this precise time.
Exactly, yeah. And it all went to plan, it impacted, and Hubble saw nothing.
Nothing.
But you have an experiment, and sometimes you don't know what you're going to see.
Exactly. Yeah, it's not, and it's difficult at the time. It was very difficult to predict what they were going to see. It was the first time they'd ever tried something like this. So just like in the Ranger series, where the first few launches weren't so good, this is the first time they tried an experiment like this.
And why do they think Hubble didn't see anything? What about this didn't work?
Yeah, so we looked at that, and we looked at that because we were planning a follow-on mission to get at that question: what is the hydrogen?
Again, learning from what came before.
Exactly. And that was a mission that came later, about 10 years later, called LCROSS. And what we did was we learned a lot about what not to do. What this did, Lunar Prospector, it came in very shallow, a grazing angle.
It's in orbit around the moon. And so when it's going to re-enter, it's going to come in at a shallow angle.
Shallow angle. And it's not
very large.
What do you mean by
shallow?
Shallow, just kind of grazes, almost skipping a rock.
Oh, okay.
And it's a small spacecraft, as you saw. It's only about 130 kilograms, 300 pounds.
300 pounds.
And so, again, if you want to make a splash, you throw a bigger rock, right? The bigger the rock, the better. And it was going relatively slow. Because it was in orbit, its top speed was only about 1.8 kilometers per second. Which is slow. It doesn't sound slow, but that is slow.
Yeah, you say so.
In space, that's slow. Yeah, that's space, that's slow. So all those things led to probably a very small splash. So not a lot of material got up, if hardly any. It didn't just have to splash dirt. It had to splash enough of it to get into sunlight so that the Hubble Space Telescope could see it, because it couldn't see in the dark. So that's where, again, the next NASA impactor mission, and the next NASA Ames mission to the moon comes in.
Is the 3 out of the 5 lunar missions were managed here at Ames, and this is one of the...
Yeah, this was the first one managed at Ames.
Yeah. Ames is actually quite a leader in lunar research. I just want to mention that my questions are not loading at the moment, so I don't have any questions from the chat for you just yet, but hopefully we'll get those up and running before the end, so we can throw you a lot of questions.
Thanks.
So we can put you in the hot
quiz,
seat.
Questions.
Now, LCROSS, you just mentioned, is a special mission for the two of you, right?
Yes.
Tell us how you were involved.
It was one of Tony's ideas, and I helped build it.
Wow.
Exactly. I had a crazy idea, and I told Kim about it, and she said, yeah, it's crazy enough. It could work.
So what does that stand for, LCROSS?
Oh, no. Lunar Crater Observation Sensing Satellite.
Yes, that's right.
Think what was part of the quiz?
It's continuing.
It's not the sport, lacrosse.
Okay, very different.
It's LCROSS.
So, and this was a very special, unique in its design.
Than the other one.
Yes.
And so, if you recall, what I said was bigger rock makes bigger splashes.
Yes.
Right? And so, and it's
the bigger
hard.
Rock?
This is part of the bigger rock. Yeah.
Okay.
It takes a lot of. It's very expensive to launch large things into space. So we didn't want to just launch or spend a lot of money, if you will,
and bring a heavy rock with us. So
we used the. This is the upper stage to the Atlas V that launched us to the moon.
Oh, so it's part of the rocket.
Part of the
rocket.
That was going to be there anyway?
Yeah.
Okay. Yeah, it's the one that got us, to leave the Earth system and go to the moon, and it would have eventually fallen back to Earth. It's space junk, but we recycled space junk and turned it into a scientific experiment.
That's right, and
yes.
and
It's a great idea.
So there's your bigger rock compared to the
so cool.
140 kilogram impact from the spacecraft. This is 2,500 kilograms, 2,500.
So about 5,000 pounds.
Something like that.
Yeah.
It's like the size of a school bus.
School bus and
School bus.
It's a much bigger rock.
It's a much bigger rock. Yeah, exactly.
So you pulled them apart.
Yeah.
And it's a smart. This is we had some smarts on board too.
And also it came in at a very steep angle. It came in at 89 degrees, so it wasn't skipping a rock.
Because we came from Earth orbit and we actually crashed into the moon.
Not to scale.
So not to scale, but we came in a very almost 90-degree angle.
Okay.
So therefore we don't have the grazing incidents. We're gonna.
So your rocket hits the moon, and then this little guy.
And the best part, we call this the shepherding spacecraft because it tugged this around for 100 days, about.
Yeah, 2 months, 2.5 months.
Yeah.
Well, we had to do that because the upper stage of the rocket contained hydrogen and oxygen, the fuel of rockets, and we're trying to find hydrogen and oxygen water on the moon. So we were just drying it out for 2.5.
Open up the vents and dry it out.
The operators of our shepherding spacecraft, when they tugged, we had this massive weight on the back. Of course, in space it's weightless, but it does affect how much your propellant was. When we separated, that was we've gotten rid of our loads.
Yeah,
so
exactly.
we were trying to relearn the spacecraft. It was really cool.
Yeah, and so one of the you're talking about the separation. That's one of the best parts actually too. So we had the big rock coming at steep angle with a lot of energy. It came in also almost twice as fast. We had this shepherding spacecraft. It wasn't just a tugboat, but it had instruments on it, and that's what Kim was mentioning. She was the lead for
like a camera.
Oh, cameras, spectrometers.
5 cameras, 3 spectrometers, a radiometer, and so
it was smart.
It was smart.
We had a smart payload.
And it actually observed the impact.
Oh, I think we have a video.
Yes,
of it.
the impact's better than me doing this. Yeah.
So there we are with a separation, and you can see the Centaur's on its way to the moon. In fact, the moon got in its way, and we're turning the shepherding spacecraft around, and we're following behind. And as the moon got in the way, the impact happened, and we are taking data live stream back to Earth, and 4 minutes behind. So as we flew through the ejecta from this impact experiment, we ourselves, as a spacecraft,
here we come,
fell right into the moon as well. So all the time the data is live from the moon being streamed back to Earth, and we were commanding all 10 instruments.
You were commanding?
Yeah. Yeah,
tell us about that moment.
Oh, well, it was very, we had 4 minutes of data, and the fact that you couldn't store and, look at it later, it was all coming down in live stream, and we were changing the exposure times of the cameras in real time.
During your 4 minute?
During our 4 minutes. And this was also happening at 4 in the morning, because, when you're going to do something like this, it always happens at 4 in the morning. So we had separated from the Centaur about an hour prior, and we were taking data, and as the moon was coming closer to us, the complexity of the scene was starting to have our instruments start getting a little bit overloading. So we were actually adjusting the gain and exposure times of our camera in real time.
Oh my gosh.
During 4 minutes.
Yeah.
Do you have 4 minutes to get this?
Yes.
That's it?
And one of my favorite memories from that was the exposure. She knows what I'm talking about. So they're dark craters. You can't see in them. But we had some cameras. We had thermal cameras. We also had one that looks into the near infrared. It's just past the visible wavelengths of light that we see. And the soils in the area where we impacted on the moon are actually brighter in these near infrared wavelengths. So some light scattering off of rim tops goes into the dark craters, and we thought we might be able to image them with our cameras, and for the first time get an image of the floor. And this was a risky thing. We wanted first and foremost just to get good images of where we were impacting the plume and so on. But about 3 minutes in or so, Kim and I decided, let's change the exposure.
3 minutes into 4 minutes.
Yeah, exactly.
Yeah.
Seriously.
And so
we were just going to...
And we didn't control it. We had to call in the request to command, who then had to get approval from flight. So, there's process, right?
Okay.
And, of course, we had lots of cameras. We have 5. These are the near-infrared cameras we want to change, NIR. We also had mid-infrared cameras, MIR.
Different camera.
Different camera. Kim calls in, change near IR1 exposure to 3. Command, copy, MIR1 exposure 3. No.
NIR.
This goes on
This
like
is N versus M.
M, exactly. This goes.
We're going to hit
The moon is getting really big.
That was really.
So finally, it goes on a couple more times. Finally, Kim screams, "November! November! November!"
Instead of Mike, the alphanumeric.
Yeah, and he got it. Then Command goes, "Oh, NIR1," and then he made the change and.
In time.
In time. And we have a video here that shows those images. Those are still the only images of the impact site that we've gotten from it. And they're beautiful because it actually showed the crater we made.
Yeah.
And you could see it, and we measured it. It was 30 meters across.
Mm. Wow. And we're looking in these permanently shadowed regions that don't have any sunlight. And we're looking at it in the infrared because we can get the scattered light off the crater walls, but then we also were able to measure the thermal signature, the heat from the impact.
Yeah.
And we're able to find the crater we made.
Yeah. Oh my gosh.
It was a really neat experiment. It was a really fun project.
Sure. Yeah. I have a question here from the chat. Could setting up a telescope in a dark crater on the moon be beneficial to astronomy?
Oh, I'll let the astronomer take that one.
Absolutely. Actually, having a telescope on the moon in general would be wonderful because you don't have the atmosphere in the way. And the atmosphere prevents us from seeing a lot of light. In fact, telescopes on the ground are really restricted to two wavelengths, the visible, what our eyes can see, and also the radio that can transmit through our atmosphere. And having a telescope anywhere on the moon would allow us to see a whole range of light. Now, if you were in the permanently shadowed part, you have to, deal with technicalities of how you keep everything warm because it's also very cold there.
Your equipment.
And from using a telescope to look at things in the universe, you just have to stay away from having when the Earth comes into your field of view, it's a nice bright reflected ball because of the sunlight reflecting off the Earth. And of course, you don't want to look at the sun, but yeah, you can look at the universe from there or anywhere on the moon.
Very cool.
Yeah, I think it's.
Yeah. So. I don't know if you had a question, but I want to know what this thing is all about. Okay,
yes,
so
I'm curious.
Getting back to LCROSS, which you crashed into the crater.
Yeah.
See what was in that debris. Okay, I know that a month after that, there was a press conference, right?
Yeah.
And you turn up with a bucket, right?
Yes.
Okay, we have a photo of that. Younger Tony with his bucket at the press conference. There he is.
I don't age very well, I don't think.
Oh, nonsense. So tell us what's going on there.
So, the unfortunate thing about an impact mission is it comes to an end very dramatically, and everybody wants to know, well, what'd you see? What'd you see? This is actually our second press conference. Kim and I had to prepare for a press conference 1 hour after the impact. So at 5 a.m.
Pacific, which is 8 a.m. East Coast time.
Oh, yeah.
So that was the first one. Then 1 month later, after working, basically the entire team working 24/7, we came to a unanimous decision to go forward with the results, which was we found water. And it was not a small amount of water. It was a significant amount. And I was talking with my wife, actually, about how to convey this, because I could talk, it was 5% by weight, or it was, 1,342 kilograms and a 30-meter.
What's that mean?
What is that exactly?
And you're like 5% by weight, whereas water in the Sahara deserts on Earth are 3% by weight. So we did sort of hit a relatively dry, but still has a lot of water.
So the moon pretty wet, right?
So wetter than the Sahara Desert.
Wetter than the Sahara Desert.
About as wet,
Yeah, it's even comparable to Earth. That's pretty crazy.
Yeah, it is, isn't it? Yeah.
So we were,
Yeah, and so my wife said, well, how many buckets is that? I'm like, buckets? She's like, why don't you just get a bucket and say, I got this much water on the moon? I said, okay, I could do that. So we got a 2-gallon bucket, and in that press briefing, we said we found not a small amount, we found a significant amount, and actually, in the little hole we made, teeny little hole we made, we had 150 of these 2-gallon buckets, or I forget the exact number at the time. So that's the origin of the bucket. And I think it made a good point. And that's actually really key. And the other thing that I like about using the bucket was LCROSS was not a science mission. It did fantastic science, but it was not a science mission. Its purpose, it was actually supported and funded through the Human Exploration Office in NASA, not the science mission. Its purpose was to understand that hydrogen as it related to a potential resource. Okay. Could we use the hydrogen on the moon for making water, for
Making fuel.
rocket fuel.
Making fuel.
And that's the most important one. It takes a lot of energy to lift anything out of the gravity well of the Earth.
Using resources right there, right on the surface.
Making it here, bringing it up is not efficient.
That's not efficient. If you can make it there, you're saving a 90% of your fuel need, because you spend 90% or so of the fuel just to get off the Earth.
And LCROSS just sampled one tiny place and had buckets of water, and all those images from the predecessor orbiters that showed hydrogen signatures and many, many craters on both poles. There's a lot of resources there.
Yeah.
So the anniversary of that was Tuesday?
Yeah,
it was last Tuesday, 9
October
years
9.
ago.
9 years ago.
And we're still writing papers on it.
Yeah.
I mean, it's 4 minutes. All the data could fit onto a circa 2009 thumb drive, and then have plenty of room left over.
Yeah, and it's also changed the way we were looking at the moon now.
Completely.
It really has, changed the way.
Well, yeah, and that's actually a really good point. The last thing I'll say about the results. Well, so there are significant results out of LCROSS that we reported at that meeting was we knew the form of the water, or the hydrogen. It indeed was, at least
part
in
of
part,
H2O.
was water, and we know now is water ice. We knew there was enough to be a potential resource for in situ resource utilization, and those were the two big questions. And the third thing was unexpected. We saw lots of other things besides water.
Yeah, it's almost like these permanently shallow craters are garbage heaps of the solar system. There's a lot of treasure troves
Who
there.
said that?
I don't know who said that, but maybe it's not a very colorful
Resource
image.
heavy.
Resource heavy.
And
we're all into recycling too. So here are ways you can reuse things that have been coming.
And the other things were like carbon dioxide, hydrogen sulfide, mercury,
sodium, argon.
Yeah, some of these things you can use. Some of these things you want to avoid. Like if you mine the water for drinking, you better get rid of the mercury. And so, but it's very interesting from a science standpoint. So from a resource standpoint, yes, interesting. But from a scientific standpoint,
where did it come from?
This says something about the origin of the water, and then therefore says something about the history of the moon and the Earth and all the inner planets, the inner solar system planets. And so it's really was an amazing finding from LCROSS.
Yeah, I mean, the moon is a laboratory, and it's a time machine back to, what had happened back then and what's been happening since.
That water and those other species have been there for at least 2 billion years.
So we found the water.
Yeah.
And now we followed up. There's another mission. We said there was 3 out of the last 5. What was?
Oh,
what was
yes.
that third one?
So we'll get rid of this guy.
And to warn you, I've got a bunch of awesome questions. So
okay,
good. You want to throw a question while we get the model?
Oh yeah, okay.
So Tony was talking about how we found all these other things in the basin of this crater, this one place, and you naturally ask more questions. That's the beauty of these missions. You find a discovery, but you're like, where did it come from? Did it come from within the moon? Did it come from things hitting the moon, bringing it, like comets or asteroids? Or, is it from the atmosphere around the moon? So that led to the next mission.
The next mission, LADEE.
Which stands for?
Lunar Atmospheric and Dust Environment Explorer.
Yes, you got that right. Another quiz continues.
Another quiz of the acronyms of NASA.
This is hard.
Okay, so this is LADEE.
Yes.
And
this
and
was
it looks different too.
Managed by Ames, spacecraft built by Ames, one of the instruments I led built here at Ames.
Wow. Which was a daughter instrument from the LCROSS mission.
Exactly.
We like to build upon our knowledge of what we've learned before.
Exactly. That's key. That's really important.
So LADEE was looking at?
It was looking at the atmosphere of the moon.
Okay.
We call it an exosphere. So an exosphere is an atmosphere where the molecules in the atmosphere never come in contact with each other. They're very lonely.
Oh,
they just bounce around and they never run into each other.
So it's so thin that there's just not enough to touch each other. Okay.
But it's important because, as Kim was saying, it says something about how the surface of the moon interacts with its environment, the space environment. And there are numerous other bodies like Mercury, the moons of Mars, the outer moons of Jupiter, Saturn, icy moons, that have these what are called surface exosphere boundary conditions, where they are interacting with space, and how they interact with micrometeorites, charged particles, etc., says a lot, or governs a lot of how they have evolved over time.
So this mission is, was designed to basically sniff the atmosphere. Sniff the exosphere of the moon.
Exosphere.
It's a big technical term.
And I think we have an animation of how it kind of went about sniffing.
Yeah. It also, if you read, now it shows it's spinning here, and it's got panels on all sides like Lunar Prospector did, but it actually had very fine pointing capabilities. It had to point its instruments in all different directions, mostly my instrument. I was the real pain in the
And it's barnstorming the moon.
And it had to fly
really
low. So one of the really interesting questions that Laddie addressed comes from Apollo, actually, and the surveyor. The Apollo astronauts thought they saw something that looked like scattered light from dust being elevated off the surface of the moon up to tens of kilometers above the surface. And there's these images from the surveyor landers that show dust near the horizon at sunrise and sunset. So there's this question, is there elevated dust around the moon near the terminators where you go from light to dark? Laddie had a dust detector and flew very low, just under 40 kilometers above the surface at the terminator, trying to sniff out that dust and other species. And one of the really important findings is it didn't see it.
So the astronaut saw it, but Laddie didn't saw it.
Laddie did not. Yeah. And robots are never wrong.
But humans can be.
I would never say that to an astronaut.
So what were the astronauts seeing?
It could be zodiacal light. They undoubtedly saw scattered light. It's the question is, where did it come from?
Yeah. And zodiacal light is light from our sun scattering off the dust in the plane of our own solar system, the remnants of our
so
our
not
solar
coming,
system.
it was dust, just wasn't from the moon.
Yeah, exactly.
Yeah,
Yeah,
it's just a background light
And
in our
there
local
could
solar
still
system.
be dust down low. We didn't get that low. You know, the surveyor dust could be just meters above the surface. To this day, though, Jack Schmitt, one of the astronauts on Apollo 17, really does contend that while there was dust, it wasn't on rock. So he's really of the opinion that this elevated dust is not there.
Okay. Well,
so we still have more questions. We need to go back,
many more
right?
questions.
Because
You
we
do.
have tantalizing evidence or non-evidence of things, you know?
Yeah.
I also have questions.
Yes.
Oh, more questions. Okay.
I suggest we forge ahead into
Yes.
our next segment, which is rapid fire questions. So let's roll the segment. All right, you asked for it, so here we go again. It's time for rapid fire questions where we cover as many from the chat as we can. So, quick answers, lots of questions.
Quick.
And then we're going to get to the future after some questions. So there are a number of questions about exploring caves on the moon. Are there plans to do this? People have heard about suggestions of building colonies in those caves to avoid solar radiation. Any plans to explore caves?
From NASA? Potentially.
I
So
think it'd be a great idea.
It is. Yes. So absolutely very interesting places. There are some commercial companies that are very interested in these locations as well. And NASA is now working very closely with commercial private sector companies who are going to be providing lunar services to the moon. And eventually, we're going to definitely be exploring those caves. There's a number of projects working on the technologies, methods, and whatnot for exploring those caves.
And the questioner was right about going beneath the surface to get away from the radiation. We're protected here with our magnetosphere that protects us from the space radiation that's coming mainly from the sun. Out in the moon, you don't have that exposure, but you can use rock or water as a shield.
Oh, yeah.
So, a cave is a lovely good
Caves
idea.
have potential.
Yeah.
Okay. Here's a cool one. What do your guests personally think is the most interesting mystery about the moon? What would you love to solve?
You first.
Oh, me.
Yeah.
Well,
I gotta think.
we had NASA had this mission called Grail that had two satellites, ebb and flow. And they flew around the moon, and they were to measure the. They wanted to look at the interior of the moon because we were wondering why, it's a little bit lopsided in terms of its surface and where its gravity is. So it gave us the first map of the gravity of the moon, and it's still kind of asymmetric. And so I think that's one of the interesting mysteries of the moon. It comes down to its origin. Again, we don't know how the moon formed, but we can see its signatures 4.6 billion years later, and try to work out, be that detective.
Right,
You know.
the things you can work
But
out.
I think
amazing.
the gravity field of the moon is intriguing.
Cool.
For me, it's the water.
Oh, yeah.
We know there's
Wow.
water, but we don't understand why we see it, where we see it, and why we don't see it where we think we ought to see it. Mercury also has water at its poles, and it is where you expect to find it. It is in where the models say that it has these permanent shadowed craters too, because it has no tilt to its axis, very little tilt, and it behaves. I always like to say Mercury is behaving itself. The moon, it's that crater is plenty cold, but it looks
still water. It's dry.
It's dry. Oh. The crater right next to it is cold and does have water. So that is an ongoing mystery right now, is the history of the water on the moon. Where did it come from? And this is very relevant for utilizing it, because you need to understand where it is to be able to access it at the scales we need to access it.
Okay. Quick question. Can you build houses with moon dust? Think we could use that as a resource?
Yes. Yeah. They can sinter. There's a lot of projects going on right now where they are developing the techniques to sinter, basically heat it up and form it into bricks.
Yeah. Or like ceramics.
Ceramics,
Yeah. Moon ceramics. You'll open up a shop.
Right, cool. We have like 5 minutes left, and we also want to talk about future missions, which is one of the questions. Do we have any named missions gearing up to land on the moon? I know Ames has some instruments that we're building to study the moon, but how would you guys talk about the future?
So right, there is Space Directive 1, which
from the president,
from the president, and he established the Space Council to see it enacted, and what it does is it gives direction to NASA to reestablish a presence on the moon in a sustained way. So it's not just, as our administrator says, it's not about flags and footsteps. It's about a sustained, permanent presence on the moon. So right now, NASA is building that plan to do that, and it's coming together right now and formulating right now. One of the big differences between what we're doing now and what we've done in the past is the involvement of the private sector and commercial companies. We routinely use private rockets to launch our hardware. Now we're talking about using private landed services to bring payloads to the moon for NASA. It's a whole new paradigm.
And we shouldn't ignore that the space between the Earth and the moon is also very special, because there's designs in place for what they call it the cislunar highway. Or a cislunar gateway. I feel like I'm babbling fiving or something, but it's like a gateway that it's a place where you have to we were talking earlier about getting to the moon is one part of that evolution of leaving the Earth and getting to the moon. But if there's ways to be efficient to refuel your modules, that will help add to the sustainability of a long-term presence.
Absolutely.
So there's infrastructure.
And here
using the resources
and you can put a telescope there, too.
And you put a telescope there.
I put a telescope there.
Says the astronomer. And here at Ames, we're actually two things we're working on, or two instruments that are going forward, are prospecting instruments. They're instruments that are used to look for water on a rover at the scales, what I call the human scales, the scales at which we would utilize it. One's a neutron spectrometer and one's a near-infrared spectrometer, and these are the bloodhounds that would go on a rover and characterize an area for the water form and concentrations and distributions, the things you need to know to establish whether or not, or how you're going to utilize it. Yeah.
That's something you tested here in California, right?
Yes, we've tested this.
Yeah, we have footage of the
So
rover.
this is on the K-Rex rover here at Ames. And on it are the two instruments. That black skirt there, we called it the skirt, keeps the sunlight out. We don't like the sun because it's looking through the atmosphere. It's built for the moon. These instruments are built for the moon. The sun carries other signatures on it.
And our neutron spectrometer is like a granddaughter instrument from Lunar Prospector.
Yeah.
And the infrared spectrometer is a granddaughter instrument from LCROSS.
LCROSS, yeah.
You keep saying that today.
We learn from we're building on the knowledge that we have passed.
And this is in the Mojave Desert, so that's why it's again water concentrations there are not too far different from what we see.
Dry in the desert.
It's pretty dry, exactly, and we are learning there in this that's called an analog field test, where you're trying to test something that's analogous to how you do it on the moon, and there we're learning how to use the data real time to make decisions about where to make additional measurements, where to prospect to best characterize the distribution of water.
When you say prospect, like we like the gold rush miners,
Exactly.
prospecting.
And, and if you think about how those gold mine, they were trying to find the gold, and they don't find anything. They go to another place and they try again, and they go to another place. Found the gold, and that's where we'll set up shop for the.
But instead of gold, it's still water.
It's water, and the rovers are going to go first and scope it out for us before we get there.
Right? Well, it's exactly as you saw earlier with the surveyor imagery with Apollo in the background. Yeah, the robotic precursors, they're called, go there to survey it, to understand it, and then you bring in the more valuable assets following the robotic surveys. Yeah.
We have a little animation showing what a
So we've studied this a lot here at NASA Ames. We built synthetic lunar terrains and rock yard tests. So over the past really 4 years, we've been studying this heavily, along with partnering with a lot of other NASA centers. And this just shows what a prospecting rover would look like as it drove up to a permanently shadowed crater.
So it'll have that light?
It'll have a light. We've got to look in there somehow. This particular design uses cameras for navigation, so you need to bring light. There's other variant that could use LiDAR, lasers that you wouldn't need the light.
And rovers are all part of this evolution of exploring new worlds. You start with your flyby, then you have your orbiter, then you land, like the surveyors.
Right.
And then you bring the rovers.
And you get the mobility.
You get mobility.
That's key.
And you get to explore.
Yeah, step by step building up
Exactly.
mobility, right?
Yeah.
Awesome.
Cool.
Wow. That's just about all the time we have, sadly, but this has been awesome. Thank you for your stories and expertise.
Well, the future is very bright for lunar exploration.
It is.
We still don't know much about the moon, even though we've been studying it, and we're always surprised by what we find. And we seem asking a lot more questions than we asked before.
Yeah.
As it should be, right?
That's the beauty of science and exploration. There's always more. And the amazing thing is if you look at how we think about the moon now with the water cycle. We talk about a water cycle on the moon. Now.
No one ever said that.
Now you know.
Now there's a water
used to
cycle.
say this is not your grandparents' moon. This is not my father's moon. This is, and I know in another 10 years we're going to be looking back and going, wow, we didn't know that.
We didn't know that.
Yeah.
So much to discover.
More treasures.
Yeah, well, thank you for joining us, both of you. It's been great having you here.
Thanks for having us. It's fun.
So this has been NASA in Silicon Valley Live, a conversational talk show out of NASA Ames Research Center with the various scientists, engineers, and researchers, and all-around cool people at NASA, where we talk about the nerdy NASA news you need to know about. If you like that, you can find us on Twitch, YouTube, and Facebook, and we're also on NASA TV. And if you didn't catch us live, we'll be on video on demand after the show is over. You can also catch the audio version on podcast services. So a huge thanks again to our guests, Tony and Kimberly. We'll be back on October 25th when we have a NASA-themed Halloween costume contest and cosplay contest. So until then, we'll see you next time. Bye.
The historic launch of our Artemis I flight test, a power walk outside the space station, and the beginnings of a new star. A few of the stories to tell you about this week at NASA.
And here we go.
On November 16th, NASA's Space Launch System rocket and Orion spacecraft lit up the night sky at the Kennedy Space Center to mark the start of our historic Artemis I flight test.
And liftoff of Artemis I. We rise together, back to the moon and beyond.
The planned 25.5-day mission calls for the uncrewed Orion to go about 40,000 miles beyond the moon before returning to Earth. The mission will also test all systems before flying astronauts on future Artemis missions. On November 15th, NASA astronauts Josh Cassada and Frank Rubio conducted a spacewalk to prepare the International Space Station for some new solar arrays that could help the station generate about 30% more power. This new Webb Space Telescope image shows once hidden features of a protostar within an hourglass-shaped cloud of gas and dust. The image is providing insight into the beginnings of a new star. NASA's quiet supersonic X-59 now has the engine that will power it after assembly of the experimental aircraft is complete. The engine will propel the X-59 to speeds up to Mach 1.4 and altitudes up to 55,000 feet. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
There are milestones in human progress that mark recorded history. In my judgment, this nation's orbital pioneering in space is of such historic stature, representing as it does a vast advancement that will profoundly influence the progress of all mankind. It signals also a call for alertness to our national opportunities and responsibilities. It requires physical and moral stamina to equal the stresses of these times and a willingness to meet the dangers and the challenges of the future. John Glenn, throughout his life, has eloquently portrayed these great qualities and is an inspiration to all Americans. This film, in paying tribute to John Glenn, also pays tribute to the best in American life.
Concord, Ohio wasn't on many maps until February 20th, 1962. It came to fame in a single day with an American adventure that history will call the John Glenn story. Fashioned in the American image, this pleasant little city typifies a nation's ideal way of life. A man might make a good life here in the circle of family and friends. And a boy might let his imagination soar. He might explore the wonders of the wide world all about him, life's simple mysteries, with bright discovery daily opening doors to knowledge. He can look away to distant places, to exciting adventures, hidden only by the horizon and the future. Like this boy, like boys everywhere, young John Glenn dreamed of the future as he looked to faraway new frontiers. Why, he might even learn to fly. This town and these people, they knew John Glenn as a schoolboy, as a teenager, and as a neighbor. Like Mayor Taylor, they followed his career as he blazed a trail across the high sky.
I watched John Glenn grow up from a freckled-faced, red-headed lad into the man you all know today. John's youth and his life today are an example for all Americans to follow.
New Concord High. Like these youngsters, John attended school here. His principal and teacher was Harford Steele.
He was an excellent student, and he graduated with honors from our high school. I taught Johnny and hundreds of others that our democracy is a priceless heritage, and that we should preserve, protect, and if at all possible, make some contributions to it. He has made a significant contribution in his mission in space.
And this fine new school in New Concord, it's the John Glenn High School, with its first graduating class receiving diplomas. Young John helped his father about this shop when he wasn't in school, or acting as lifeguard in the summer at High Y Camp or at college. John went on to college at Muskingum, right in New Concord. The high regard of the college is expressed by its president, Dr. Glenn McConaughey.
John's conquest of space has captured the hearts and the imagination of all Americans. So have his superb qualities of leadership, moral and physical strength, and emotional stability.
John found time for athletics, winning 4 high school letters. Muskingum coach Ed Sherman recalls John Glenn's athletic record.
John played football right here on this field. He was captain of his high school team and played center for the college. He has proven the value of teamwork both as an athlete and later as an astronaut. Just like these boys, John took an active part in our physical fitness program. He proved that a good mind and a good body always go together.
Campus discussions are inspired by the first orbital flight of an American.
I think that John Glenn, by his flight, has given us an opportunity to see that, well, we have a chance to do something for our nation, too. Maybe I'll even go somewhere sometime.
We have the same opportunities that he had. Glenn proved by his flight that there are still many frontiers to be explored and conquered.
And that just shows how very vital our education is if our future is to be go.
Glenn always had a strong spiritual side, as Dr. Charles Moorhead recalls.
John Glenn attended Sunday school in the services at this church when he was a boy like Randy Bradley here.
Let's attend services for a moment at John Glenn's church. John and Annie were married at this church by Dr. Henry Evans.
They made a most handsome couple. John in his Marine uniform, Annie a beautiful, happy bride. They both recognized the importance of the spiritual things of life as well as the mental and physical.
The trial is also great for those who wait, as recalled by Annie's parents, Homer and Margaret Castor.
Johnny's orbital flight was a real test of courage for Annie, too.
She was a very brave girl.
Annie had complete faith in the space program, just as she had confidence in everything Johnny set out to do.
This house was home for John Glenn. John Glenn Sr. and Mrs. Clara Glenn are gratefully proud of their son's accomplishments.
John was fully prepared for his orbital flight, as were the other astronauts and the entire team.
In a way, John has been preparing all his life for his venture into space. As a small boy, his idea of a holiday was a visit to the airport. And when he grew up, it was no surprise to us when he decided to learn to fly.
Flight commanded young John's major interest. He had to learn to fly. World War II interrupted college. He received his first flying lessons from pilot Harry Clever.
This is John's flight record with my comment after his first flight, which was eager to learn, relaxed, alert, and good coordination. He certainly has retained these flight qualities right into outer space.
Training at Pensacola and Corpus Christi. Many aviators have won their wings here. Like these cadets, John went on to Corpus Christi, Texas to learn about airplanes and navigation, with time also for physical conditioning and sports, and for religious inspiration. Like these naval aviators, to win his wings. training prepared Lieutenant John Glenn for wartime action in the South Pacific. Flying 59 missions in Corsairs like these, he joined in blasting enemy targets. Until there was peace, and Glenn returned to Corpus Christi as advanced flying instructor until Korea. Major John Glenn came back to combat to fly 90 missions to shoot down 3 MiGs. Following Korea, John Glenn came home to flight test the supersonic F-8U Crusader, to flash across the nation, California to New York, setting a supersonic speed record of 3 hours and 23 minutes. With experimental thrusts toward speed and altitude, the limitations of time and distance were being brushed aside as experimental planes like the X-15 launched from its Air Force mothership rocket to record-breaking altitudes and speeds. Unmanned experimental flights and orbits pressed onward until it was time for man to orbit, until the word was go. Chosen from many Americans who answered the president's call, these astronauts dedicated themselves to study, training, and physical conditioning. With Alan Shepard learning about weightlessness as it will be encountered in outer space, and Gus Grissom becoming acquainted with the stress of greatly increased gravity, as Wally Schirra masters manual spacecraft control. Three years of engineering skill and scientific experimentation have gone into this historic Atlas launching. Its component parts have come from countless sources, devised and fabricated by many thousands of technicians in hundreds of United States cities. And this, the motive power, carefully raised to position on its gantry. This, the Atlas, with power to develop 360,000 pounds of thrust, with capability to swiftly lift the spacecraft and its passenger as high as 160 miles, to inject the spacecraft into orbit at 17,500 miles an hour. And now the word is go, as the spacecraft is lifted into its position atop the Atlas. This spacecraft, 6 feet across at its widest heat shield end, 10 feet tall, built to withstand heat shield temperatures of 3,000 degrees Fahrenheit as the wind rushes by at more than 15,000 miles an hour. As the astronaut prepares for space flight, for adventure into outer space. Mercury control waits and watches, with the Atlas standing ready to throb into life. Ready. Friendship 7 is ready. And so is John Glenn. At the gantry, elevators lift Glenn to the 11th level, the spacecraft level. Glenn takes his place in Friendship 7, looking towards the unknown. Ready. Mercury Atlas is ready, and so is the astronaut. The countdown is underway at Cape Canaveral, as all the world holds its breath, and all the world is witness.
vibration area coming up here now. We're smoothing out some now, getting out of the vibration area.
Roger, reading you loud and clear. Flight path looks good. Pitch 25, stand by for...
Roger, Pico. Back to 1 1/4, the tower fired. Could not see the tower go. I saw the smoke go by the window.
Yeah, we confirm staging on PM.
Roger. 1.5 Gs.
Friendship 7, Bermuda has you.
Roger, Bermuda, stand by. This is Friendship 7. Pico. Posigrades fired, okay. Roger, 0G, and I feel fine. Capsule is turning around. Oh, that view is tremendous.
Roger, turnaround has started.
Roger, capsule turning around, and I could see the booster during turnaround just a couple of 100 yards behind me. It was beautiful.
The word is go, and John Glenn is go, and with him go all of mankind's dreams of someday touching the unattainable stars. Under a tropic sun, the tracking ship Rosenot waits and follows his course as he flashes towards the coast of Africa. To John Glenn belongs an awesome panorama of the Earth below. Beyond human sight, Friendship 7 makes a slow boat out of the sun as the spacecraft girdles the Earth every 90 minutes. Like a shooting star at 5 miles a second, 17,500 miles an hour, John Glenn streaks away from today into the night of tomorrow, racing towards the dawn of yesterday. As Glenn sights the lights of Perth and Rockingham, as he flashes over Australia, across the Pacific, to contact waiting ground stations at Guaymas, Mexico. And California waits as Friendship 7 streaks home to the land of its origin. An unseen comet lining across the United States in 8 lightning minutes of flight. Completing 3 history-making circuits of the globe, John Glenn fires retro rockets to slow the spacecraft, to direct it back to Earth.
5, 4, 3, 2, 1, fire.
Roger. Retros are firing.
Good, indeed.
Are they ever? It feels like I'm going back toward Hawaii.
Then the first ominous note, the first warning of possible disaster. A chilling signal flashes an indication that the capsule's heat shield may be loose. The astronaut might perish like an earthbound meteor in 3,000 degrees of re-entry heat without the heat shield. Strapped over it, the retro pack might hold it in place. Cape Canaveral makes the decision.
We are recommending that you leave the retro package on through the entire re-entry.
As all the world listens and stands still and helplessly hopes, Cape Control shows the way. Using fly-by-wire control for re-entry, John Glenn rides his craft through the vastness of space towards the curving globe beneath. As science in its amazing exactness selects the Caribbean from all the oceans of the Earth to receive Friendship 7 as it blazes into the Earth's atmosphere.
This is Friendship 7, a real fireball outside.
A fireball. The fiberglass surface of the heat shield is starting to oblate, to melt and vaporize as a glowing electrically charged wake streams back to block off communication as the Earth's atmosphere slows the capsule's descent.
Friendship 7. Stroke is out. Coming down on 10, snorkels are open. Main chute is on green. Chute is out in reef condition at 10,800 feet and beautiful chute. Chute looks good. Rate of descent has gone to about 4.2 feet per second. The chute looks very good. Hello, Mercury Recovery. This is Friendship 7. Do you receive? Friendship 7, this is Steeland. Be advised, I have you visually. Roger. What is your estimate on recovery time? Over. like it's okay, over. Capsule looks good from here, over.
Home to Earth comes the Voyager. Transported now to the aircraft carrier Randolph. In 4 hours and 56 minutes, John Glenn has streaked through 3 days and 3 nights and over 81,000 miles. Never a journey so far. Never a traveler so welcomed by the world. So brief a journey in time. So far the way. So long the hours for those who wait. As Annie Glenn has waited. As all the world has waited. To salute the Glens with Vice President Lyndon Johnson. As the President of the United States arrives at Cape Canaveral to be greeted with John and Annie Glenn by the cheers of thrilled lines of proud Americans. In ceremonies at Mercury Control Center, President John F. Kennedy presents the NASA Distinguished Service Medal to astronaut John Glenn. As Annie and Lynn and David Glenn proudly share applause with the other astronauts and with the world. As John's parents learn firsthand about Friendship 7. As does Marine Corps Commandant General David M. Shoup and the President of the United States. And this rainy day in Washington is a happy day as the President and the astronaut arrive to drive through rain-washed, crowd-flooded streets to the White House for a reception as John and Annie Glenn with Vice President Lyndon Johnson greet distinguished guests, including astronaut Alan Shepard. Godspeed, John Glenn. Godspeed into the future. Into even greater accomplishment. Into the hearts of all Americans. Welcome to Washington. Welcome back to this planet. From the nation's capital to the towers of Manhattan to the ticker tape parade of New York, cheering crowds roar a mighty welcome, shared by all Americans, by free people everywhere. And across the land, the scene is the same, and the heart is the same, as John Glenn comes home to New Concord, Ohio. At the Capitol, there's an introduction by the Speaker of the House, the Honorable John McCormick.
Members of the Congress, it is a privilege, and I deem it a high honor, to present to you a brave and courageous American, a hero in World War II and in the Korean conflict, who recently, in a most notable manner, added glory and prestige to our country, the first United States astronaut to have achieved orbital flight, Lieutenant Colonel John Herschel Glenn, United States Marine Corps. Colonel Glenn.
Mr. Speaker, Mr. President, members of the Congress, I am only too aware of the tremendous honor that's being shown us at this joint meeting of the Congress today. This has been a great experience for all of us on the program and for all Americans, I guess, too. And I'm certainly glad to see that pride in our country and its accomplishments are not a thing of the past. I know I still get a real hard-to-define feeling down inside when the flag goes by, and I know all of you do too. The launch itself was conducted openly and with the news media representatives from around the world in attendance. This is certainly in sharp contrast with similar programs conducted elsewhere in the world and elevates the peaceful intent of our program. Today, I know that I seem to be standing alone on this great platform, just as I seem to be alone in the cockpit of the Friendship 7 spacecraft. But I'm not. There were with me then and with me now thousands of Americans and many hundreds of citizens of many countries around the world who contributed to this truly international undertaking voluntarily and in a spirit of cooperation and understanding. We are all proud to have been privileged to be part of this effort, to represent our country as we have. As our knowledge of this universe in which we live increases, may God grant us the wisdom and guidance to use it wisely. Thank you.
And crown thy good with brotherhood, from sea to shining sea. In the pattern of all our free American traditions, John Glenn's trailblazing venture into space has shown the way for human progress, for brotherhood around the world. His story speaks of people and places and industry, of the greatness that is America. It sings of the unselfish aims of a nation striving constantly for peace, directing all its power and persuasion toward the preservation of freedom. In its majesty and magnificence, this is the land. In all their historic greatness, these are the people. And the John Glenn story is their story. It throbs with a nation's restless energy. It soars with the adventurous spirit of Americans everywhere. Across this vast spread land, in all its towns and cities, on all its far-flung farms and ranches, deep in its reaches of forest and plains, of winding roads and rivers, majestic mountains and lakes and sea-lashed shores, people turned their eyes and hearts toward the high sky, sending their hopes and prayers, riding through space, with John Glenn in Friendship 7, as all the world watched and hoped, with mankind's wonderment about the universe, finding an approach at last toward fulfillment. In the John Glenn story.
Oh, it's a privilege. Please call me Tom.
Tom, Victor.
I call you Victor.
And the privilege is mine. It's so amazing to meet you, even virtually.
It's great to meet you. Congratulations on your extraordinary career thus far. It's really what you've accomplished. I have great admiration for.
Well, thank you. And, you know, the movie Top Gun obviously had a huge impact on me. And as much as I want to throw Top Gun quotes at you, I won't. I'm sure you get a lot of that. So thank you, because you had a part in that.
Boy, it's an honor for me. And I can't wait for you to see the next one, Top Gun Maverick. I can't wait.
Oh, I can't wait either.
It's an honor.
I'm ready.
Oh, man. I'm ready to show it to you. I can't wait, man.
Awesome.
So listen,
I'm
I have a few
excited.
questions for you, if you don't mind.
Yes, sir. Let's do it, Tom.
Because obviously you've flown, I guess, 40 aircraft over as a test pilot, many different aircrafts. The F-18 is a naval aviator test pilot. Now, flying the Dragon, SpaceX Dragon. How does that compare to that? And what do you think for yourself? What was the most exhilarating aspect?
Awesome. The Dragon is a touchscreen. The displays are also where the controls are. And so that's quite different than flying an aircraft with a stick and a throttle. And so when I first saw it, I will be honest with you, I was like, I don't know, guys, I need my inceptors. I need something to move around. But as I learned more about what the vehicle does and what its purpose was, the touchscreen actually was wonderful. It worked great. And the most exhilarating part of it all was riding the Falcon 9 rocket. It is such a high-performing liquid rocket. It's smooth, but it really leapt off the pad. And we got to the 100-kilometer point, and we were all smiles. It was just so amazing. You can really feel the accelerations and decelerations. And then once we got onto the upper stage, the second stage, and you just start building speed, I've pulled Gs before in fighter aircraft, but to be able to pull Gs for almost 10 minutes straight was just power like I've never experienced, not even launching or landing on a carrier.
Really? I've been fortunate. I've got some launches and I landed on carriers on the Roosevelt, and that kind of G's, that kind of force coming off there is pretty incredible. What was it like with the Dragon? What did it feel like with the Falcon 9? I mean, how many G's were you pulling? And I know you're laying down.
Yes.
What was that like?
And so it is different. In the fighter, the G's go from your head to your toe, and that's why we practice these specific maneuvers to keep blood flow to your brain so you stay conscious and you don't gray out or black out. The G on a rocket launch goes into your chest, and so you naturally can sustain more G's in that direction, and the G is actually lower. So the maximum G we saw was about 4.5. But what's different in a fighter, you'll experience. I pulled 9 G's in a fighter aircraft, but that was only for seconds. And, I've sustained 3 to 4 G's for maybe a minute or a minute and a half in a dogfight, in a turning fight. But on the Falcon, except for staging and throttle down, you are accelerating the entire way for about 9 minutes. It was about 8 minutes and 50 or so seconds. I mean, and you're accelerating the entire way because you wind up 200 kilometers above the Earth going 17,000 miles per hour. It's an amazing amount of power. And so we actually were above 3.5 G's for about 3 minutes. That's amazing.
That's incredible. That is absolutely incredible. I know I've been fortunate, different aircraft that I've flown is those G's, and feeling them momentarily 9.5 is what I pulled actually in the F-14, the first Top Gun, from we got 9.5, and we, on the new one, we were pulling a lot of different G's, but to sustain that, I was wondering, because I always wanted to know what that rocket and feeling that acceleration, where you could actually feel that acceleration the whole time. Do you felt that the whole time, acceleration on the body?
The whole time. Yes, coming off the pad initially, it feels like a very high speed elevator. The first move off the pad, you're not going very fast, and you're actually not accelerating very fast, but it just continues to pick up. I mean, the entire time you're moving. And at about 1 minute into the flight, you're in the region of maximum dynamic pressure, what you hear people say, max Q. And that's where you're in the thickest part of the air down low, but you're also going really fast. And that could actually crumple the rocket and the spacecraft. So they actually slow down. They throttle the rocket down. And you feel that. You feel yourself. It's like tapping the brakes. And then really what stands out is the throttle up. Then they go back to full power. And when they do that, it felt like lighting the afterburner in an F-18. I wish I would have been able to feel what it was like in an F-14, because I hear it is quite impressive. But I never got to fly that aircraft. But you definitely feel it the entire way up. And then the first stage shuts down after about 2.5 minutes. And then we ride the second stage all the way into orbit. And that one starts just at about 1 G. And so, again, it's a very light push, but then you push for another 6 minutes. And about half of that time, you're above 3 G's. And so your chest is very heavy, and you have to focus on breathing, inhale, and then the exhale kind of works itself out, because of the pressure. It is quite amazing. It was a truly incredible experience.
I did not know you had to work on that inhale. That's incredible. That is extraordinary. Yeah. Now, being a NASA astronaut, I mean, you require, constantly pushing the boundaries. And what is the most physically demanding task, both kind of before and after, like during the space flight?
Yeah. Yeah, great question. You know, and I think it's interesting to think about this. It depends on the time horizon you're looking at. So, in the moment, the short term, short duration, most challenging part of what we do, I think, is training for and executing spacewalks. It's 6 to 7 hours of working and doing these very important things on the outside of the space station in the extreme environment of the vacuum of space, high temperatures, low temperatures, no air. And so that life support is critical, but it's also very physically demanding. You're moving around a suit that can weigh with your body in as much as 1,000 pounds, and you very rarely use your legs. It's like running 2 marathons, but on your hands the whole time. Your hands and fingers are very sore when you're done with this. And so that's the most physically challenging thing. And training for it on the ground, you're still in an extreme environment. In the neutral buoyancy lab, our 2 million gallon, 40-foot deep pool where we train for spacewalks. And so it's still also physically demanding, even underwater. But when I think about the duration of a career and maybe something that has a huge impact on your lifespan, I think all the traveling and training and the stresses of this job, if you don't have healthy ways to manage that stress, it can actually affect your sleep. And then we also have to become comfortable sleeping in space, which is an extreme environment. We do lots of outdoor training, and you have to be able to sleep outdoors as well. So I think just looking at the way that these things, all of these stresses manifest in your life, you also have to have healthy coping strategies for the travel, all the different time zones we go in, and all the different stressors that come with the work. And then obviously then getting to space and being able to fall asleep and get the important rest that you need to accomplish your workday. That's one I think is a very physically demanding aspect of training and living in space.
Okay, Victor, there's two things. One, I from what I understand, and I've been fortunate enough to actually be fitted for a suit years ago, and just feeling the weight on Earth versus, I guess, in zero G. But what people I don't think understand also is what I understand, this, is how hard it is opening and closing your hand, let alone like talk about moving the arms and moving the hands, the stiffness of the suit because of the pressure differential, just moving your hands, the dexterity of that. Could you, and then the next thing I want to ask you about is sleep, but could you tell us a little bit about that, please?
So yes, in that spacesuit, right, you're in the vacuum of space. The pressure there is zero, absolute zero. So you need something to keep your fluids in your blood and to help you stay conscious and comfortable. It keeps your temperature in a comfortable range as well. And so the suit is pressurized to 4.2 pressure pounds per square inch, 4.2 psi. And so the entire suit is at 4.2 psi, and it wants to sit about like this. And so anytime you move, you're moving against 4 pounds per square inch. And so we have certain bearings. If you rotate your arm like this, you're rotating a bearing. So that's roughly, you have to overcome a little friction. But if you move like this, you're pushing against the suit, the stiff fabric, the many layers that can maintain that pressure in the vacuum of space. And so when you close your hand, a great example, sometimes you'll hear people say it's like squeezing a tennis ball. But squeezing a tennis ball, if you squeeze it, it's work to squeeze it, but then to let it go, opening it pushes against you and helps you out. What I like to say is moving around in the suit is like putting your hand in rice. If you open your hand very wide, you're pushing against that rice. If you close your hand, you're closing it against that rice. And there are some athletes that use buckets of rice to train their grip strength. And I think that's a little bit more of an accurate comparison.
Did you do things like that to increase your grip strength? Because even dropping your arms, you talk about pushing it up, but dropping your arms and moving in that way. I mean, what did you do anything physically to increase your strength with that?
Absolutely. We have a great team of, we call them astronaut strength conditioning and rehabilitation specialists, ACERS for short. And our ACERS craft very specific workouts to help us. Like I said, training for spacewalks is also physically rigorous. And so they actually develop those workouts to help us be safe in the neutral buoyancy lab where we train, and obviously to also help benefit while we're in space. And we do very specific exercises for our grip as well as for our shoulders. Those are two of the areas that you really tax when you're doing spacewalk training or an actual walk in space. And the other thing is they give us suggestions on how to work out. For example, when I do my shoulder exercises, I originally started using dumbbells, and I would hold the handle and do my shoulder exercising, rotating, and doing things to exercise my rotator cuff and all those small muscles around your shoulders. What I started doing, because of the suggestion of my strength trainer specialist, was to use plates, the same weight, but in a plate, and I would pinch them so that during my exercise, I was also increasing the challenge on my grip and therefore getting a better grip workout while I was exercising my shoulders. Things like that are the kinds of things that our astronaut strength conditioning and rehabilitation specialists help us with.
Did you feel, that's incredible, did you feel the longer you were up there, because I want to just a little question on this also, is that you were there for so long, and the time when you got there and when you did the spacewalk, what level of depreciation of bone and muscle density is there? And did you feel a difference? Like, what happens to your metabolism with the Krebs cycle, with the mitochondria? Did that affect the spacewalk? Could you tell the difference in terms of your strength on the ground that you built up? Is there a diminishing effect the longer that you're in space, is my question ultimately? And how did that affect your metabolism, your BMR, with calories and nutrition? Did you have to think about that?
Oh, wow. There's a lot packed in there. And so that is definitely something we work hard to mitigate. You're going to lose bone and muscle, muscle due to potential atrophy from I weigh 200 pounds and I'm not carrying that 200 pounds. It's like taking off a 200-pound backpack when I get to weightlessness. And so I'm losing that effort every day. And so I have to make it up in my workout. And also your bone density, we have this condition called osteopenia. It's like space-induced osteoporosis, the enzymes that encourage bone growth. Our bones are constantly being reclaimed or eaten and then reconstituted. And in space, for some reason, the process that eats the bone or takes away bone continues, but the part that reforms new bone slows down. And so we try to mitigate that with our strength training and also with medication. And so the effects there it can have a huge effect on you. But the workouts that we do are one of the biggest mitigators. And so I actually started working out before the mission. And then when I got into space, I continued to work out. We get 2.5 hours every day to do exercise, strength training, cardiovascular training, and then also time to clean up and get ready for the workday. And that was extremely valuable. Now, when I first got to space, my body is going through so many changes. I lost about 2 kilograms and I was only eating about 2,200 calories. It took me about 45 days to get used to the environment, to come up with some strategies for me to eat like I did on the ground, like keeping snacks in my pocket at all time. And when I started snacking and eating in space more like I did on the ground, I got up to 3,300 or so calories, 3,200 calories a day. And I was also working out very hard. So overall, in space, I actually felt stronger than I did on the ground. I was able to work out really hard. In fact, I told myself before flight, I wanted to make sure I didn't get hurt. I didn't want to hurt my back or my shoulders because I wanted to always be ready for the spacewalks and all of the other work on the space station. And so I felt like I could have lifted even heavier and ran harder on the treadmill, but I just didn't want to hurt myself. But the strength training and cardio training are excellent in space.
Incredible. So that when you were doing your spacewalks, you didn't feel like you had lost strength?
Not at all. By the time we went out the door, I felt stronger, actually. And over my mission, I did lose a little bit of bone mass. I lost about 2% of my bone mass, and they say I'll have that recovered in about a year. Muscle mass, I actually gained. So I told you I lost 2 kilograms in the first 2 months. At the end of the mission, though, after the complete 6 months, I was 4 kilograms heavier. So I gained back that 2 and then put 4 more on. So I came back with more muscle mass than I launched with.
That's incredible. And so you feel like, did that had a reflection on your metabolism overall? Increase your metabolism?
I think so. I think it may have been an increase. I took a test when I got back to check our VO2 max. And so the VO2 max is a great example of how we're doing metabolically. And so I was in family. I was close to when I launched. And that's what our ACERs also are focused on, helping us reacclimate to Earth and getting us back to what we were like pre-flight. And so my strength numbers, my bench press, squat, my VO2 max, we do that by getting on a cycle and going until we fail, pretty much. and they measure our gases that we're inspiring and expiring, and that tells them our VO2 max. And my number was a point or two different than what I was pre-flight. And so I would say overall, I was able to maintain my metabolism, and that's pretty impressive considering all of the things that your body is experiencing.
Flight, to understand what that was, did that change at all? That number?
We don't normally do that for crew members. I think that's something you can get if you want to. But I was involved in an experiment called myotones, which is studying not just muscle mass, but the quality of your muscle. And it's really looking at this device to see if we can use a very simple external device without having to do like biopsies to determine muscle tissue quality. And so that experiment actually takes 10 measurements all around your body over the course of the mission. And you also have pre-flight and post-flight numbers to compare it to. And so I actually was able to get those kinds of measurements. But like I said, before flight, in flight, and after.
Yeah, because you were there for 6 months. What was the difference? Because when we talk about going to the moon, we talk about going to Mars. Was there a large difference as time went on with those numbers?
It actually, I lost a little bit in the beginning and gained muscle over time. And so I think I lost a little bit in the beginning and gained muscle over time. And so I think my overall proportion stayed the same. And being able to maintain what you start with on Earth is great. That's a great standard. But that's very much because of the amazing exercise equipment. And if you've never seen it, the ARED, it's the Advanced Resistive Exercise Device, one of the most important technologies on the space station, in my opinion. It allows us to do all kinds of exercises, bench press, squats, curls. And that machine, though, takes up almost half a module. The space for the machine plus the range of motion for the body that you put on it. And so when we go to the moon, we won't be able to do that kind of workout in transit. And that's very important to understand. We're going to have something smaller like a rower, like an erg that you would see on Earth. But when we get to the moon or to lunar orbit, we're going to need some type of a habitation module where we can get exercise, because that bone and muscle health. And also it was a part of what I enjoyed most during the day. So it's also a part of mental well-being, but it's very important to our physical well-being.
Right. So you feel like when we go to Mars, obviously on the planet, there'll be a whole module for it, but on the way to Mars, you'll feel like we'll need a separate thing? I mean, because when you see 2001, we're talking about, do we put a force of gravity? When you talk about what the difference of gravity on Mars versus the moon and on the way there, I know there's been a lot of talk and evaluation as to what is 0.6 gravity on the human body. We don't really know until we get there, and it's done for an extended period of time. So you feel like, will we have a separate module just on the way to Mars? That's what it'll have.
I think so, because with current propulsion technology, right, we need to get better propulsion technology, because if we can shorten the duration of the trip, right now it's going to be 6 to 9 months. If we can shorten that trip, that means less radiation exposure and less time for your body to degrade in weightlessness. But, trying to create artificial gravity by spinning one module, that creates guidance and navigation and control challenges due to gyroscopic effects. So it would actually be it would be really complicated to do that. So you're going to need to exercise. You're going to need basic exercise. And something I try to encourage our scientists and our exercise specialists to think about is, ARED is a fantastic machine, a wonderful contraption. But we also need to remember basic things. I wrestled in college and in high school. And so I think of the most amazing exercise device there is in history is another human body. That's my opinion. But, also doing calisthenics or just basic isometrics where you push on a structure. And so maybe just getting in the corner of a module and putting your hands and feet against different sides and pushing statically against something, or using another crewmate and you both kind of do squat presses where you're pushing against each other. Those are the kinds of things we need to think about and find ways to incorporate so that we not only have the ability to do strength training, but we also have a backup in case a machine breaks. Because again, on the way to Mars, you're not going to be able to stop off at the hardware store and get parts to fix it. And so we need to have a way to back up those exercise devices, because it's such a vital a part of physical and mental well-being.
That's a very good point. That is a very good point. It's interesting because we know what zero G is, have a great idea, I think, of how the body behaves under zero G over extended period of time. and on our way, and when we get to Mars, how's the body at 0.6, at the, those different forces of gravity? How will the body develop? Are these things that you guys spoke of, and as you were preparing for this flight, did you evaluate any of that?
No, we didn't, but I do know that people are thinking about that, the scientific and the medical communities. I know that the crew that just returned, so we just launched a crew to space. You were there for that launch.
I was there.
Well, just prior to that, we returned crew 2, the crew that flew to space station after us in a Dragon. And when they got back, they actually had an activity just after launch, just after landing, just within hours after they landed. We had activities where they had to climb up a contraption and move some large masses. That simulates being able to throw out the emergency equipment into the water if you landed in the water in your capsule after being deconditioned from being in space for an extended period. The moon missions are Apollo astronauts. They say that the worst period of deconditioning was after a 14 to 21 day mission in space, somewhere in that third week of being in space. And that's what our moon missions will be like. And so coming back, deconditioned, landing in the water, and maybe landing off target, we need to know that folks can operate and function in that environment. So we think about it, but for missions to the station, we're going to be in weightlessness for an extended period and then have to recondition to 1G. And so our focus is on 1G, but I do think we need to find ways in that construct to evaluate things like this, coming back from the moon or being on Mars, because it's amazing. I was just writing an email to the folks that just went up there to Crew 3. And one of the things I encouraged them to do was to learn the lessons that space is going to teach you. I used the example of the Apollo astronauts, the hop they would do on the surface of the moon. They weren't taught that. They innovated. They figured it out because the environment, it made sense. In that, 1/6 of Earth's gravity, they realized it was easier to hop than to try to ambulate, to try to walk like you do on Earth. And so sometimes you just need to be in that environment. Like you said, you need to experience 0.6G to understand how your body wants to operate. And, the physical sense, there's a little genius to the body, and we need to be good at listening to what our bodies tell us.
Boy, that's incredible. I know that hop, I was always thinking, you don't want to fall. Do you know what I mean? Because you can't damage that suit at all. One thing I just want to ask, like, when you did your spacewalk, what happens if you have an itch on your nose, your ear? What are you you're thinking, like, you start sweating, you're going, oh my gosh, are you one of these? I mean, you can't get your arm out to just scratch that. Did you ever have have an itch somewhere where you're like, man, I can't wait till this is over. I'm gonna have a good scratch here.
Well, yes, I think as soon as you put the suit on and you're going to pressurize it, that's when everything does start to feel. You start, oh, is that an itch coming? But so we actually have a device inside the suit that is for Valsalva. Just like in airplanes, as you start to descend and you feel the pressure build up in your ears, we have a small foam block that we can push our nostrils against so that we can force air and then expand air into our eardrums to Valsalva. But that device is used mostly, I think I can speak for the entire astronaut corps to say its number one use is to rest your chin on so that you can rest. And then number 2 is to scratch your face. And so there is a way to scratch certain itches, depending on if it's in this area, you can scratch it. But when you take the suit off, yeah.
When you take the suit off, I didn't mean to cut you off. I beg your pardon.
Yeah, you're definitely looking for some relief when you take it off. There's all kind of little itches or aches and pains, and so interestingly, I also had a situation that I almost couldn't do anything about. So we have this anti-fog on the inside. We dab just a few drops, wipe it on the entire visor, and try to get rid of it. And there have been other instances of astronauts experiencing that anti-fog getting in their eyes. And I don't believe it was the anti-fog I applied to the suit. There's actually an investigation going on to find out where it may have come from. Maybe it was sucked up into the life support system and then pushed back out later. But I had 3 spacewalks where I did 4 total. And on 3 of those spacewalks, I had something in my eye that caused a burning sensation. And one of those happened while I was working on a pretty important piece of hardware. And so I actually had to just stop and hold still. And I just kept blinking, waiting for my eye to water. And it did. And again, my body took care of itself. And so I just kept blinking, and my eye watering, over time, it dissolved, whatever that was. But it took time. it wasn't just a small thing that the liquid pushed out. It had to dissolve something, and I could feel the burning sensation slowly decrease. And then I was able to see and finish my activity. But it felt like I was standing there out on the mast on the very end of the space station. I was on the solar array on the space station, and I was way out there waiting for this burning sensation to go away. A pretty interesting experience.
I think that's an understatement, isn't it? Pretty interesting. It was like, okay, wow, that's intense. That is intense. Congratulations. I'm glad you made it through. Did they figure out what that vapor
solution? But there's other things in the suit. You know, we wear a harness that can take biometric measurements. It sees our heart rate, and they can figure out respiration and understand how quickly we're going through our oxygen and CO2 scrubbing systems. And so those we have those leads stuck to our body with an adhesive, but underneath that there is they call it the electrode gel. And it's this gel that we put on before we stick them to our chest and cover them with tape. Well, that gel could have potentially leaked out as well. And I've never put it in my eye to see what it feels like, but I imagine it wouldn't feel very good. So there are a few things within that sealed volume of the spacesuit that are culprits. And I'm actually waiting to get the results of the investigation because I'd love to understand that more. At this time, I'm not sure what it was. It definitely wasn't water, and it wasn't my own sweat. I've had my own sweat in my eyes plenty of times at the gym, and it didn't feel like that. It wasn't my own sweat. I've had my own sweat in my eyes plenty of times at the gym, and it didn't feel like that.
Wow. Incredible. Well, congratulations with that. Now, let me ask you something. You had you gave advice to to the ISS and the group that just took off. What did you get any good advice as you were a trainee that you applied that you when you were up there you thought, you know what, I'm glad they told me this?
Oh, so often before flight, even in flight, and even now after flight. Some of the things that really resonated before flight. So in training, someone said to me, actually several people said it. One of the primary things, our job to integrate all the training and to know how it's different than doing it in weightlessness. And that is just so true. You get there and everything has this one theme, weightlessness. And being in orbit can change everything. The way you brush your teeth, go to the bathroom, eat, drink, and then of course, maintenance, science, and spacewalks. Waking up and going to sleep and waking up again in weightlessness, it's just something that you can't train for on Earth. And so you have to learn how to live like that and work like that once you get there. It's on the job training. Another piece of advice before my first spacewalk was to keep your world small. That was such a great thing to think about on your first spacewalk, just going out there and focusing on one thing at a time, because it's really easy to just want to look at the Earth, but that could be overwhelming. And since I had never done it, I didn't want to take a chance at, putting myself in a situation where, the anxiety or the nerves took over. I think of myself as a steely-eyed fighter pilot, but I've never been 260 miles above the surface of the Earth and been able to look down and see nothing under my feet. So I didn't want to take any chances, and I slowly small. And then I would say my favorite piece of advice was something someone wrote on the space station. We have a sheet of paper taped to our exercise device, that ARID I was telling you about. And it actually has an acronym, PLEASE, written down the side, which tells you what to do to turn off the machine when you're done exercising. But someone wrote a picture of that, and I sent it to my family, and I sent it to my friends, and I also suggested the crew that just got up there. I didn't tell them what it was. I just told them, go look at the machine and the piece of paper. I meditated on that daily. Every time I passed by it, I read it. And even sometimes hourly, I would tell myself that, because it's really easy to focus on a spacewalk. But you know what? When I was repairing the toilet, I thought it was just as important as going out into the vacuum of space. Nothing is more important than what you're doing right now, because everything that we did in space was so vital.
I think that's words of wisdom for life down here on Earth too. It's an incredible thing. When you talk about space, when you were talking about your purview or your view expanding, my question is, have you skydived before? Have you gone through skydiving and scuba diving? Did you do a lot of that prior to this?
You know, I've never been skydiving, and I would love to. Our cosmonaut colleagues do that as a part of their training. And so maybe I need to go evaluate the cosmonaut training program so that I can do some skydiving. But I did learn to scuba dive. I actually learned to do it in Guam while I was on a Navy deployment there, and before I became an astronaut. And then as a part of this job, when we train in the neutral buoyancy lab with the full pressure suit on, that's considered full pressure suit diving. But sometimes we'll do a practice run without all the other divers and the cameras, by ourselves, just with our buddy, and we'll go down in scuba the run before, so we can see where things are, how we're going to attack the problem with the tools, and how we'll get out and back from the work site as a team. And so we do lots of scuba diving in this job, and that is flying and diving are two of the parts of this job that I love the most.
It's a great job. I'm going to take you skydiving. I'll take you skydiving. I'll teach you.
Yes, please.
I'll take you that. We'll do that. We'll do that. Okay, I'll call you after. I'll figure it out. That'll be fun. That'd be really fun.
Awesome.
Yeah. So when you're up there, was on the spacewalk, was that the most astonishing view that you had? Was that the moment for you? You know, everyone talks about inside, obviously the cupola. We've seen those shots and film of that, but outside and looking back at Earth, or, you know, what other things? What was? Did you see anything else, or just share a little bit of that with us, if you don't mind, please?
Wow, absolutely. You know, because you're inside the space station, the windows there, you know, it is a great view out of the cupola, and we have other windows. But when you're outside on a spacewalk, that visor wraps around you so that you actually have peripheral view. And so when you can see the Earth, there's nothing besides that visor from orbit, and it is truly breathtaking. That's why it's important to keep your world small. If you walk out and the first thing you do is just stare at the Earth, I mean, you may be stuck in that for several minutes, and you've got work to do in those first few minutes. And it's also important to keep your heart rate low in the first few minutes. I can tell you more about that later. But that view is very special. It is extremely special. But I think the view that impacted me the most was the first time I saw the Earth from orbit. And that was after launch. We got to orbit safely, and now we had 27 hours before we were going to catch up to the space station and dock. And first of all, the orientation of the Earth, I thought, you know, that I was just used to seeing the Earth like you see it in this picture, you know, horizon there and the Earth down. And it was like sideways, and I felt like I was underneath the Earth, and I'm looking out, and I was just amazed at the view, how much detail that I could see, but then how much of that detail. And so I just grabbed my iPad and I started recording a video. And it wasn't that I wanted to share the imagery with people. I wanted to capture the feeling that I was just awestruck. And I wanted to share that with people, how it impacted me. And so that really was a powerful moment. And you know, I think the overview effect, if you've heard about that, seeing the world without borders, without labels, it just as it is, seeing the magnitude and the majesty, but also the fragility of the planet, has an effect on most people who get the privilege of flying. I've been back for a little over 6 months now. I realized that it's important and it is amazing and it's a privilege to see it. But one of the reasons that it's so powerful and it's so impactful is because of what you build up over your life here on Earth. Seeing an entire ocean, entire body of water from space is amazing. I could see the entire ocean, but it makes you still want to stand on the beach and walk in the surf. And so it's the fact that it connects to your experience on Earth. Being in space just accelerates that and makes you appreciate the planet and appreciate the life that it supports, the fragility of Earth and the preciousness of human life. And so it's one of my missions now to try and remind people of that right here on Earth, that we already start the overview process. The overview effect starts right here in 1G on the surface of the Earth with each other.
That's spectacular. That's really amazing. Thank you. Gave me new images of what that experience must be like. That's amazing. Absolutely amazing.
Thank you. It's powerful. The Earth is amazing.
That's amazing. It really is. Well, you know, when you came back, did anything, you know, in terms of, I know we talked about physically calories and nutrition, was the food, did you pick your food ahead of time? I mean, these are like, did you know, what physically, what were you going through? What was it like eating the food there? Did it change? Was it different eating it in 0G than it was on Earth? Did you change your calorie count? Did you change your diet specifically for it? Did you get advice the same on Earth as it is in the space station?
Yes. A topic that I really care a lot about. I love to eat. And, the food on space MREs like we have in the military to reducing the salt, increasing variety and options that we all share. And then we are able to pick about 10 to 20% of our food. And they can even go depending on the packaging and if it will last long enough, because your food is up there for a year or years before you get there. And so it has to have safe packaging and be shelf stable for long enough. And so I had lots of advice. We had nutritionists in a food science lab where we can taste the foods. And the value in that is what the entire menu is like, but it also gives you a chance to start thinking about ways to combine and recombine the food to add even more variety to it. Or using one, like I used a lot of tomato basil soup as sauce for other things, putting it on the chicken breast, for example. It just added a little bit of flavor. And so those kinds of things are very important. I also got lots of advice from my crewmates. And in fact, I don't think I took that advice well enough. When they told me, really think about the stuff you can choose, I picked one or two things, and I was really happy that they had these dry fruit strips that I really like. And so I was like, okay, great. And I've got my coffee. And I wish I would have spent more time and gone to the store and dedicated some time to looking at different things and seeing, hey, I could get that. I could have a few of these, and adding even more variety, just maximizing variety and taste and textures. Because of 6 months of eating the same things, it is really easy for it to become boring and routine. And so we constantly are finding ways to adapt and adapt. Utensils. You don't use utensils like you do on Earth. You don't scoop out your soup. Honestly, you cut the corner off, not all the way off, because now you've created a little piece of the soup out and you kind of suck it out of the bag. We do a lot of eating like kids do, like toddlers drink and they eat their food out of pouches. We do that often. And so you don't need utensils as much as you do on Earth. Drinking water, you need to be careful because the water floats, or all of your drinks float. And so you have to really be intentional. When I first got there, I was trying to have a drink, and I was talking to one of my crewmates, and I briefly choked, and I was like, whoa, okay, no more talking and drinking. I'm just going to focus on one at a time because this is a new challenge. And so it definitely changes the mode in which you do those things. And there's just things that you have to learn in space, and you have to learn the lessons space has to teach you. Hot things can be really interesting. On Earth, when something is warm, like your coffee in a mug, the warm air is less dense, and so it wafts up and you can smell it, and you don't have that sense of smell in space. You have fluid shift, which makes you feel a little more congested, and you also don't have gravity to create that differential that makes warm things rise. So your foods don't smell as strong, and it affects the taste. And so we use a lot of condiments to make things taste better. But also, you don't have the sensation of heat when you pull a hot package out of the food warmer. It's not, if you're not holding it, you don't sense the heat like you do on a hot plate of food with the warm air rising up to you. So you really need to check the temperatures of your food. When I ate my first bag of warm tomato basil soup, my first one in space was cold. The first time I heated it up, I cut the package open. I made a big cut, too big, and so soup was starting to come up out of it, and I put my face down by it, and the soup, as soon as it touches your lip, surface tension and capillary action take over, and it wants to spread over your face. And so that's how I found out that it was really myself. And so that's not something you think about on Earth, because you can sense the heat, and then you can get a spoon out and sort of slurp it and check it. And in space, you just have to really be careful about your hot foods. And that's just true about everything. Space requires...
Yeah, the temperature inside the ISS. I mean, obviously, it's closely monitored. How did that feel for you? The atmosphere inside, the air, the smell of the air being different. Was there any other things in terms of the electronics of the ISS? And did you feel a difference being in that space? I mean, just the EMFs, or you talk about radiation. Those things in terms of being surrounded by so many electrical devices and the radiation. Could you tell and feel a different environment with that on your body?
Yes, it's interesting. The entire space station is controlled to about 22 degrees Celsius, 72 degrees Fahrenheit, and so it feels very much like your home, except for all the air moves in space station because of a fan. You know, there's no natural circulation. And so because of that, if you stand in one place too long and you talk as much as I'm speaking right now, you build up a bubble of CO2, you know, and that definitely has effects. One of the most common effects of high levels of CO2 are headaches. And so you can also experience air hunger, kind of like the sensation just before you yawn. And so those are things that happen that are kind of compartmentalized depending on where you are and the activity that you're doing. If you're working in one area for a long time, you may want to have an extra fan. Bring a fan with you to blow air out as you're sitting there breathing and adding CO2. But the temperature was very comfortable. But depending on where you're working, sometimes I would go up on the overhead, and we generally would have inlets on the deck, and the outlets for the air conditioning were overhead. So when I would be working up on the ceiling, on the overhead, I would be really close to the airflow. And you know, with this haircut, it was easy to lose a lot of heat. And so when I was working on the overhead, I would grab a hat or a knit cap, and I would wear that. And even sometimes I would put on my hoodie just because if my head was losing heat, it made my entire body feel cold. And so it really was local specific. The entire space station was very comfortable. But depending on where you worked, you may want to be in your short sleeves or you may need a jacket to stay warm. And then the smell. It's very interesting. When you first get to space station is when you notice the smell the strongest because you kind of get saturated and you get used to it after. But it was an interesting combination. And again, it's also local. When you go into the module that has the lifting, the strength training equipment, that's also where the bathroom is. So that's the most odoriferous module. That one smells like a locker room. And so the overall space station, it smells very much like a factory. It has this machine, sterile, metallic quality to it. And it very much smells like a workspace. You know, when you walk into a hospital, you sense that, yeah, this smells like a hospital. It's got this antiseptic, germ-free quality. And so we work really hard to keep it clean. And it just, you know, between all the machines and the fans on the computers and the power boxes on all the hardware, there's this hum and there's a smell, there's a visual, and there's a sound of the space station that kind of, it's almost like a living thing. And it's neat because if that ever changes, you know the ground did something or something broke. And all of us would hear something shut down and go, uh-oh, something just changed, and the ground would call you. So you get used to all of those qualities of the space station. It's almost like another crew member up there that you get used to the personality and the characteristics of ISS.
So it's always that electronic sound throughout. That never
All
stops.
day. All the fans and electronics, there's a whir, a hum that just is continuous. And if that ever stops and it gets quiet would actually make us all go, uh-oh, what's wrong? Did we just lose power? What happened? Because there's always some machine running 24 hours a day, 365, 366 in a leap year. It's always moving.
So you feel the vibration when you're sleeping. Was it hard to make yourself fall asleep and stay on a schedule with that? Did you feel the vibration? You're hearing the noise. Did you have earplugs?
We have earplugs. We also have, you know, sleep medication if you need it. If you wake up and you have trouble going back to sleep, we have lots of options there. I think I was very fortunate. I did not use earplugs because I wanted to be able to hear if the ground called us or if there was an alarm in the middle of the night. And we actually had several, about a half a dozen times where we were woken up in the middle of the night. Once it was 3 times in one night, and you don't ever want to discount them. You want to take each one seriously. And so I wanted to hear, but I didn't have trouble falling asleep. And a part of that is because we sleep in crew quarters, all of us except our commander. We increased the normal size of the space station crew from 6 to 7. And so we didn't yet have an extra room. We call them crew quarters, and they're padded on the inside. So when you shut the door, it has its own fan. And other than that fan and your computer or music, if you have music playing, you don't hear much when you're in your crew quarters. And that's great. You can hop in your sleeping bag. And for me, I didn't like to tie my sleeping bag down very tight. Some people tried to recreate the sensation of sleeping on Earth, and they would put a pillow and try to squeeze themselves up against the wall and create the sense of pressure that would mimic laying down. And I just tried to embrace the floating. And so I tied my sleeping bag at the waist in 2 places, and the rest of it, I let it float. And so I just slept out in the middle of the module, and my body was in whatever its normal relaxed position was. And I slept great. I slept great on the space station, and I actually needed less sleep. I average 7 hours a night, and on Earth, I try to get 8 hours a night. But at 7 hours, my eyes would fly open, and I would be rested and ready to start the day. That was very interesting.
And did you feel a difference in your sleep on Earth from when you came back? Did it, when the gravity, did it change any? Did you feel any physical effects?
Coming back to Earth, I had to get used to lying down again, and then especially sitting up. My midsection was so weak compared to before I flew, that when I would sit up, it was a concerted effort, and then just getting stable and then standing up. That was an interesting thing, to lie down all night and then sit up. But overall, the sleep quality, I think my sleep, once I was asleep, was very much in space like it was on Earth. And that was nice, because sleep is very important to me. Just food, sleep, flying, those are things that I very much love.
I appreciate that. By the way, speaking of flying, I'm talking to you now from England at a great airfield, Duxford. At the it's a restoration center. This is a Spitfire behind me right here. So these guys, I don't know if you can see it on the scene.
I can, and it's beautiful. Mark told me where you are, and that is, I'm jealous. This is a cool view, but there's no airplane behind me. That's awesome.
That's a very cool view. This airplane, that's what we're doing. We're flying a bunch of stuff, and we're releasing Top Gun, and we're working on missions. So being a fighter pilot, I know.
I'm jealous.
I know, man. I'll be flying this thing when I get off here. We're gonna go fly some Spitfires. We got Mustang here too.
Oh, very cool. Wow. Well,
if you're ever in, where are you now? Are you in California? Where are you?
I'm in Houston. South
nice.
Houston.
Well, you tell me, you ever get to California, I have a P-51 out there. You can go have a flight if you want it. You just tell me.
Okay,
I've got a P-51. So we go skydiving and little P-51 stuff.
Oh, okay. You had me at hello. Yes, sign me up. I flew 35 airplanes in test pilot school, and 2 that I never got to fly that I always wanted to fly were the F-14 Tomcat and the P-51 Mustang. The test pilot school wasn't able to get a P-51 that year. Sometimes they do, but we didn't get one. So that's on my bucket list.
Well, good, man. I'm gonna get that bucket list for you. We got some good pilots taking you through it.
Awesome. Thank you.
We'll get that done. Now, let me see.
Awesome.
We talked through your science experiments. I'm going to kind of look at the questions that we had written down. I want to make sure, we went through the sleep, okay? And, one of the things that I'd like to discuss also is the team dynamic, the preparation for that. I mean, being in such close quarters, obviously you went through the Air Force Academy, the preparation, understanding the military teamwork and the flow of communication. Was that different with the ISS? Was that different with this team? Is there, did you find in terms of everyone under stress or personal conflict and how to resolve those conflicts when you're there, so that did you guys have to have, that kind of training in terms of dealing with those situations when they arise?
Absolutely. And I think it's time well spent. And that's what I would say is it takes intention and it takes time. You have to put in work for self-care, learning how to take care of yourself, and understanding what gets you going and what makes you stop. And then also team care, how you fit into the role of a high-performing, high-functioning team that has to work in this isolated, confined, and extreme environment. And so I think the effort that we take on the ground in training is really to give you a tool bag, a set of tools that science, you really don't know what it's like initially and emotionally, and you don't know how that's going to affect you until you get there. For example, on Earth, I would consider myself an extrovert's extrovert, a type A extrovert. I love being with people and communicating and telling stories and hearing stories, and that gives me energy. Moment, I wanted to be by myself because you're constantly engaged with things and people and getting instruction and giving a report, and there's so much extrovertism that I needed to just be by myself to recharge, and that surprised me. And so it's important to have your tools so that in space, in the moment, you can actually contrive something. You can use the basic building blocks that we study on Earth to create whatever it is that you need when you're in the environment. I like to tell this story about, working together. It's important to train with folks on the ground so that you know them. And Mike Hopkins, our Dragon commander, he and I were together for 3 years prior to this mission. And over time, we developed a couple of things. We would say, hey, if we're ever talking to the ground and you hear me say something and you think I'm being too pushy, we both played college football. And so we came up with this saying, take a knee, take a knee. And that was if we thought we were being too pushy with the ground or with each other, take a knee. And we agreed, we had trust in each other, that if we ever heard that, it was an automatic stop, and then we would do whatever our other crewmates suggested. And we also came up with another saying over time that was, if we were doing something that, maybe seemed tedious and we could tell that might be a frustrating item for each other, that we would say over the intercom, or if we were floating by, we would just say, this is the mission. We're both military officers also, and sometimes you just got to follow orders and salute and carry on. And so we would say to each other, this is the mission. And over time, because the TV show The Mandalorian was out, and they say, we loved watching The Mandalorian. We took a Baby Yoda to space as our zero-G indicator. And so we started saying, this is the way. And we actually used that one all the time. And it was mostly in humor. It was mostly a joke. We'd hear something come up from the ground and we'd be in a completely different module, and one of us would yell, this is the way, and everybody would laugh because we understood what was going on. But the other one, the taking a knee, we never had to use that in space. But I think it's important that we had to come up with that. And I think because we put the time to develop a system to hold each other accountable, but also to build trust to use that system of accountability, I think that's one of the reasons that we never actually had to use it. And that's a good thing. I think that's a win. And so overall, though, it's important to intentionally take time to do self-care and team care training, and then to have the time dedicated to doing it. And sometimes we're going to have to do it in real time. We're getting ready to launch a private mission to the space station. And as we do that, we're going to have less time to be together on the ground. And I think it's important for us to consider time on the space station that we dedicate solely to building team camaraderie and morale, so that those folks can be effective as they can be in space, because it requires intentionality and it requires time.
That makes total sense. That makes total sense. That's excellent. Now, also just going on the journey, 6.5 hours to the space station. What was that like? That's 6.5 hours of you. At a certain point, you've had the G, you've had the ride into space, and now you're just, did you feel like, okay, I'm ready to get there? Let's, what was going through your mind beforehand? Were you thinking?
So, it can be as short as about 6.5 hours, or it can be much longer. Sometimes it can take up to 2 days. In the Soyuz, it used to take 48 hours. They can get there as short as 6 hours. And so our rendezvous actually was in between. It was 27 hours. And so after the exhilarating ride of about 9 minutes into orbit, we had over a day before we could dock with the space station. And, that's when I had my first view of Earth from space. I had my first meal, macadamia nuts and cold tomato soup. And the first time I got to use the bathroom in space. And so it was fun. But after trying to go to sleep, that's when I realized, okay, I'm ready to be on the space station, because I slept in my chair so I could see the displays. If something happened, I would be right there at my workstation, ready to, get back to piloting Crew Dragon resilience. And so you actually don't sleep well in the spacecraft. You really nap. It's really snacking instead of having a meal, and napping instead of getting a good night's sleep. And so after just taking naps over a day, when I got to the space station, I knew that was where I was going to get my first good sleep. So I was ready.
Well, that's really interesting. Now, Victor, I could talk to you I could stay here all day. And we have a worldwide audience of extreme medics listening to you, you know, and they want to use the medical training as a powerful force for good, pushing the boundaries of extreme medicine. Now, is there anything that you would like to say to them now? Give them a message before we close?
Absolutely. Yes, thank you. And thank you for this opportunity. That's what I want to say is thank you, thank you, thank you. You know, as our planet is still, you know, experiencing this pandemic, I think all of us have healthcare workers and professionals and janitorial workers and professionals on our minds all the time. And then you add something to that, you know, in church, it really impacted me when I was young and I heard someone say to me, you have to meet people where they are. You have to take your gifts to people. You have to meet people where they are. And I think of the extreme medical community as not only this great group of folks that provide healthcare, but you do it in isolated, confined, extreme, and hostile sometimes environments. You take this life-saving care and meet people where they are. And so I just want to express my gratitude and my awe that you are able to do things that most people can't even do so that you can provide healthcare to people in these extreme circumstances. Thank you. I think what you do is commendable and I look up to you and I really want to be like you. I hope to engage in more training for extreme environments. And, you know, they say imitation is the greatest form of flattery. And I desire to be very much like you all. Thank you for your service.
That was excellent. I agree with you, Victor. You are impressive, and what you've accomplished thus far is absolutely impressive, absolutely engaging, incredibly informative. And I'm grateful to be here, and I'm grateful also to all these people out there that are helping people, and just want to thank you. You're gonna get you that Tom if you want to.
Yes, sir. Yes, please. And it's been so amazing to talk to you. Oh, I'm ready to go. And thank you for this. It has been a treat. I showed up. I showed up here today, and you know I saw this on the calendar, and I read the papers and stuff. But I still asked my public affairs team, this awesome group of pros, and I said, "Hey guys, I just want to get this straight." So Tom Cruise is going to ask me questions today. Right? I just figured there was a typo somewhere. So this has truly been a treat. Tom, thank you so much for the time, and I hope you enjoy flying that Spitfire. That's going to be amazing.
Thank you, man. We'll get you to P-51. I enjoyed this immensely. Awesome. Incredibly informative. I just very grateful to have this opportunity. And thank you.
Same. Me too. Thank you.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe get into a ball, I'll do the same, I'm gonna face you this way so that I don't throw you into something you can't see. Now I'm gonna get into a ball behind Joe, and I'm gonna apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
Welcome to the International Space Station. I'm astronaut Joe Acaba. Today, we're going to talk about potential and kinetic energy. Let's get started. Kinetic energy is the energy an object has because of its motion. An object can store energy based on its position. This is called potential energy. On Earth, imagine dropping an object from a raised position. As an object's altitude above the Earth's surface increases, its gravitational potential energy also increases. The potential energy stored due to its position is now being converted to kinetic energy. We also observe this with elastic potential energy.
Okay, new term. Elastic potential energy occurs when objects are compressed and stretched, or generally deformed in any manner, creating potential energy. Think of this bungee or a spring. Okay, Joe, what's next?
We pull back on the band and create potential energy. When we release the potential energy, it is converted to kinetic energy. Here on the International Space Station, we are still under the influence of gravity, primarily due to our position with the Earth. So when I have this ball on this ramp, normally back on Earth, I release the ball and it rolls down the ramp due to a change in its potential energy that's being transferred to kinetic energy. But as you can see, it doesn't happen here. So it doesn't mean we don't have potential energy. It just means we're not converting it at this time to kinetic energy. And why is that? Gravity is pulling us down, but we're moving super fast. And so what it is we're bending around the Earth in this perpetual falling motion. Thanks for joining me on board the International Space Station. We're sending it back to Earth so you can try your own experiment. See you next time.
Hello, and welcome to the International Space Station. My name is Scott Tingle. Here on the space station, we live in a microgravity environment, which makes eating here a very unique experience. To stay healthy, we have to maintain a nutritious diet, just like we would back on Earth. Let's go take a look at some of our food and drinks and check out our meal preparation area. During long-duration spaceflight, we have to make sure that we receive enough energy, proteins, and vitamins. Our food lab back on Earth makes sure we get plenty of each as they carefully prepare, test, and package everything. We combine all of this excellent nutrition with exercise to ensure our bodies stay healthy and strong while we're here. We eat 3 square meals a day, just like we do on Earth, and maybe throw in a snack or two. One of my most favorite foods to eat are natural raisins. Here on Space Station, we have to keep our calories up if we want to get all our work done. And the carbohydrates in these raisins really help. And they're kind of fun to eat, too. And how do we stay hydrated in microgravity? With these special pouches. They're filled with water, and we use a straw that has a one-way valve that prevents water from floating out of the pouch while we're not drinking from it. Here's a liquid drink. This is a tropical punch for today. I love drinking fluids on station. Here on station, we have a pretty cool food preparation area. We have a place to get fresh water for us to drink or to put in our rehydratable foods. And we also have an oven to put food in. We pick out some of our favorite foods. Chicken fajita for me. Put it in the oven, close the door, and turn it on. In about 15 minutes, I'm gonna have a warm meal. Thanks for exploring a little nutrition with me. I'm gonna send you back to Earth so you can create your very own astronaut menus. See you again soon. Hello, my name is Scott Tingle, and I'm living and working on board the International Space Station. You know, I love my views from the cupola. It's our orbiting altitude of around 400 kilometers or 250 miles above the Earth's surface that gives us these unique perspectives. Let's explore how our ISS orbits work. Come on. First, I should explain, orbits are elliptical or oval in shape, with some being almost circular. Planets, comets, and moons have elliptical orbits. Spacecraft orbiting Earth, like the space station, are placed into a nearly circular orbit to keep a consistent altitude as they travel around the planet. Let's take a look at the Earth. It has a radius of 6,378 kilometers, and the station orbits about 400 kilometers above the surface at 8 kilometers per second. That's 17,500 miles per hour. See if you can use these values to calculate how far and how long we travel in one orbit around the Earth. All of this information and more activities related to orbits are available in the accompanying lesson plan at nasa.gov/STEM on station.
Answers coming in.
4, 3, 2, 1.
The answers to the questions, by the way, are approximately 42,600 kilometers and 90 minutes. And due to our altitude on orbit, we have our very unique and awesome view of the Earth. Thanks for exploring with me today. I'm going to send you back to Earth now so you can start your challenge on orbits. See you again soon.
Welcome to the International Space Station. I'm NASA astronaut Ricky Arnold. Our view from the ISS of Earth is absolutely magnificent, but we quickly realized we really should call it Planet Ocean. We are mostly a water planet. Water occurs here in all three phases, solid, liquid, and gas. And the presence of water on other planets and moons within our own solar system has us wondering, is there life there too? Well, why is water so special? One reason is called surface tension. So what is surface tension? Let's have a look. Surface tension is a property of liquids in which molecules of one substance are more attracted to each other than to molecules of another substance. Water is unique in that it has a high surface tension compared to other liquids. This is due to its polar property. The positive hydrogen ends and the negative oxygen ends create a strong bond. As they say, opposites attract. So the hydrogen end of the water tends to stick to the oxygen end in a nearby water molecule. At water's surface, its molecules are only attracted to the water molecules below and to the sides of them, as there is only air above these molecules. So the surface molecules of a body of water are pulled down, creating a more stable, stronger environment. That is why certain animals, like the water strider, can actually walk on the surface of water. Here on the International Space Station, the microgravity environment makes it easy to show how well water uses surface tension to stick together. We even rely on surface tension to help us wash our hair, those of us that have a lot. Thanks for coming along today and learning a little bit about surface tension. Want to learn more about the unique properties of water and do your own experiments? Try out the activity related to this video at the STEMonstrations website. See you next time.
Hi, I'm NASA astronaut Drew Foystel. Welcome to the International Space Station. On our station, our water recovery system is vital to our mission and our survival. Want to know why and how we recycle and filter our water? Let's go. We use water recovery and filtration because it is expensive to launch resupply missions, and the weight of the water is a problem as well. Think about the weight of a single bucket of water. Can you imagine the weight of water for a month's supply for 6 people on the International Space Station? What about the water for a year or more when we leave low Earth orbit for deeper space missions? That's a lot of water, and bringing it with us is not very efficient. Our concentration process includes our urine, moisture we exhale, and sweat, along with the water we use to bathe and shave. It works like this. When we use the bathroom, urine is collected and pumped to a distillation assembly. The assembly spins, pulling the urine to its walls. The urine is heated to evaporate water from the waste, and then condensed in the outer chamber to form distillate. Next, the water is pumped to a tank where it is joined with the water recovered from cabin air created by crew sweat and respiration. Down the line from there, odors and any other contaminants are removed with heat. Then iodine is added for microbial control. Our water is checked often to ensure it meets water quality requirements. It is also monitored closely for bacteria, pollutants, and proper pH. The pH scale ranges from 0 to 14 and is a tool used by scientists to measure the strength of an acid or base. Our water is required to be in the 6.0 to 8.5 range. The end result of the entire process is clean drinking water that we get to enjoy every day. The recycled water on the space station is sterile. There's no odor or bad taste. You've seen that water recycling is critical for long-duration missions, such as here on the space station, and will be for future trips to the Moon or Mars. Be sure to check out the activity connected to this video so you can learn more about water filtration. Thanks for learning with me, and I'll see you next time.
Hey there, my name is Joe Acaba, and I'm living and working on the International Space Station as part of Expedition 53. One of the best parts about living on the space station is being able to float. Just like you walk from place to place throughout your day, we float from place to place throughout our day. However, we have learned that the same thing that allows us to float, microgravity, is hard on our bodies over time. Our muscles and bones are made of millions of tiny units called cells, and these cells can have problems in microgravity. Up here on the station, bones and muscles no longer have to support the weight of our bodies, so they get weaker. Astronauts could develop something called muscle atrophy, where our muscles become weak from lack of use. Each bone in your body is made of cells too. A healthy bone has more density than an unhealthy bone. Weakened bones can lead to a disease called osteoporosis. Fortunately, our scientists at NASA have figured out one way to keep astronauts healthy and strong. It's called exercise. Let's take a look at how astronauts exercise in space. This machine here is the Advanced Resistive Exercise Device, or we call it ARED. It simulates free weight exercises in normal gravity to work all of the major muscle groups. ARED's primary goal is to maintain our muscle strength and mass so that we have less of a recovery period when we land back on Earth. All right, so there's looking at lifting. But what about a little cardio? We have a treadmill for that. Let's check it out. Staying physically active helps both astronauts in space and humans on the ground to stay healthy. And it prevents muscle atrophy and osteoporosis. Now you can try the activity connected to this video to learn more about muscle and bone cells. I'm Joe Acaba, and I hope you enjoyed learning about exercise on the International Space Station. We'll see you next time.
Hello, everyone. I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live on... Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Surely good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small, something you might have at home, a little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and we'll pull it back. Let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
On December 17, 1903, two brothers from Dayton, Ohio, would alter human history forever. On that day, Wilbur and Orville Wright flew their wooden and canvas machine off the sandy dunes in Kitty Hawk, North Carolina, becoming the first to flight. Heavy experimentations with gliders, like advancements in engine technologies, controls, and aerodynamics, provided a pathway for heavier-than-air crafts, like the Wright brothers' Flyer. By the 1930s, airships, which have dominated the long-distance flight, were replaced by flying boats and other rudimentary aircraft. By the 1930s and 40s, development of aircraft for war effort greatly accelerated infusion of new technologies into civilian general aviation. This stream of innovation led to the start of the jet age, which would revolutionize both general and military aviation. Later in the 20th century, even more advanced technologies like digital electronics would bring about fly-by-wire, digital engine controls, GPS, and these advancements even changed the way we go about designing aircrafts. This century has been marked by transitioning to large-scale pilotless drones, and for the first time ever, inherently unstable aircrafts, such as highly integrated flying wings, have become a possibility. And with all these advancements in the past 112 years, we're still only scratching the surface of capability and performance, but we're paying a heavy price for lagging innovation. Who here has traveled by air in the past 6 months? Were you surprised by the cost and time of your trip? Today we find ourselves at the doorstep of yet another revolutionary advancement in aviation history: electric or hybrid electric aircrafts. As part of its portfolio to improve fuel efficiency, emissions, and noise levels in commercial transport aircrafts. EAP uses electric motors to drive some or all of the engines on an aircraft. The energy source for the system can be electric, hybrid, or turboelectric. NASA is working across a range of markets, from urban air mobility to subsonic transport. Each market has differences in vehicle size, range, and speeds. Our strategy at NASA is to work with our industry partners to enable technology development, demonstrate these technologies in flight, and transfer the knowledge to commercial sector for future products and markets. One such emerging market is urban air mobility, developed through NASA's revolutionary vertical lift technology project. Urban air mobility, or UAM, is a conceptual market that would enable passenger-carrying air transportation in and around metropolitan areas. Think of flying Ubers. These vehicles could use all-electric or hybrid-electric propulsion systems capable of vertical takeoff and landing. The overarching goal of NASA's work in this space is to develop and validate tools, technologies, and concepts to overcome key challenges for vertical lift vehicles. A critical challenge for UAM market growth is public's acceptance that these vehicles can be as safe as commercial air travel or automotive transportation. However, the most immediate impact from NASA's work for the flying public is the reduction in cost through fuel burn improvements and lower airfare prices. To put that in context, let's look at some numbers. The overall global fleet of large commercial aircrafts totaled over 25,000 in 2017 and is expected to grow to 37,000 aircraft by 2027. Out of the 25,000 aircraft today, nearly 60% of those are narrow-body aircraft, small regional aircrafts, both jet and turboprops. Saving just 10% in fuel consumption across this fleet would yield more than 5 billion gallons of fuel savings per year, and is forecasted to save approximately 10 billion gallons by 2040. We also have to take into account the reduction into CO2 emissions. So how do we get there? The leading concept that NASA is currently investigating for partially turboelectric configuration is single-aisle turboelectric with IVE boundary layer propulsor known as Stark-Able. This configuration is being developed assuming entry into service by 2035. It consists of 2 underwing turbofans with generators extracted to rear fuselage boundary layer ingesting fan. One of the main sources of drag on an aircraft is a layer of slow-moving air that builds up along the fuselage and wings, known as boundary layer. Boundary layer creates extra drag, and we believe we can improve aircraft performance by embedding engines into the airframe and having those engines consume boundary layer air. By ingesting boundary layer, the drag is significantly decreased, which leads to an overall improvement in aircraft efficiency. Results indicate that this turboelectric concept an emission fuel burn reduction of 12% comparing to other aircraft designs. Several years ago, NASA has developed an advanced and highly integrated concept known as N3X, which explored fuel savings by combining a blended wing body design with fully turboelectric and fully distributed propulsion system based on superconducting electric machines and power distribution. The fuel benefits of this configuration is very significant, estimated at nearly 70% reduction comparing to conventional aircrafts such as Boeing 777. This concept has the best benefits so far studied. However, it requires the most aggressive technology and infrastructure development. And last but not least, NASA is building its first ever all-electric X-plane, X-57 Maxwell. This design will demonstrate an effective interaction between a wing, the engine propellers, and a flight mission flight path, while simultaneously solving a number of challenging technical issues for electrified propulsion in crew-rated aircrafts. While electric motors are more efficient than fuel-burning engines, they produce a significant amount of heat during operation, requiring an integrated thermal management system to be incorporated into the design. Now, a common method of solving such heat-related problems is to employ an embedded heat sink or a large metal heat sink or water cooling system. But this can cause a dramatic increase in weight, thus reducing the benefit gained by electric conversion. One such research effort to control the heat generated by these systems was performed late last year by my team, where we developed a 98% efficient 13 kilowatt power system for X-57 high-lift propulsors, weighing only 2 pounds and completely air-cooled. This system was fully qualified across various facilities at NASA Glenn in 10 short months. And within the next 2 years, our system will be flying on X-57 flights, proving that it is possible to have a lightweight air-cooled solution for aircrafts. In order to qualify the components in this electrified era in aviation, NASA needed to develop capability to test and verify them before in-flight testing. So we converted our hypersonic test facility in Plumbrook Station in Sandusky to NASA Electrified Aircraft Testbed, NEAT. Currently, this state-of-the-art facility is being used to test full-scale megawatt powertrains with an eye towards incorporating component technologies into an overall system. The facility can support single-aisle aircraft geometries with proper cable lengths and electromagnetic interference mitigation. It can supply power for up to 24 megawatts, thermal management system for up to 2 megawatts, and it even contains an altitude chamber that can simulate up to 120,000 feet. All electric aircraft concepts that we've seen so far rely heavily on advancements of components such as advanced motors, power converters, and material science, to name a few. X-57 work is an example of much larger research portfolio within the field of power systems led by NASA Glenn. Over the past 20 years, Glenn has pioneered designs of various high power, density, and high efficient motors for space, aeronautics, medical, and terrestrial applications. All our work has always pushed the boundaries of what's possible, and our newest motor work is no different. NASA Glenn has a small in-house team that is developing a 1.4 megawatt motor with a performance goal of 16 kilowatts per kilogram and efficiency greater than 98%. The motor contains a self-cooled superconducting rotor, which has never been done before, allowing the motor to achieve exceptional specific power and efficiencies without inheriting external cooling weight penalty commonly attributed to superconducting machines. Integrated rotor superconductor, spinning at 6,800 RPM, 4 times higher than the state-of-the-art, and weighing only 80 kilograms. This motor revolutionizes the field of advanced motors and greatly increased number of aircraft concepts that can utilize hybrid architectures. All our electric motor work is all diverse in size, applications, and power levels. And it's beyond the world of aeronautics. Just 5 years ago, my team designed, built, and delivered a biconical motor to University of Indiana School of Medicine. This motor was designed to help catalyze advancements in the field of cardiovascular assist devices, such as pacemakers for kids who are born with a single heart ventricle. This motor is tiny in comparison to the ones on aircraft, just 2 inches tall, and is powered by a total of 5 watts, same power as USB ports on your computers. Currently, our design is being used to develop a clinical trial version, and hopefully a viable device will enter a market within a decade, saving an estimated 1,500 children per year. All great progress is accompanied with great difficulty and must be enterprised and overcome with answerable courage. In our efforts, we don't underestimate the power of vision and direction. These are irresistible forces able to transform what might appear to be unconquerable obstacles into traversable pathways and expanding opportunities. I am deeply humbled to have an opportunity to be part of this amazing journey, a journey that will surely.
Imagine if you were an alien who, was visiting the Earth for the first time from some other galaxy. Imagine only visiting the United States and never visiting any other part of the Earth's surface. That's essentially what we've done with the Apollo missions. Really been able to do wonderful and groundbreaking science with the samples, collected during the Apollo missions. But again, we visited only a very small part of the lunar surface.
The way that I think about it is it's the equivalent of landing on Earth and getting rocks from Kansas. It would give us insight into one particular location on the Earth, but not at all the diversity of what we see on the Earth, what we know is present on the Earth. That location, get different samples, will just enrich what we've already learned from our Apollo samples.
There's a lot left to be learned about the moon, and it starts with the South Pole.
Artemis astronauts will fulfill a different mission in a unique environment. While the Apollo astronauts who visited the moon's surface between 1969 and 1972 landed near the equator, Artemis astronauts will venture to the moon's South Pole region, frigid, rugged, and with unique light and darkness conditions that make it an ideal location for exploration. The South Pole region is also home to the rim of the moon's largest, oldest, and deepest crater, called South Pole Aitken. It takes up almost a quarter of the moon, and is so deep, it exposes portions of the moon's interior.
Yeah, the South Pole it's fascinating. There are some very unique types of rocks that are at the South Pole that will allow us to understand the entire history, not just of the moon, but potentially of the solar system.
Very early on in lunar history, we think that there was this increased period or very intense period of huge material hitting the surface of the moon, creating these really large craters or like giant holes, which we actually call basins. So getting a sample of impact melt from this basin would kind of help us bracket that early period of time.
The Moon's South Pole region has resources that are vital for long-term exploration. Because the Moon is barely tilted relative to the Sun hovers over the horizon at the South Pole. Imagine a flashlight turned on, laying on a table. That's how the Sun illuminates the South Pole. Light at the South Pole strikes at such a low angle, it brushes only areas of higher elevation, such as crater rims. These locations have sunlight for extended periods of time to harness for power. At the same time, the bottoms of some deep craters are shrouded in constant darkness. Scientists have measured the coldest temperatures in the solar system inside these craters, which have become known as perfect environments for preserving water for eons.
Over time, there's individual molecules of water and carbon dioxide and other gases that actually bounce around the surface of the moon. And when they get to one of these cold spots, they actually get stuck. So we call those places cold traps. And if you do that for millions and even billions of years, you can actually build up a pretty significant deposit of water and other ices.
From an exploration perspective, if we can understand just how much water there is and where it is and how to get it out of the regolith of the moon, we can turn it into really important things like drinking water for astronauts and even rocket fuel to take them back home. So really understanding these resources and how to use them is one of the objectives of the Artemis program, and it's what makes the South Pole of the moon so exciting.
We know the moon in incredible detail, thanks in large part to NASA's Lunar Reconnaissance Orbiter, or LRO. LRO has been circling the moon since 2009. It's the longest-lived spacecraft there. Through tens of thousands of orbits and data from 7 instruments, LRO has mapped the moon's temperature, geology, radiation environment, and is providing insight on how the moon is changing over time. LRO is led by Dr. Noah Petro, a planetary geologist at NASA's Goddard Space Flight Center.
LRO is this incredible mission. It was launched in 2009 as the opportunity to go back to the moon, to create this three-dimensional, high-resolution, high-definition atlas of the moon. Where are there safe landing sites for human and robotic explorers? So what LRO is doing is really giving us the tools, the material, the data we need to make those missions successful.
For many years, LRO's elliptical orbit was closest to the moon during the spacecraft's pass over the South Pole. So scientists have more information about the South Pole region than any other region of the moon.
We know that we can do more and build upon the legacy of Apollo, but to do that we needed a higher resolution data set. We wanted to know where the hazards were. We wanted to know where the geologic features were that we want to go explore, and so LRO has created that database. Incidentally, the LRO data volume is now over 1.3 petabytes. It's the largest volume of data that NASA has ever collected from any planetary body. It's remarkable. And what we've done now in support of Artemis, in support of other NASA missions to the moon, is we've created special maps. We share them with the public and we share them with the various engineers and scientists who are going to help enact and make Artemis a reality.
You know, this is basically a Google Maps of the moon, taken from pictures from the Lunar Reconnaissance Orbiter camera, and you can just zoom in and see a 5-meter boulder on the surface of the moon. That's just crazy. I could spend all day, and I have spent all day, sometimes just browsing around different parts of the moon, just looking at air rocks.
This wealth of information will make it easier to find ideal locations for a NASA base camp, and to quickly identify scientifically interesting areas to visit nearby.
So it's my real belief that we have an opportunity with Artemis to do something different than Apollo. We build on Apollo, we learn from Apollo, but we want to expand what Apollo was able to do and build this presence on the moon that is more than just 3 days, more than just 6 individual missions, but a much larger program that eventually will result in the ability to go onto Mars.
Mars is quite a bit longer away from our own planet than, of course, the moon is. It takes several months in some cases to get to Mars, and it's therefore going to be really critical when we have astronauts walking around on the surface of Mars to be able to stay there for longer periods of time. You've just spent 6 or so months to get there. You want to really be able to explore the surface around you, and having the ability to live off the land and know how to conduct exploration for longer periods of time is going to be critical for Martian exploration, and lessons learned for that sustainable type of exploration start right here at the moon.
So there's still so much for us to learn from going back to the moon from a scientific perspective. It's a no-brainer in my head. So with Mars in the horizon as our kind of end goal, this is an important step for us to take. And then also just kind of from a human aspect, we all have this kind of intrinsic desire to explore. I think it's in all of us and certainly in us as a society. And so I think setting our sights on something and accomplishing this goal together is really important just for international relations, for, just coming together as a humankind, the human spirit. I think that's a piece of what we're doing that we can't ignore as well.
I have 3 kids, aged 10, 6, and 2. I talk about space often with them. The great thing that my parents did for me was let me find my path. I also look at my daughter, and I think, okay, Amelia, she keeps saying she wants to be a firefighter, a construction worker, and an astronaut. And I said, well, Amelia, you can do all 3 and be an astronaut. Well, when you're an astronaut, you got to learn how to fight a fire in space. You got to learn how to build stuff. So you got to do all those things. What they'll become, I'm so excited to find out. But I have no idea what they're gonna end up gravitating towards.
So why is the moon my favorite body to study? I think growing up, you could always see it in the sky. You could see some beautiful stars and maybe Mars or Jupiter as like small little dots, but the moon is just there in all its glory. It's like our nearest and dearest neighbor, and you can even with the naked eye, you could start picking out features on the moon. I think that was really cool. This is thousands of miles away, and you can still kind of be a geologist from the ground if you want to, and I think that's really cool, and that's why I always wanted to study the moon. Just seeing people walk on the moon, on this foreign planetary body, looking at images like the one behind me here, I think that always blows my mind.
I will say with my 2-year-old, what I have noticed recently, and this is wonderful, is that when he sees the moon, we're out for a walk, we're driving around, or outside a window, we go, moon, moon. And it's just the fact that he can look up and see, go, oh, moon, moon. That makes me so happy.
Greenland, a massive ice-covered island in the northern Arctic, a land of pristine geology, and for some, the site of a hotly contested claim of the oldest signs of microbial life on Earth. Meet Dr. Abigail Allwood, astrobiologist at the NASA Jet Propulsion Laboratory. Dr. Allwood is here in Greenland to investigate recently published findings of possible stromatolites, or microbial fossils, dating back to 3.7 billion years ago.
It's always when I go and see some rocks and outcrops in the flesh, that it's so much more eye-opening and informative than it is to read about them in papers. And absolutely the case with this one. When I came to see them after that paper was published, I very much doubted that interpretation, and I thought, well, we need to do 2 things. One, we need to put a paper out, and secondly, we need to do a workshop and bring a lot of people out here to also see what their opinion is, reach some sort of a consensus on what the right interpretation was.
Extraordinary claims require extraordinary evidence, and a finding like this requires further investigation. Dr. Allwood has gathered a team of astrobiologists and will now travel by helicopter into the wilderness of the Ishua Greenstone Belt.
So we're out here to study an outcrop that there is some controversy over. There's a group of authors that has made a claim that there are biosignatures in the form of stromatolites in these rocks, and there's another group of authors, I happen to be one of that other group of authors, that has refuted that claim. So we're out here in Greenland to study those outcrops in more detail and to try to get a sense of the geology that surrounds those potentially stromatolite-bearing outcrops and try to get a sense for what the ancient environment looked like at the time that those rocks were forming. The claim was such a big deal because if it proves to be true, then this pushes back the earliest signs of life in Earth's geological record by a couple of 100 million years.
It means that the window of opportunity for life to emerge doesn't have to be very big. You know, literally, as the last bombardment is occurring, that you can say that life can take hold. At least our one example that we have that life took hold. Go to Mars. It means that it only also had to maintain its conditions, its sort of cradle of life, its its opportunity for life to emerge for that short period of time. It didn't have to sort of maintain it for a couple of 100 million years longer.
And when you go back to those very old rocks, they're usually altered and deformed, and it's very difficult to find those signs of life. But those are also the most interesting rocks to look at because we don't know when life originated on Earth, and we don't know what that earliest life was like. So the record that we have from geology is in these rocks that are very difficult to interpret.
Wonder which way I'm going to put it.
Yeah. Sampling here in Greenland is, it's not all that different from sampling anywhere else. A geologist's tools are kind of the same no matter where you go. You need a hammer, a chisel, a little, hand lens to look at the rocks up close, field notebook, camera, and you record your observations, and when you think you've zeroed in on a piece of rock that might be worth taking back to the lab, you get your trusty rock hammer out and just start banging away until the sample comes out.
When we're looking at rocks, trying to understand if they preserve evidence of life, we look for things in the rock that cannot form without the influence of life. They can change the chemistry, and they can actually change the shape of the ground. And they can make things like peaks and domes that are sometimes unique to the biology.
Again, I think here what you need to do is look at the context of the rocks around those stromatolites and try to get a sense for what that...
Came from the outcrop. We've got that more sort of cut and polished face there. And if it was really a cone-shaped structure, then... See in the back of the hole there, that's about 14 centimetres depth hole, and you're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. Got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front and it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what those understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.
The rocks that we're looking at here in Greenland are similar, if not identical, in age to the rocks that we're going to be exploring with the Mars 2020 rover. We'd like to think that we can use the lessons that we take from studying the Earth's geological record and apply them when we start exploring the geology of Mars.
One of the really interesting things about searching for life on other worlds is, as a scientist, I have to actually, when I'm looking for life anywhere, I have to actually have a model of what I'm looking for to help guide my observations. And so by looking at these places that are very difficult to interpret on Earth, we get that practice and experience of how do we look at something and what are the questions that we need to ask and what are the observations we need to take to be able to answer them.
Any claim that is made about a biosignature on Mars is going to be debated. So I think that this workshop gives us an opportunity to exercise our ability to have civil disagreements over matters of scientific importance, because I think we're going to be doing much of that with the data that comes back from Mars as well.
I think seeing the rocks in the flesh is just so important. Can't do that for many people, so I think the next best thing is to try and recreate that in a virtual terrain sort of field trip kind of thing. That's what we're trying to do.
So OnSite is an application that we developed for the Mars Science Laboratory mission to help the science team that works with the Mars rover understand the context of the environment around the rover.
And it provides scientists the ability to basically meet on Mars. So it's taking Martian data down from the rover and using photogrammetry to stitch it together to create a 3D model of the outcrop. And then scientists involved in the mission and engineers as well. Next, we're also using LiDAR imagery out here, which is something not available on Mars. So that's using a laser scanner to basically three-dimensionally scan outcrops and get higher fidelity data so that we can get some very accurate information.
Yeah, so this is the map of the primary outcrops and the laser scans. This is the A outcrop here. Scenario because we're limited to the instruments on board the rover. The rover doesn't have LiDAR. It'd be great if it did. So all we have are the 2D images to work with. 3D reconstruction from 2D images has been part of the Mars missions all the way back to Pathfinder in the late 90s. But it's always been on a per image basis from one rover position. So one of the innovations in OnSite is we started combining rover imagery from multiple rover positions. So if the rover's parked next to a rock and the next day you drive around the rock, you can take imagery from those two positions and take all of the rover drives from landing to the current position, register them all together so you could walk from the landing site to the current rover position, seeing high quality 3D imagery all the way. So OnSite was started in the context of the Mars rover missions, but the capability that OnSite and tools like it provide is really, it's a virtual presence and situational awareness in an environment that's hard to visit. Mars is an extreme example of that, but where we are today in Western Greenland is not quite as hard to visit as Mars, but it's certainly not easy. So you can imagine geologists going into the field to these remote locations and bringing back not only their written field notes and photos, but a 3D capture of the environment that becomes kind of an immersive field notebook that they can revisit, they can share with their colleagues and with the public and help to communicate what that environment is like in a way that's really hard to get without actually being there in the field. So I don't think this technology ever really replaces a human in the field. Whether or not humans will go to Mars is not my expertise. But if and when humans do go to Mars, only a select few will go to Mars. But with this kind of technology, they can bring along experts from Earth to extend their knowledge and share that experience with the public, so the whole world gets to go along, for the ride.
So I've never been here before, and the landscape in this environment is just, my mind has been blown being out here for a couple of days. I mean, the scale of the glaciers, the complete lack of vegetation in this area, other than sort of, lichens and moss, it's kind of an otherworldly place. It's really starkly beautiful. I think in terms of why anybody should care about these rocks, I mean, they are the record of some of the oldest processes occurring on our planet. I mean, there are very few places that preserve rocks this old, and so they're really a precious resource for geologists to understand what was going on the Earth, close to, in its infancy. So it's an important and special place.
I will gain a huge insight into these particular rocks, but it will also increase my understanding of how you actually demonstrate that something is or isn't a biosignature that I will apply in all my other work.
It's the ability to minimize the ambiguity before it even gets to the publication, minimize the ambiguity and minimize the bias. When it gets out into the press, it's going to be that much more considered, that much more robust. I think that's what's the best outcome of this workshop.
To observe with Hubble, we actually have to plan out pretty far in advance. And for the outer planets, what we do is we pick the time when they're at opposition. And that means that it's opposite from the sun, from the Earth's point of view. And that basically gives us the highest resolution view. That's when Hubble is the closest to each planet, even though that doesn't vary much over a year. And the planets are a little bit more challenging because they move. And so Hubble has to find guide stars first that tell it where it's pointing in the sky, but then it has to track those planets. So it has to move following the planet across the sky. And so that has to be interleaved with all the other science program Hubble's doing every single day. And so it's very carefully coordinated to fit in as Hubble then orbits around the Earth. And so it gets planned out down to the minute of exactly which image we're going to take in which filter for each of those planets. So it's a cosmic dance of getting Hubble pointed in the right place, moving in the right direction, and tracking all at the same time. The OPAL project, or the Outer Planets Atmospheres Legacy Program, is an observational program using the Hubble Space Telescope. And what we're doing is we're looking at each of the outer planets every year so that we can build up a time base using the exact same facility and the same instruments, so we can actually track what's changing over the years on each of those planets. And it started really with Jupiter. In essence, we were trying to look at the weather on Jupiter. And as we're trying to understand weather, we know even here on Earth it changes every minute, every hour, every day. And we didn't have that kind of time coverage, but we also didn't even have long time coverage to look at things that changed over seasons. And so we had this big gap in our knowledge where we just weren't getting frequent enough data to be able to trend any of these things. And the idea kind of came about to look at a legacy program where we built up a legacy for Hubble within the planetary community. And in 2014, we started with our first observations of Uranus. And the first thing I think we noticed was Uranus had a very prominent polar cap. It was very much brighter and getting brighter over time. We've watched it over the last few years get much brighter. Neptune, on the other hand, has been really quite interesting. The first thing we noted was it had a lot of bright white clouds, and they were coming and going pretty rapidly at a lot of different latitudes. And so when we start looking at Neptune and Uranus as dynamic planets with changing atmospheres, weather, like we know now for Jupiter and Saturn, we realize that we have a lot of gaps in our understanding. And so we've been able to use the Opal program to track how much cloud cover we have from year to year. But the other thing we can do with Hubble that we can't really do any other way is look for dark spots. And so the Great Dark Spot was this big, iconic feature we saw with Voyager. And when we looked again a few years later, finally when Hubble was online, it was gone. And that kind of surprised us because we were used to the Great Red Spot, which doesn't go away we see on Jupiter because they form and go away on much more rapid timescales. The latest image of Neptune is really interesting to me because we don't see those bright white clouds we've been seeing the last few years. As a matter of fact, the only thing we see in that particular image is this great dark spot. And so in a lot of ways, it brings us around full circle because this looks so much like the Voyager image from 1989. And that was pretty surprising to me, not to see as much cloud activity as we've been seeing in previous years. The Opal team's actually a fairly small team. There's only 3 of us, but our data is immediately available to the public and any other scientist that wants to use them. And so we do that, as well as our own scientific analysis. I think having so much Hubble data now, there's just so much in there to study. And, you know, as a scientist, that's what drives us, is trying to solve mysteries, trying to look for new mysteries. And so having these long-term data sets with just such rich numbers of features in there, there's always something to go look at. And it's certainly going to keep us busy for years to come, even when we're not getting any more data.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis I to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the ONC building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the O&C. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module, such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the O&C's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, and then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
On into this vehicle. It's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis I.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European service module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. it hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of 2 young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the ONC, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year. This is our time and what folks have worked so hard for.
Now we're going to continue with processing, get that thing checked out, fueled, get the launch abort motor stuck on top of it.
With fueling of Orion's crew and service modules complete, the spacecraft moves from the MPPF into the Launch Abort System facility.
We just finished fueling the spaceship, and we moved it to the LASA facility, the Launch Abort System facility, to put the Launch Abort System on the top of Orion.
And in July 2019, teams completed a critical test, the Ascent Abort 2 flight test, to validate the Launch Abort System works as expected. After reaching an altitude of about 6 miles, where the test spacecraft experienced high-stress conditions expected during launch, the abort sequence triggered. Within milliseconds, the abort motor fired to pull the crew module away to safety. Its attitude control motor flipped the capsule into the proper orientation, and the jettison motor fired to release the crew module for a splashdown in the Atlantic Ocean.
I feel, just honored and humbled every day to be able to work on this.
This rocket is just going to be absolutely amazing.
Now that the spacecraft's launch abort system is securely in place, Orion is ready for the next stop on its path to the pad, the Vehicle Assembly Building. Once inside, the spacecraft will be placed on top of the Space Launch System rocket, the most powerful rocket the world has ever seen.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
The sun would first stir life on our planet. Gradual shiftings and upheavals would bury creatures and plants beneath the surface of the Earth. There, they would fossilize, eventually turning into huge reservoirs of gas and coal.
Oil made possible one of the greatest inventions of history, the internal combustion engine, which gave us mastery over the air.
Pollution grew around us, until one day, at last, we noticed that something had gone wrong with our once pretty world.
Just in time, the satellite now gives us a view of pollution impossible to get in any other way.
Scientists and researchers continue to develop various technologies to cut fuel consumption through aircraft structure and engine design.
Lightweight wires and electronics replace mechanical linkage.
NASA researchers see vertical takeoff aircraft as commercially useful. These types of aircraft use less room for takeoff and landing and keep noise and air pollution lower than our present commercial planes.
One of the most unusual and highly experimental aircraft ever tested at Dryden was the Gossamer Albatross. The Albatross was human-powered and pedaled like a bicycle. The man who designed the Albatross also built the Gossamer Penguin, the world's first flight-worthy sun-powered plane.
ERAST is NASA's environmental research, aircraft, and sensor technology program, and its mission is to develop aircraft that are capable of flying very high and very slowly, primarily to do atmospheric sampling and monitoring of the global environment.
Solar power offers some unique capability for flying in the stratosphere.
The Helio should be able to stay aloft for up to 6 months at a time to function very much as an atmospheric satellite.
What's very unique to the solar-powered airplanes is that they are not polluting the very atmosphere that they're trying to take samples from, so they're ideally suited for that purpose.
These vehicles can help us attain a desirable balance between technology and nature. The stakes are high as we speed toward a challenging future.
Solar-powered aircraft don't really work well at nighttime. This is a way of compensating for the inability to get energy at night. The airplane flies off the energy provided by the laser.
This is the energy to a flight vehicle to achieve truly fuelless flight.
NASA Aeronautics continued its green aviation initiatives, cleaner and more efficient, while increasing the safety and comfort of passengers.
With this mandate to significantly lower noise and emissions and increase performance for subsonic aircraft, there will be a need to address virtually every aspect of the current aircraft configuration.
We're using a blended alternative for the emissions of the aircraft.
People have done life cycle studies to look at the carbon balance, which takes into account the amount of energy that you use in growing the plant, processing the oil. Some of the studies have shown about a 75% reduction in the amount of CO2 that you get using camelina compared to a conventional petroleum-based fuel.
NASA started investigating alternative fuels as a way of reducing the carbon emissions from aircraft, but there's other benefits of these fuels. They produce much lower levels of soot, and also they do not have sulfur contaminants.
Hopefully there will be a fairly significant return on the investment in terms of improved public health and environment.
Everything within subsonic aviation now is looking for efficiency. We're looking at structures to make aircraft lighter. We're looking at various propulsion systems in order to make them more fuel efficient, and we're looking at configurations to lower the noise impact of community noise, essentially looking at an environmentally responsible aircraft.
We really think this airplane is revolutionary. It's a big jump in technology from the tube and wing kind of airplanes that you see today. It's much more efficient. I like to say it's like a hybrid car compared to a regular car.
It's exciting to think that we're contributing to the green aircraft of the future.
The aircraft now can be programmed to have, for example, engines that are more fuel efficient. Control the engines separately and also more closely and carefully.
This is NASA's first all-electric crewed aircraft.
We can use electric propulsion systems and aircraft design
in an interactive way. The wing itself is designed so that the electric motors enable extra efficiency in the wing itself.
There's several different types of airplanes that can benefit from electric propulsion. The one that's gaining a lot of interest right now is the smaller version, the air taxi type vehicle.
In doing the work of developing these systems, integrating these systems and so forth, we have helped industry along their path.
We've been able to deliver lessons learned on batteries, on how you do the power electronics, how you build up the motors. And so X-57 really has been a pathfinder early on for electric propulsion.
The next generation of vehicles, they're going to be much greener and much more efficient types of propulsive technology.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Something has now emerged that might make even our most elegant theories workable.
Scientists developed equipment which would be able to think.
Machines that do things and make choices without human beings. That uncanny spectacle is automation.
Capable of storing, processing.
Calculations that would ordinarily take hundreds of man-hours. Unique ability to check itself on possible errors.
Cheaper and quicker and better.
Electric eyes, limit switches, servo mechanisms.
Secretary, librarian, banker, teacher, medical technician, bridge partner.
Volumes of changing data into a continuous flow of interpretations. Aladdin's lamp couldn't do more.
Jaws, loading machines, electric drills, it's all automation.
Computers have taken wing.
By the late 1960s, digital computers had become more available.
Using data about the aircraft's performance, the computers vote on the correct amount of control deflection to make in response to the pilot's stick and rudder movements.
This system could make air travel of the future smoother and safer by reducing aircraft vibration through automatic response from the computer to the aircraft controls.
We did the digital engine control. We had an early large digital computer that ran the engine and the inlet and exhaust system.
We did an integrated control study to provide digital control of the inlets, autopilot, throttle, air data, and navigation system. A digital computer here, major improvement in the capability of the airplane.
Test pilots are flying a plane without having to leave the ground. It's a new way of flight testing advanced aircraft that's both more economical and less hazardous. A research pilot in a realistically recreated cockpit on the ground, complete with flight controls, flies the remotely piloted craft using computers and television.
The airplane includes computers. Those computers take stick command and
continuously monitor what the airplane is doing and compares it to what the pilot wants the airplane to do.
The computer signals the control surfaces to not only execute the pilot's maneuver, but also to counter any attempt by the X-29 to veer out of control.
Fly up.
Yikes! No doubt about it. We didn't get a roll from that one.
You've got
New initiative in the artificial intelligence area, and it's called aircraft automation. The technologies that end up coming out of this would be autonomous flight vehicle technology.
ERAS stands for Environmental Research Aircraft and Sensor Technology. Platforms that could fly higher and longer than the current piloted airplanes, do science missions and other commercial applications.
Primarily the dull, dirty, and dangerous.
We can go all the way up to where the airplane can fly itself completely autonomously with no input from anyone on the ground.
Fly up to 50, 60,000 feet, fly a circle loop perhaps over a city, providing the capability that a satellite now does.
Now that we can fly for on the order of 8 to 10 to 12 hours, we can look at long duration processes, biogeochemical cycling, looking at carbon and nitrogen moving through an ecosystem.
To sort of kickstart a commercial UAV industry.
The technology that we've seen here in this test is what would be the foundation for a follow-on program to really address the issue of how can UAVs routinely operate in the national airspace system.
The primary benefit of this technology is the ability of it to adapt to the unknown, whether it be a system failure, battle damage, icing on the wing, or flying in an unknown atmospheric environment.
The aircraft may be able to be flown, but the pilot may or may not be able to find a solution to how to fly that aircraft.
Neural net control systems where the controls are going to teach themselves and keep getting smarter from flight to flight.
It can reconfigure the airplane in an optimal way in order to give you the best flying qualities.
Okay.
There is no operator of the vehicle itself on the ground. Basically, the role that the human plays is more in managing the mission, an orchestra director, not the instrument player.
The vehicle will complete all the autonomous actions necessary to release the weapon optimally positioned to hit the target.
One of the next things that we'll be demonstrating in UCAV is the collaboration amongst aircraft. How do sets of aircraft interact together in almost a social form?
We're going to examine the feasibility and technical utility of actually being able to fly two airplanes or multiple aircraft in formation with each other.
Now the trick to this is to make sure that they fly in formation closely enough that they can extract the advantage without obviously running into each other.
The station keeping would be fairly close proximity for hours. The workload on the flight crew would be quite high, so we started to develop autonomous algorithms to do the station keeping. So you basically would have an autopilot that you could engage.
The computers are flying the airplane without your stick input, even in the system, to allow a piloted airplane to take 2, 3, or 4 unpiloted vehicles on a long distance trip.
We're just getting started on this technology. We'll use this technology to refuel unoccupied combat air vehicles.
The basket's slightly moving. Looks like it's going high. Okay, it detected a miss and came back on its own. So I did not do anything. She's got it. She's got it. Congratulations, guys. That was fantastic.
The Autonomous Soaring Project has one simple goal, is to program a small UAV to automatically detect that it's in an updraft and then use that updraft by circling. There's a wide variety of applications for this technology to help UAVs do things like forest fire detection, police surveillance, border patrol, and weather monitoring.
If the aircraft was damaged, you don't have to necessarily just rely on the pilot to compensate and fly the airplane. Adaptive flight controls, autonomous flight controls, different things where we're using the airplane to assist the pilot.
It will take over basically the controls of the airplane as far as flight stability.
The platform precision autopilot is capable of staying on a given path within about 15 feet. It allows the synthetic aperture radar system to fly over essentially the same path more than once. This obviously has some potential applicability.
We went out and tested the system and based them on actual mishap cases. It prevented every single mishap. What we're developing here is merely an aid should the pilot get distracted or disoriented. By automating it, we can take out the pilot reaction time entirely.
The computer takes full control away from the pilot for a very brief period of time, and it redirects the trajectory of the aircraft to save the human.
ADS-B is automatic dependent surveillance broadcast. It's equipment on board an airplane that transmits its position and velocity information twice per second.
We were really trying to prove that we could use ADS-B as a way to do coordinated flight between multiple vehicles.
This system is present on a lot of manned aircraft, but we were one of the first UAS to perform testing of it in the national airspace. NASA has a project for integrating UAS.
So one day, the UAS could hopefully fly with other commercial airlines and everybody will fly together safely.
There's various benefits to integrating unmanned aircraft, being able to monitor specific weather systems, monitor fires, delivering packages to your doorstep.
Operations to deliver medical emergency supplies, infrastructure, surveillance, and monitoring.
The technical side is a big challenge, but being able to integrate them safely is maybe even a bigger challenge.
To have thousands of these vehicles flying at the same time, you're going to have a lot more automation on the vehicle and in the airspace system.
Regulations for operations of the vehicle, regulations for airspace, regulations for infrastructure.
These aircraft are going to be highly autonomous, piloted, optionally piloted, unpiloted vehicle.
It's not just looking at the UAM, it's actually integrating the small UAS, the package delivery, or even the larger cargo delivery.
Subscale aircraft, we use those for a variety of reasons, to test things like new technology, which could be hardware or software, or even a completely new vehicle. You can do almost anything you want without much risk. And you can realize those gains very quickly. We're researching some level of autonomy. The aircraft, in most cases, are capable of taking off, flying around and landing without any human intervention. Things like ardupilots and multi-rotors and flying computers are allowing kids to play with research type tools that they never had access to before. So it's sort of driving in this new robotic learning type environment that never did exist.
We're so excited to have this special collaboration with NASA Johnson Space Center, and we're honored to present this historic event. I'm also very excited to introduce the moderator for our program. She's also the first African-American woman to be the director of NASA Johnson Space Center, Vanessa White.
I'm happy to be here with you all at Space Center Houston. Today, we're going to hear from former and current astronauts who will share with you their own journeys to space. Robert Kirby, Jeanette F., Bernard Harris, Leland Melvin, Stephanie Wilson, Victor Glover, I'm going to start with a question, and I'm going to throw it out and would like for everyone to have an opportunity to give a response. Describe to us a picture of who you thought you would be as a student or young child. What were you studying, and what type of person did you think you could be? We'll start with Stephanie.
Well, when I was in middle school, I was very fortunate that my parents were very supportive and education was very important to them. And I was given a school assignment in a career awareness class to interview somebody that worked in an interesting career field, and I was interested in astronomy at the time. And after talking to a local area astronomy professor, I was fascinated by his work. I thought that that would be an excellent way to contribute to being a STEM professional.
When I was a really young kid, probably 6th grade, my mother gave me this age-appropriate non-OSHA certified chemistry set. And I mixed these two dissimilar chemicals and created the most incredible explosion in my mother's living room. I burned a hole in her carpet. And my mother she was small, but she had the power to knock me off the... But it was that moment that I realized that I could be a chemist because I'd already done it. All I needed was a lab coat and goggles. So, so chemistry was something that I learned at an early age, and I love sports. But I never saw myself going into the NFL because just, I don't know, for whatever reason. But I did see myself as a scientist. So STEM was always something that was very critical to me.
It's funny, I think it all starts with chemistry because my mother was a chemistry teacher. And as I got older, the chemistry set kept getting bigger and bigger. I didn't burn a hole in her carpet, thank God, because I might not be here if that happened. But that was always interesting to me. And I grew up in Baltimore during a time when Apollo was big, so I just kept seeing these larger and larger rockets being designed. And it just, design always interested me, and I always thought I was going to be a design engineer. That's what I was going to be.
So as a kid, I didn't really know who I thought I would be when I grew up. I just kind of, did my thing and, did my work. And one day, when I was about 9 years old, my twin sister and I, we brought home our report cards. And back then you had a report card and you had a row of all your grades and you could see immediately, okay, you had all A's or B's or whatever. And Janet and I, we were pretty obedient kids, and we knew that if we brought home anything less than an A, our mother was not gonna be happy. And yeah, she knew how to throw a shoe or whatever to make sure you stayed in line. But one day we brought our report cards home and my older brother, he goes, wow, you guys can probably become aerospace engineers or even an astronaut. And my 9-year-old brain said, well, they'll never pick me to be an astronaut, but I can definitely become an aerospace engineer. And so at 9, I had set my sights on becoming an engineer, an aerospace engineer. I didn't even know what it was.
Version of who I saw, what I, that I could become was my father. My father was a police officer in Pomona, where I grew up. And so I just really was blown away by the way people responded to him, and so I looked up to him, but other people clearly didn't. So I wanted to be a police officer like my father. I also looked up to Marcus Allen, Los Angeles Raiders running back, and I wanted to be like Marcus Allen. So sports were important. My father and his influence were important. And then I and drive one of those, and so the interest in tinkering and machines and speed and power and sports, and also just wanting to be a good person like my father, those things all wove together and one way or another led to me being here.
So I was listening to the others talk about what inspired them, and what inspired me was what inspired a lot of American kids back in the 60s. I grew up watching the space program. I learned very early that I liked science and science fiction, so I always like to say that I was an original Star Trek fan. And so that got me exposed to space on television. But in real life, I watched the program develop. The Mercury program, Gemini program, Apollo program. And in 1969, when I turned 13 years old, I watched Neil and Buzz Aldrin land on the moon, and I said, I want to follow in their footsteps.
Here, men, from the planet Earth, first step foot upon the moon. July 1969, AD.
And as I looked around at NASA, to the point that we're talking about race, I didn't see anybody who looked like me. I didn't see any women. In fact, the first people that they selected to be the creme de la creme, the top astronauts were white guys, all white guys. And so I remember saying to myself, even though I don't see anybody who looks like me, I'm still not going to let that deter me from deciding on what I wanted to do.
Did race ever play a role in the idea of who you could be?
Did race ever play a factor? I would say one major area where race played a factor was in high school. So as I'm kind of starting to develop this plan on how do I become those things, and I knew college was in my path, but I didn't have any, neither of my parents went to college. So, we were having to figure this out together. And the Naval Academy came to my house and said, do you want to play football at Annapolis? And I was like, nope, no thank you. And West Point said the same thing. And I said, nope. And Annapolis actually came back and says, would you like to wrestle? And that was really my main sport. I love football. I wanted to be like Marcus Allen, but I was a better wrestler. And you want to come grapple at Annapolis? And I said, no, thank you. And so I don't know if any of you have seen the movie Boys in the Hood, but the father in that movie is Furious Styles. And the conversation that he has with his son is something very similar to how I felt. It was that there wasn't a place for me in the military. And so I go off to college, and one of my mentors, I'm in his office waiting for him to come in. He's one of the few black faculty members at my university. And he comes into the room, and as he steps in, he is in this full regalia, the black suit with the gold around the wrists and the hat. And I was like, wow, sir, when did you enlist? And he said, I'm actually an officer in the Navy Reserves. Boom. The next version of what I could become. And that, to me, there's so many lessons I pulled from that. But the power of exposure and seeing yourself in something.
Hello, everyone. Victor Glover here, checking in during my 6-month mission aboard the International Space Station.
When we were growing up in the 60s, it was interesting to see some of the greatest feats of humankind on the television, little black and white television, but turn the channel and see some of the greatest challenges that we had in the United States at the time. So, watching Martin Luther King at the same time we're going to the moon, it was incredible. Talking to my mom, who was a teacher, who said, would always ask us, what do you want to do when you grow up? What do you want to do when you grow up? And kind of pushing us. And I remember going to her and saying, Mom, I know what I want to be. I want to be an astronaut. And she said, that's nice. And started to turn around, but then again, she turned back, she said, but if that's what you want to do, you can be and do anything that you want.
Good time.
As a kid, I became interested in airplanes, and I liked making model airplanes and reading books on airplanes, and I was fascinated by airplanes, and so that proved to be what I find later on to be my passion.
I don't know if I had a vision of who I wanted to be when I was younger, but I will tell you this. I think I was born to be an engineer, and I think specifically I was born to be an electrical engineer.
I remember being in, I think it was 7th grade. We had this assignment before we could take off early to go to recess. So you had to write down where you saw yourself in, 10, 15, 25 years. And I simply wrote down on my little assignment sheet that I want to be able to look up from where I was working and see the curvature of the Earth from space. And I plunked that down on the desk and headed off to recess.
My mother was my main inspiration. They discovered art when I was in preschool, and she had me in every art class that ever was. And she got me a library card when I was 4, and we had conversations, and she would talk about astronomy and orbital mechanics and space.
I grew up in the segregated South, so I am a son of the South, if you will. Blacks and whites went to separate schools and had separate facilities and everything. But in the mid-50s or so, there were lots of programs on television that talked about life in the military and actually promoted the military. So that's where I saw the Naval Academy. I fell in love with the uniforms more than anything else, and the beauty of what's called the Yard. It's the campus of the U.S. Naval Academy. And it didn't hurt that all the pretty girls from all over the Northeast came there on the weekends looking for husbands.
You sort of assume that astronauts never had hard times. Yes, I've had hard times too.
At some point in everybody's life, they're going to have that moment where they're going to have to step off the ledge. They're going to have to just make that push out into the void. And it's always, always, always going to be a extreme gut check.
But I think the important thing is to keep your goal in mind. And my goal was to succeed and eventually become an astronaut, and to be patient enough in order to hang in there. In other words, don't quit.
Don't ever let anybody tell you that you can't do something, and always have an alternative plan if things in your life kind of go awry.
You never learn a damn thing with your successes. And so the idea of failure is probably the best thing that can happen to people who want lasting success. because on the next time around, you think your way through a better way, a more creative way to get through to your success. And then it forces you to be creative.
Well, I feel very honored to be the first Black astronaut to fly in space. And in that role, one of the things that I wanted to do is not only be a role model for African Americans on the ground, but also be a leader in helping pull other Black astronauts into space with me.
It is hugely important to see people who look like you and who can inspire you, especially in fields that you want, because it shows you, I mean, right there, the people that are there that you can touch, that you can feel, that you can reach out to, that you can talk to, that, you know, if they can do it, then there's a chance for me to do it too.
When I was first thinking about becoming an astronaut, I asked my father, can Black people become astronauts? Remember, this is just a few years after the Civil Rights Act of '64 had been passed, and there was still a lot of segregation. It didn't go away overnight. And he looked at me, he says, not only can you be an astronaut, there have been people, Black people. There was at least one Black pilot who was selected to be an astronaut. But the fact that he had gone out there and had blazed that trail meant to me as a 5-year-old boy that there was no limit. Nobody's going to stand in my way. The only way I was not going to become an astronaut is if I decided not to become an astronaut. And I needed that role model out there to inspire me.
I have a connection to all the African-American astronauts because in some way either we were in the office together and so we share experiences from that, or they came before me and I met them, and it's just a small sorority/fraternity, and we try to support each other, and we get together every once in a while and talk, and so it's a great group to be a part of, and I appreciate each and every one of them.
And the heroes themselves.
I want to frame this as this is all about you guys because you are our future. And again, he said, ask us anything, but the transparency and the authenticity is so important that you guys go back because you're the leaders.
What would the next big culture shift, what would you like to see? What would you want it to be?
When I think about what Elon Musk is doing, and Jeff Bezos, these billionaires are spending a lot of money on these new platforms that's going to enable us to have that life, to have that economy in space. But then when I go to our communities, our Black and brown communities, and see what the kids are doing and seeing whether they're prepared for that future, that's when I'm going to go, oh, we got a lot of work to do. Because if we're not there, and we're going to be stuck on Earth, right? So they're going to leave us behind. So my vision is that we don't get left behind as a people.
I got to tell a quick story. So yesterday, I was in National Car Rental, getting my car, and this little lady was right here. I was like, hey, she saw my NASA shirt on. She said, NASA, oh, is there this thing tomorrow at Space Center Houston? I'm like, yeah, are you coming? Oh, no, I didn't fill out the application. No, I didn't do it. I said, and she was supposed to be off yesterday, right? Mm-hmm. She was there, I was there, and she is here today because she was supposed to be here today to hear this. Chemistry major, gonna rule the world one day, maybe be where it starts.
Like, we're talking a lot about what we see for the future and shaping a lot of the stuff for the future. And there's so many schools, so many elementary schools that don't have a lot of funds and et cetera, but people like you come in and they talk and then my life has changed. Now I'm an astronaut. That's crazy. For me, I've always wanted to be a scientist. I've always wanted to work in NASA. I've always wanted to do, this has been my entire life. When I was 2 years old, I drew a permanent marker on the wall, all of my friends, and they were all astronauts, et cetera. And I've always known what I wanted to do with myself. So it was beautiful that I felt like the universe came in with a confirmation, hey, well, you're a little bit nervous about starting classes back up, but here goes Leland. And he comes in with all this positivity and like, yeah, you should do it. And I did.
Honestly, coming from places where I came from, I never see anybody aspire to work for NASA to be an astronaut or to be in these fields. So seeing people, these heroes, reaching these heights, it lets me know, hey, you know what, I can do this. It's possible.
I often find myself, sometimes having a lack of motivation. I often tell myself I can't do something if something gets too difficult, or if I just get frustrated, or if I fail too many times at something. So I often just see myself kind of like almost giving up. So it's all like, for y'all to be in such, leadership and strong positions, accomplish so much within y'all time, like, how do y'all stay motivated?
So one thing that I think about, which can kind of seem like a burden at times, but it can also be the power to keep going. Like, I love thinking about the civil rights era and like the fact that when you see them getting off those buses, going to the March on Washington for Jobs and Freedom, say the whole title, they had bags in their hands. They didn't make those sandwiches. There was a party making sandwiches, and then there was a different group of people that took the sandwiches to the people, and then there was a different group of people directing them to get on the buses. They were organized, right? And that work was done so you could sit in this seat. And when you think about that, our legacy runs from the very beginning up to you right now.
It's deep, bro.
It's your job to keep it on. And sometimes that can seem like a burden, but it's also a privilege. We are connected to all that. We come from greatness.
What are the emotions that come to your mind when you think about Juneteenth and the role that you play today?
Oh, wow. So Juneteenth is a way that we honor the fact that right here, not far from us, after the Emancipation Proclamation was signed, we had slaves that were still enslaved. And it was 2 years after that process that they were able to actually attain the freedom. And so Juneteenth is now received a lot of attention, but it was something that wasn't widely celebrated. And so one, I'm encouraged to know that it's become something that is gaining national and maybe even global attention. But it also is a reminder that, we have come a long way, but we have a long way to go. The person who started the Journal of Negro History and then started Negro History Week, which is what we now celebrate as Black History Month. When he started it, he wrote in the journal, he said, we need not celebrate Negro history. We celebrate the Negro in history. What we need is history void of racial, gender, and religious bias, because it's our story, all of our stories. And so I'm just encouraged that we have a chance now to be a part of telling that story.
So Victor, I'm going to ask you, what strategic steps are needed to offer more persons of color in more active roles?
There's a lot of things we could do, and we don't have time. We could take all the time we have today to talk about just what we can do. But one thing that we must do is those of us who are already in this enterprise, we have to go and, it's not just like encouraging you. I love this saying. We say that we have space for you. Listen, we need you. We need you. When the baby boomer generation retires, the science and technology jobs that are going to go away, if you look at the university students in undergrad and graduate school right now, we don't have enough of you in science and tech to fill those jobs. So we need you. It is a national security imperative for you all to become the best you can be so that we can keep doing what we do.
And so we have an audience with students, and I know that they want to hear about your space time. So what was your most challenging time in space? Can you tell us that, Stephanie?
Probably my most challenging time was...
Solar array deploys starting on my mark. 3, 2, 1, mark.
And it's a smaller module. It's a connecting module on the end of the U.S. laboratory, but it allows our partner laboratories to have a connection point on the space station, our partners from Europe and Japan. And during that mission, we had installed that module, and it also required reconfiguring the electrical system. So we had to move one of the solar arrays from a central position to the end of the truss on the space station. And in order to do that with the robotic arm, basically have to fold up the solar array, move it with the robotic arm, and then extend it, re-extend it. And during that extension, we had a dynamic event.
Houston Alpha on the big loop. We detected some what appears to be a wraparound or some damage, and we're zoomed in on it on camera 24 right now.
So similar to what you may have heard about Apollo 13, where when we're in space, we have limited resources, we have limited materials, we have to fix whatever happens with what we have on board. Because of this relocation, it was hard for spacewalkers to reach, so we had to do something that we had not practiced before with the robotic arm and the boom sensor system that we used at the time for the orbiter. We hooked those two together, put the spacewalker at the end, and then sent him out to the work site with what we had fabricated on board, these cufflinks to tear across, to drape across the hole, to give the panel system additional rigidity so that we could continue the extension. So I say all that to say, we worked together with our mission control team to come up with a solution, but we had to use the resources that we had in hand, do robotics and spacewalking operations that we had not performed before, and rely on each other's and our skills.
It's a good day's work right there.
I'm going to go back a little bit because it ties into the story she just told. And so I go into test pilot school, and we, as a class, have to go to a conference. And at this conference, the keynote speaker is Pam Melroy. And Pam Melroy, who is, I believe, the second female shuttle commander, stands up and tells that story. She tells the story about the cufflinks. They use the cufflinks. And she tells that story. And that's the day I decided, all right, I'm throwing an application in. So I also think it's neat how our stories do link together, like you just said, and I think that that's beautiful, this legacy here that continues to grow and evolve.
I found myself immediately thrown into a leadership situation for which I was unbelievably well prepared, but I didn't know it, because my idea of what I was going to have to do as a leader, as the leader of NASA, the leader of human spaceflight, the leader of science, the leader of space stuff for the whole world. If you've ever heard of